Welcome to this Java developer course. In this video, I'll give you a high-level overview of the topics you'll learn and the impressive new skills you can expect. By the time you'll complete this course, you'll be well equipped to create Java applications and you'll have built some projects to showcase your abilities. So let's talk about the topics. We'll start by introducing you to Java and its importance to the world of programming. We'll first deal with the Java application structure, so you get an idea of what Java applications look like. Next, we'll move on to the basic block of programming, variables and arrays. After that, we're ready to see the difference between primitives and objects. Since objects play a very important role in Java, it's an object-oriented programming language, we better start with this really soon. After this, we're going to add more logic and be able to do some control flow of our code. And then we'll see how we can write and use methods. Once we have the basics down, you are ready for step 2. This includes some concepts that might sound very difficult right now. For example, we'll be talking about access and static modifiers. Also be dealing with the string and string builder class. And we'll see dates and times in Java. And we even introduce object-oriented programming, OOP. And we'll deal with constructors. So this is going to be tough. And we're going to include topics for OOP such as inheritance, polymorphism and encapsulation. But not to worry. I'll break them down into small parts so you can master them as well. And you'll need them, because these concepts are key to writing reusable and maintainable Java code. And also enums. So this is going to include some very difficult concepts. For example, when we deal with OOP, we'll be dealing with inheritance, polymorphism and encapsulation. This might sound very difficult right now, but not to worry. I'll break them down into small parts so you can master them. And you'll need them, because these concepts are key to writing Java code. Not to mention, they get us ready for the more advanced topics. And yes, we'll cover quite some more advanced topics too. We'll be dealing with interfaces and abstract classes. We're going to cover collection and generics, so that we can store multiple values in one variable. We'll also deal with exceptions, so that we know what to do when something doesn't go according to the happy path. And we're also going to be focusing on reading and writing files. Next, we'll see Lambda expressions, which probably sounds more intimidating than it really is. And then we'll be dealing with functional programming. After that, you're ready to talk about the Java memory in a bit more detail. And lastly, we'll be dealing with the basics of concurrency. This is quite a lot, but this will really enhance your programming capabilities in Java. After every module, you'll be doing some hands-on exercises to truly master them before proceeding. It can be tempting to skip those, I know that feeling, but I'd really like to encourage you to wrestle your way through. Practicing with the separate concepts will get you ready for applying your newly acquired skills in real life. And then we'll end the course with some fun projects, such as creating games like tic-tac-toe and hangman. At that point, you'll have a solid foundation in Java programming, and you'll be ready to tackle more advanced topics and frameworks. I really can't wait to see what you'll create. So, are you ready for this exciting journey? Let's start coding and transform you into a Java developer. Welcome to this Java course. In this video, we'll kick off your Java programming journey with some fun and easy hands-on exercises. Let's get started and make you fall in love with Java. In this course, we'll cover everything you need to know about Java, from basic syntax to advanced concepts. By the end of this course, you'll be well equipped to create amazing Java applications. But it starts at the very beginning. And we'll dive right in. Well, sort of. There's one thing I briefly want to mention first. Before we really dive into Java, let's quickly understand the difference between front-end and back-end development and where Java comes into play. Front-end development focuses on what users see and interact with. So there you are creating the application that's visible on the screen of the user. While back-end development handles the logic, data storage, and communication between the different components. Let's say that we're having a banking application, and we have a user who'd like to log in. They grab their device, for example their phone, tablet, or laptop, and they navigate to the banking site or they open the banking app. Then they want to log in and they enter their codes. But your phone doesn't know whether you're allowed to log in or not. Even though it has the app installed, it can open the app without the internet, but it cannot determine whether you can log in or not. So you enter your code, and that sends a signal to the server. And on this server, there's an application who can determine whether you can log in. But also this server doesn't know whether you can log in or not. In order to know whether you can log in, the server needs to communicate with the database. The database will then send a response back to the server, and if the user can indeed log in, the server will go ahead and process the page. If not, the server will go ahead and process an error message. Anyway, a response is being sent back to the device, and this is where you see the message that you can either not log in or you see your starting screen. And then, of course, in order to get all the data in your banking app, your phone is connecting with the server and the database constantly. In this web application, the front end might be built using HTML, CSS, JavaScript, Angular, Vue, React, those sort of languages, and that's meant for the user interface. Java is on the server. So the backend would be written in Java, and that would go ahead and manage the user data, process any registration requests, and also communicate with the database. So what is Java? Java is a popular backend programming language, and in the olden days we would used to do front end with it too. I'm not saying you won't ever run into that anymore, but today it's mainly used for web backend development, mobile app development, particularly Android, and even enterprise software development. Okay, now we can dive in. Let's see Java in action with some fun examples. Alright, so I want you to navigate to replit.com/languages/Java. You can also use another online IDE, but I'd like this one because here we can go ahead and create some Java without actually having to install anything on our computer. So I'm going to click on the sign up to code, and I'm going to continue with my GitHub account. And now I'm in the environment. So I'm going to skip the tour and I'm going to dive right in. Okay, so here's our first Java program already. I don't even need to write it myself. I'm going to modify it in just a bit, but let's explore the program. So I'm just going to hit the run button to show you what it does. And you can see the output in the bottom right. You can see it prints hello world. And that's it. You've now run your first Java program. So let's break down the code of a Hello World program. So as you can see, my first line is a little bit different because we had class main and now I'm having public class Hello World. But this is the class declaration. And in Java, everything is organized in classes. The next line is the main method. Java programs start executing from this method with this particular name. And then finally, the body of our method. This line prints hello world to the console. Now that we've created a simple Java program, let's expand it to make it more interactive. We'll ask the user for their name and greet them accordingly. So in here, I'm going to create a new line, like this. And in order to make this work, I have to go ahead and import scanner. Then I change this to enter your name. I'm going to process the user input using our scanner. And then I go ahead and I'm going to print the results. And now I'm going to press the run button again. And as you can see in the bottom right, it now prompts for entering my name. So I'm going to enter my name, and my name is Maaike. So there we go. And then it says, hello, Maaike. We now see the personalized greeting. If I would have entered a different name, it would have greeted that name. We've just added a few lines to the previous program basically, though we also modified the existing ones. But let's break it down. So here we say import scanner, and this imports the scanner class, which we use to read user input. Then on this line we create a scanner object that reads from the console. Then I'm skipping the enter your name, but if you pay close attention you see that in my example I used print line, here I'm using print. The difference is that the example on the slide is not switching to a new line, whereas the one in Replit was. So what I'm doing with the string name with scanner.nextLine is that I'm going to read the user input and store it in a variable called name. Then on the next line, I'm using this user input to print a personalized greeting, as you can tell, but I'm using the name variable in there. Well, congratulations! You've completed the Java introduction and you've even written some Java code already. It's very understandable if you don't get every detail yet, but that's exactly what I'm going to walk you through throughout this course. From here, just keep going and soon you'll be a Java programmer. This is just the beginning of an amazing journey. Join me for some more happy coding. Next, use the setup guide for your operating system to get your system ready for coding. Let's start with Java classes. And when I say classes, I don't mean this or this. I mean one of the most fundamental concepts of Java programming, classes. So a class is a blueprint to create objects. And now I'm probably mentioning some other things you don't know about objects. That's always the problem about teaching programming from scratch. Where to begin? It's like finding the very beginning of a yarn of wool. Alright, so objects are instances of classes. And you can compare classes and objects with blueprints of houses, and then the actual houses. The blueprint are the class, they define properties of the eventual houses. The houses are the objects, or sometimes called instances. These instances can have differences amongst each other. They're not the same objects, but separate objects, created based on the same blueprint. Great, so back to Java classes, a blueprint to create objects. You may wonder, what is in such a blueprint? Well, there's pretty much two things in there. We have data and we have actions. Data, also known as variables or properties, are the things that define the project. We'll see this in a minute. Actions, are sometimes called functions, are things that the object can do. There's actually some more details, but it's too early to look at this right now. First, let's move over to IntelliJ and create a simple class. We're going to be creating a class for a bank account. Here's how to create one. First, I'm going to be adding a new Java file, a Java class, and I'm going to call this account. The convention is to do this in the singular form. Alright, so here we have an account. We can see this is a class by the public class account statement. Especially the class keyword is the one that we're looking at here. It defines a class in Java. As I mentioned, classes have properties and actions. Well, let's first think of some properties for an account. Examples of properties of an account could be the owner, the balance, the minimum balance, and much more actually. But let's keep it simple for now. I'm going to give our class the following properties: a owner, a balance, and a minimum balance. So I'm going to say string and then owner. And this means that our account has a piece of text which can be recognized by the word string. And this piece of text is called owner. So right now, our class has one property, owner. There's actually a lot more to this, but let's just leave it like this for now. We're also going to be giving it a balance. So in this case, I'm going to make this a double. And a double is just a decimal number, which is actually something you can definitely not use to deal with money, but for this example, it's just fine. We're also going to be giving it a minimum balance, and also this type is going to be type double. So we're having an account and it has 3 properties now. Our account has an owner, a balance, and a minimum balance. Can you think of some actions that we need to be able to do with this account? This image can actually serve as some source of inspiration. We can actually withdraw and deposit money to our account. So let's go ahead and create these methods. So where do we create these methods? Well, we have created the properties inside our class account, and that it's inside can be seen by the curly brackets, one on line 3 and one closing on line 7. Everything between the brackets is inside the class. Since these methods are going to be part of the class as well, they need to be inside the curly brackets too. So let's go ahead and create 2 methods in here. I'm going to be creating a method deposit, and I'm going to say public. Let's create it void for now and call it deposit. At this point, we do need to insert some money here, so I'm just going to say double amount. And the exact implementation, I'm going to leave this empty. This is just a random comment. So what do we see here? We have a method, and it can be recognized as a method in different ways. But for now, just know that when it has a public in front of it, this means that it's accessible. Void means that the method is not returning any value. Deposit is just the name of the method. I could have called this anything, for example x, which doesn't make much sense. It's better to give your methods sensible names so that you can actually understand what they're doing by just reading their names. And then you always get 2 braces. And these braces, they specify the parameter list for the method. In this case, there is 1 in there. It's an amount and it is of type double, meaning it's a decimal value again. If there are no input parameters, you actually still need the braces, but then there's just simply nothing in between. Alright, more on methods later. Let's also go ahead and give this one a withdraw method, and this is actually something very similar. So I'm just going to say public void withdraw. We need a certain amount that we want to withdraw, and then there is going to be some sort of implementation. For example, we're going to be deducting it from balance, and we're going to check whether it's not going to be lower than the minimum balance, etc. But I'll leave all of this for a later moment. So let's go over our class once more. On top, we define that we're creating a class. It says public class account, meaning this is a class. And actually, I did not code this. IntelliJ did this for me when I created the new Java class. Then I mentioned the different elements a class could have. And classes could contain data and action. Data are the properties of the class. And in our case, these properties are owner, balance, and minimum balance. We also have 2 actions, one for depositing money and one for withdrawing money. Classes define the blueprint. They're one of the most important building blocks in Java. In this case, we've pretty much created our own type, which is an account. And it has 3 properties and 2 methods. We can go ahead and expand this later. For now, let's first see how to actually create instances using this class. Let's go ahead and create some objects in the next video. Objects are a key concept of object-oriented programming. That can't be too surprising, it's in the name. But what are objects? Let's revisit classes first. We now know what classes are. Classes are pretty much ideas and blueprints. And if you're anything like me, you'd agree that just ideas are fun and all that, but don't get you anywhere. Luckily, we can use these classes to create actual instances. Objects are also called instances, so you can use these 2 interchangeably, and Java people will understand what you are talking about. I briefly mentioned what they are already, but let's see what they are in a bit more detail first. And please mind, this can be tough to get your head around. I'll try to make it as easy as possible, and once you do understand this, you've made quite a step in Java programming, or any OOP language in general for that matter. The concept of object or instance might need some explaining still. I'd like to stick to the house and blueprint metaphor here. When we have a blueprint, we can create a house based on that blueprint. And we can create another house based on that blueprint. And another one, and so on. All of these houses are based on the same blueprint, but they're not the same houses. For instance, they have different addresses. Every house has a different address. And also, different families are living in all these houses. And details may differ, such as the color of the door, whether or not they have an extension, the type of kitchen, etc. You probably get the point by now. This blueprint and houses metaphor also applies to classes and instances. We can use a class to create an instance. An instance is the actual object that's made based on the class. For example, if the class is user, the instance is the actual user where all the fields have values. We can have multiple instances of the same class. They are all different objects of the same type. Let's move over to IntelliJ and see how to create instances based on our account class. So first, I'm going to create a separate class. And I'm going to call this class main. And in this main class, I'm going to create a main method. Don't worry about these details for now. We'll dive into this later. But we need this main method to be created in instances of our account. Well, we could do this in any method actually, but let's create it in this main method right now. So what I can do right here, I can create a new account using our blueprint of account, the class account. And in this case, I'm going to call my account account1, and it is of type account. And in here, I'm going to create the actual instance with the keyword new. I'm going to say new account. And this is how I create an instance of my type account. In the next video, I'm going to talk about class members in more depth. When we talk about packages in Java, it's less exciting than packages in everyday life. We don't mean packages like these. But let's unbox what packages mean in Java. Packages are a structure to group our classes. They're a bit like folders in your file directory. In fact, when you create a package, a folder is being created as well. But it's more than just a folder. We can create classes that are not part of a package. At least, so it seems. If you don't create a package, Java will put these classes in a default package. Let's see how to create a package and what this does to our code. Our account class is in a package called structure. You can see this on the first line. It defines the package structure. But you can also see it in the project structure on the left, where you have Java, and under there is this folder icon with a hole in it with the name structure. This is a package. But our main should not really be in the structure package. It should probably be in the Java package, which means I would be moving it to a default package since there is no package that's on top. So if I move this one to Java, and I'm just going to say refactor, you can see that this one is now no longer part of a package because there is no package statement on the first line. Let's create a new package. I'm going to right click on Java, say new package, and let's call this package example for now. If I'm going to move my main inside the example for now, I'm going to do refactor. You can see that the first line changes to package example. So classes that are part of a package always start with the package statement as the first executable statement of the Java file. So it doesn't make a whole lot of sense to have a main in a package called example. And actually it's not that bad to have it in structure since this is the module of the course that we're at. So I'm going to move my main back to structure and I'm going to delete the example. But not before I showed you that this is what it looks like in my file explorer as well. Here you can see my Java course folder, and in the source we have our main, here's Java, And as you can see, we have both a folder example and structure. I'm going to delete example here, and as you will see, it's also going to be deleted from my file structure. We have just created a package ourselves. Why would we want that, you may wonder? Packages come with some advantages. We can group our classes and organize our application better. In one group of classes, we need to have unique class names, but double class names are allowed to exist amongst different packages. And lastly, we can import the classes of a certain package all in one go. Again, this helps to organize our application. So, we just created a custom package, but Java actually comes with a lot of built-in packages with a lot of built-in code for us to use. We call these Java APIs sometimes. We can import packages into our application with the import keyword. You've already seen that we were using the import structure.account when we were using the account in our main class outside of the structure package. You can still see it on line 3. However, we are in the structure package again, so we no longer need this line. But say that in this method I wanted to use a special built-in class called localDate, which is used for creating dates. You can see that as soon as I try to use this, it's actually going to import the java.time.localDate. The java.time is the package where the class localDate is in, and we need to import it if we want to use it in our class. We could also import the entire package in one go. And now we're importing all the classes in this package. Is that a good thing? Well, in this case, definitely not, since we're only using one. And now we're importing a whole lot of stuff that we don't need. But you must know that this is a way of importing all the classes in one go of a certain package. We need to import whatever is not part of our package. So it doesn't matter whether this is a built-in Java API, such as the ones you're seeing here, or a class of ourselves that lives in a different package. We'd have to import both of these. At this point, we've seen some of the high-level building blocks of Java applications. It may not come as a surprise to you that there are some more important building blocks, but they will reveal themselves later. The building blocks we've seen so far are classes, class members, and packages. For now, we have enough basic building blocks to zoom in on some other concepts. But first, let's zoom out for a second there and look at the structure of a basic application based on what we know so far. We have seen two of the most important concepts of Java already, classes and instances, also called objects. We're going to have a closer look at the class members now and how to use these on instances. Roughly speaking, there are two types of class members. Some of them describe the specific instance and some of them belong to the class. Let's have a look at the first group first, the class members that are part of the instance. Classes can contain certain fields and methods that become part of the instance. That might sound a bit fake, so let's go back to our house example once more. The blueprint of the house could have several different properties, just some random examples: price, color of the front door, whether or not it has an extension, who the owner is, what the address is, etc. Every single house has a field for this property, and this property could have a value. It's also possible that the property doesn't have a custom value. In that case, it will have a default value. So let's have a look at our houses. They will have fields for these values. You can see that the first house, the second house, and the third house have different values. The last house doesn't have an owner yet. The value is null. Let's examine the properties on our account class in IntelliJ. As you can see, our account has an owner, a balance, and a minimum balance. We define these on line 4, 5, and 6. This means that every instance of account can have a different value for owner, a different value for balance, and a different minimum balance. Not only can classes have properties, they can also have methods. Again, let's start with our house example. Methods are things that can be done on the house. We have special methods that give access to the properties and allow us to get them and update them. These are called getters and setters. But we can also do different things on the house. For example, estimate the value of the house. This method belongs to the instance, meaning that the estimate value house is going to be different for every instance of the house. Clearly, we need an instance of the house to determine its value, and depending on the properties, the value might actually differ. So, properties are, well, properties. They define the house, and methods are actions, code snippets with a name that can be executed. In some other languages, these methods are called functions. I might call them functions every now and then as well, but Java calls them methods. Let's see an example of a method on our account class. So, right now we have two methods already. We have a method deposit and we have a method withdraw. The method deposit is defined on line 8 till 10. The details are not too important for now, but what is very important is that you can recognize method calls by the parentheses, and the method definitions have both parentheses and then curly brackets. Between the parentheses, we can define an input for the method. Again, we'll dive into these details later, but just to give you a clue for now so that you have an idea of what you're looking at. We can also create getters and setters. Usually, the properties are private, meaning that only the class itself can access them directly. Therefore, we would need getters and setters to access them from the outside. So let me generate the getters and setters and then let's have a quick look at them. So for example, let's have a look at the first one on line 16. This is a method to get the owner of the current instance. And line 20 is a way of setting the owner, updating the owner with a new value. As you can see, this method requires an input. And after that, you can see that exactly the same is happening for both balance and for minimum balance. But we could also create other custom methods. For example, we could go ahead and create a method called calculate creditworthiness. So I'm going to say public, and then let's just say that this is going to return a certain number. Calculate creditworthiness. I'm not sure how this one will work, so let's say that we omit the implementation for now, but we do need to return a number, so let's return 100. Clearly, this is not a real implementation, this is just a demonstration of what a method in a class looks like. As I've already mentioned, classes can also have constructors. We have used these already when we created a new account in a previous video. Constructors are used to create a class. So far, we have only used the default constructor. We did this when we used the new keyword. We are definitely going to examine constructors in more detail and learn how to create custom constructors, but that's not for now. You're not ready yet. We need to cover some other concepts first to be able to understand these details about constructors. So, what about the other group of members on the class? The ones that belong to the class and not to the instance. These are the so-called static members. They are the same for all the instances of the class, and we will see these later in more detail. But let's briefly touch upon them here already. Static members exist independently of the instances, so they already exist after defining the class before having created an instance with a new keyword. Let's explore what they are with our house example again. The house has an architect, and the architect has created a blueprint. Even when there is no instance of the house yet, the house will have an architect. Also, when there are multiple instances of the house available, they'll all have the same architect. For now, just know that static members actually live independently of the instances and belong to the class, just like with our architect example. And therefore, we cannot use the instance members in the static methods, because it's possible that there is no instance available since they exist without there being an instance. To be honest, I have not covered everything that could be a class member yet, but I have covered more than enough for your brain to process at this very moment. or should I say, very instance. We're going to explore the concept of packages next. Let's talk about the application structure. Let's visualize the concepts that we have seen so far. Java applications consist of different packages. Packages are a way of grouping classes. The class names inside a package are unique, but we can have multiple classes with the same name inside our application, as long as these exist in different packages. And packages can be imported in classes outside of the package. So, packages contain Java classes. Java classes are blueprints that define what properties and methods a certain object will have. From inside a package, we can access classes that are in the same package directly. If we want to access classes from other packages, we have to import them. Java classes contain members. Class members are the elements that a class can have. We roughly have two groups: elements that live on the class and elements that live on the instance. The elements on the instance are properties and the methods of a class that can be different for all instances of the class. The properties and methods that belong to the class are the same for all instances of the class and can even exist without an instance. And lastly, we can create instances of the classes. Instances are the actual objects that are made based on the class. Alright, that's it for zooming out. Make sure you do the exercises and the quiz. After that, you're ready to zoom in. Our first topic we'll dive into are variables, one of the most important concepts of writing code. So far, we've seen how to create classes and instantiate objects. It's time for a new topic that we actually have touched upon already: variables. Without variables, our code will do the exact same thing every time we would be running it, over and over again. Even though that could still be somewhat useful, for example when we're automating manual tasks, it's typically not what we want. Luckily, we can work with variables, so we don't need to get the same result when we run the same program twice. They make our program vary, so to say. This might not be the most helpful explanation, but let's look at variables in mathematics first. Now, if mathematics is not your thing, don't be scared. You can get quite far without probably 95% of high school math. But you will definitely have to be able to understand things like this. 2x equals time. What is the value of x here? Right, it's 5. Because we divide both sides by 2 to get the answer, and 10 divided by 2 is 5. So, what would be the outcome if we would have set the variable to 7? If x equals 7, then what does 2x equal? It would have been 14, because 2 times 7 equals 14. Let's look at another example. Say we have a variable containing a word, and this variable is called name, and we use it as a display message like this: hi plus name. When name contains Scott, the message will be hi Scott. When the name contains Fatih, the output message will be hi Fatih. So, what will be the output when we run this program? Hi plus name. We don't know exactly. It depends on the value of the variables. Alright, so now we know that variables are building blocks that make our code dynamic. Let's have a look at how this is done in Java. Java variables are very much like variables as explained in the previous video. We use it as some sort of container, passing it around. And what is in it, we'll find out during runtime. Well, partially. We can define and initialize a variable. We need 3 different parts. Type, for example, a number or a piece of text. A name, whatever you want to call the variable, this starts with lowercase. and the value, what the content of the value is, so what the variable represents. In case of a number, the value could be 5. This is what a number could look like. Int x equals 5. Int is the type, x is the name, and 5 is the value. And here's another example. String hobby equals coding. String is the type. This is the type for text values. Hobby is the name of the variable. And coding is the value of the variable. Java forces us to make the type of the variable known during compile time already. Forcing to know the type during compilation means that a lot of surprises, and in this case the surprises are errors, called exceptions, will not occur when running the program, but prior to running the program. So instead of having our program breaking down during runtime, it breaks down during compile time, prior to running the program. We have 2 types of variable types. Sorry if that sounds confusing, but hear me out. We have primitive types and reference types. The reference types are for objects and the primitive types are for storing values directly. There are a lot of built-in reference types that we will deal with. These are built-in classes, and we have an infinite total amount since you can create your own types using classes. There are 8 primitive types. Let's explore them in the next video. Primitives are the simplest types of variables in Java. A primitive is just a value. There are 8 types of primitives. We have byte, short, int, long, float, double, char, and boolean. The first 4 of them are used for storing integer numbers. They can each hold a number of a certain range. For example, byte can hold a number of -128 to +127. Short has an even bigger range, int has yet an even bigger range, and so does long, an even bigger range. You can see some examples of each of these primitives on the slide. For example, byte can hold the value 34, but so can short, int, and long. But byte cannot hold the value of 23,000, but short can, so can integer, and so can long, etc. The bigger the number, the less of the primitives it fits into. Let's have a look at how to create these primitives in IntelliJ. Alright, let's start by creating a byte. And we're going to call it b, and I'm going to store the value of 34 in there. This is how to do it. You specify the type, byte, you give it a name, in this case b, and I assign a value to it, in this case 34. Let's do it for the others as well. And here's a special case. If I'm going to create a long that doesn't fit in an integer, I have to tell Java I want to create a long by putting a uppercase L at the back. To be honest, a lowercase l would work as well, but if I use the lowercase l, it looks a little bit too much like a 1, especially if you have a different font. So it's always a best practice to do this with the uppercase L. This way, we tell Java that number on the screen, which is going to consider an integer by default, is not an integer, it's a long. And this is why it doesn't work without the L. Right now it says, nope, this does not fit into an integer. Integer number too large. But then we put the L at the back, and then Java is like, oh, it's a long, and then it's all fine, and we can store it in the long value. So just saying that the value is going to be of type long is not enough for Java to realize that the right-hand side of the equation is actually a long as well. You have to specify this manually by putting the L in the back. Float and double are meant for floating point numbers. Doubles have a bigger range and higher precision than floats have. Here's an example of each of these numbers on the slide. Float has the value 3.2, and this can be stored in both a double and a float. The value of the double on the slide cannot be stored in both a double and a float. It's too precise to be stored in a float. Let's see how this is done in IntelliJ. So here's how to create the float. And as you can see, we get red squigglies. And this is because, similar to line 8 where we created a long, we need to specify that it's a float. And we do this by putting the letter F after the number. This way Java knows we just created the float. And this is how to create a double. So if I'm going to be creating a floating point number, it's going to assume it's a double by default. So I can store 3.2 in a double like this, but I cannot store it in a float like this. And this is because the default assumption of Java when it sees a floating point is double. More details on this later. So I can store a number this precise in a double. Then we have char. Char is holding a Unicode character. It can also hold a numeric value ranging from 0 to somewhere in the 65,000s. But it will translate that to the corresponding Unicode character. It can, for example, hold an A. Here's how we can create a char in Java. So we give it the type char, and then we just store some character between single quotes in there, and that's one way to create a char. We can also put a number in there, and in that case it needs to be smaller than 65,535, but bigger than 0. I cannot store a negative number in a char. The last primitive we need to talk about is the Boolean. Boolean can only hold true and false. This is a great data type for storing yes/no values. If the answer would be yes, we would store true inside the Boolean value. And here's how to create a Boolean in IntelliJ. You give it a type Boolean, we give the name B1, and I did not call this one B because we already have a B on line 5 and we cannot have two variables with the same name in the same scope. And I gave it the value true. Please mind there's no quotes around true. If you try to do that, it will not work. Let's explore the sizes of these different primitives in the next video. All of these primitives have a size, and depending on their size, they can store certain values. On the slide, you can see a table of the different sizes. Let's zoom in on how this works. As you can see at the very bottom, the Boolean holds a 1-bit value. Every bit can hold a 0 or a 1. In case of a 1-bit, that means that there are two options, 0 or 1. Since a Boolean can hold a 1-bit value, it has two options only, 1 and 0, which makes sense because it only has the options true and false. Even though the Boolean data type represents 1 bit of information, its size isn't precisely defined. That's why the very bottom row is a bit vague. Here you can see 1 bit, and 1 bit is depicted as a little square. In this case, a bit can hold two values, 0 or 1. So if we have 1 bit, the total number of options is 2. Alright, so this is how it would sort of work for a Boolean. Let's keep that in mind. If we look at byte, byte is an 8-bit signed value. What does this mean? Well, 8-bit means that we have 8 options for 0 or 1. This would give us a total of 2 to the power of 8 options. As you can see on the slide, every cell holds 2 options, hence we go to 2 to the power of 8, since we have 8 cells, 8 bits. This equals 256. The highest number we can get to with a Boolean though is 127. This is because it's a signed number. We can also have negative numbers. All the negative numbers, 0 and the 127 positive options, makes 256 options in total. Alright, to wrap up on the primitives. We have had a look at the primitive values. We've seen primitives for whole numbers, integers, byte, short, int and long. And we've seen primitives for floating points, float and double. We've also seen primitives for characters, namely char, and for booleans, the true and false values, namely boolean. There are different types for variables as well, reference types. One of these built-in reference types that we use a lot is string. String is used for storing text, and we'll have a look at it soon. First, we're going to have a look at what we can do with these primitives. We're going to be talking about operators. Now that we've seen primitives, we can have a look at some of the operations that we can do. Operators are used to change input values to new output values. Operators are more a math concept than a Java-specific concept. The basic math operators are available in Java as well. Operators are used to perform operations and produce a result. This probably sounds very vague, so let's look at a concrete example. This is an operation. The operation is addition, and the operator is the plus sign. The operands are x and y, and z is the result. There are different categories of operators in Java. Arithmetic operators, amongst which the plus sign we just saw. Assignment operators. These are often used to change and assign a value at the same time, but just assigning a value is actually also an assignment operator. We have the unary operators. These operators work on one single operand only, and we have the relational operators to compare two values. In the next video, we're going to have a closer look at the arithmetic operators. Arithmetic operators can be performed on all floating points and integer numbers. Java has the following arithmetic operators: plus, minus, times, divided by, and the modulus. Let's explore them in IntelliJ. In order to work with the operators, we need a few operands. So I'm going to be creating some. Int x equals 2 and int y equals 3. And then let's perform some operations. I'm going to say int z equals x plus y. So what will be the value of z? Well, the value is going to be 5, and let me prove that to you. Using system out println, I can write messages to the console. Let's run this program. There you go. As you can see, the value is 5. I can also use operators directly in the println command. So in here, I could also say x minus y. Please mind, this does not change the value of x or y in any way. It's just going to produce a result that's not going to be stored. It's just going to be written to the console right away, and then it's going to be forgotten. In this case, the result is going to be minus 1. And let's run this example as well. I could also have set times. In this case, the value is going to be 6, because 2 times 3 equals 6. So, what if I were to do division? Let me show you. I'm going to divide x by y, and the result is going to be 0. That's odd, isn't it? What's happening here is that I'm dividing two integers, and the result is also going to be an integer, whereas the result of 2 over 3 is actually a floating point number. So let's fix this problem. I'm going to say double, let's call it d, equals x over y. And then let me show you the result here. Will this fix it? Well, no. But let me show you how to go for the first step. So now we have 0.0, which in some way feels even more wrong. I could have fixed this by changing both of these types to double as well. Well, when these are doubles, my int needs to be a double 2 here for the result. And now it will actually print the actual result of dividing 2 over 3, namely 2/3, but then in decimal numbers. There is one operator that's sometimes a bit striking for people, and that's the modulus operator. So let me show you an example of what that does. I'm going to say int number 1 equals 10 and int number 2 equals 5. If I want to know the result of number 1 modulus number 2, this is what the computer is going to do. It's going to see how often number 2 fits into number 1 as a complete number. And then if there's any value left, that's going to be the result of the modulus. So since 5 fits in 10 twice precisely and there's no leftovers, number 1 modulus number 2 is going to be 0. So let me run this code to prove that to you. And as you can see, the modulus is 0. If I were to change this to something else, say 4, well, 4 fits twice in 10, and then you have 2 left over, right? Because the difference between 8 and 10 is 2. So the result of 10 modulus 4 equals 2. All right, so these are the arithmetic operators. In the next video, we're going to have a look at the assignment operators. Java also has assignment operators. The most basic assignment operator is the equal sign. We have seen this already when we were assigning a value to our variables. There are combined assignment operators as well. The arithmetic operators that we just saw are combined with the assignment. This way, a variable gets updated and assigned at the same time. Here are the assignment operators: equals, plus equals, minus equals, times equals, divided by equals, and modulus equals. Let's have a quick look at how this works in IntelliJ. Please mind that these still have 2 operands. So actually, in the previous example, there are already plenty of examples of the assignment operator. Namely, simply saying int, and let's go for number 3 over here, equals 7, is usage of the assignment operator already. Why? Well, equal sign is an assignment operator. We are assigning the value 7 to number 3 in this example. Let's also create a number 4, which is going to be 70. And then let's update number 3 by saying that's going to be the result of whatever number 3 is with number 4 added to it. So this is an assignment operator. We are both increasing and assigning. So we say number 3 plus number 4 and assign this to number 3. So then afterwards, if you want to print number 3, you'll see that the value is going to be 77. A similar thing can be done with the others as well. For example, the minus equals. Running this will result into negative 63. So, as I mentioned, these still have 2 operands. In this case, on line 21, number 4 and number 3 are both operands. In the next video, we're going to have a look at the unary operator. We also have operators that only have 1 operand. These are the unary operators. Unary operators are used to increment, decrement, or negate the operand. Here are the ones that you need to know about. The minus sign in front of a value. This negates a number. Then we also have the exclamation mark in front of a variable name. This operator works on Boolean values. It's actually similar to the negate symbol, but then for Booleans. If it's true, it becomes false and vice versa. And then we also have x++ and ++x. These are used to increment the variable of x by 1. And similarly, we have x minus minus and minus minus x, and these are used to decrement the variable of x by 1. Let's have a quick look at how these work in IntelliJ. So I'm going to create an int number 5 over here, and I'm going to assign it the value of 8. Then if I say number 5 plus plus, it's going to increase the value of number 5 by 1. let me prove that to you. And as you can see, it's now printing 9, 8 plus 1. Similarly, if it would have done negative, if I would have done minus minus, it would have become 7. The other two unary operators work slightly different though. For example, if I have a number 6 over here, and I store the value of 3 in it, and then I'm going to say negative number 6, and then afterwards just print number 6, you're going to see that the first time it's a negated result, but it did not update the true value of number 6. It's just a temporary working result, as opposed to the post-increment and post-decrement operators. They actually change the value by just having minus minus and plus plus, whereas this one is just negating the value without storing it in the variable. The difference between the post-increment and pre-increment and post-decrement and pre-decrement is that the pre ones happen before other actions and the post ones happen after other actions. Let's look at an example in IntelliJ to see what this means. So I'm going to create an int pre equals 5, and I'm going to create int post also equals 5. Then I'm going to print plus plus pre, and I'm going to print post plus plus. So if I'm going to run this, you'll see that the pre is being incremented prior to being printed, whereas the post is going to be incremented after having been printed. So the pre is going to be 6, and the post is going to be 5. Let me show this to you. You can see that the last two values are now 6 and 5. Does this mean that post is not incremented? No. Afterwards, both of the values pre and post are actually 6. But post is only being incremented after its value has been passed over to the print line method for being written to the console. So if I'm going to write both of these again here, you can actually see that they're being updated. Both of their values are 6. So the pre one, first it's being updated, then it's being passed along the method to be printed to the console. The post one is first being passed to the console for being printed, and then afterwards it's getting increased. In the next video, we're going to have a look at the relational operators. The last category of operators are relational operators. These are different, in a way. They express the relation between two operators with a boolean. For example, whether two values are equal, or whether the one value is bigger than the other. Here are the relational operators. Equals, or exclamation mark equals, meaning doesn't equal. Bigger than, smaller than, bigger than or equal to, smaller than or equal to. Let's explore them briefly in IntelliJ. So let's say we have two numbers. We have a small number and we have a big number. We can express the relationship between them with a boolean by using the relational operators. So, for example, I can see whether they're the same. So this is going to be printing false. Let me move this to the bottom actually. And as you can see, the result is false, because small and big are not the same value. But if I'm checking for whether they are not the same value, I will actually get the result true, since they're not the same value. I can also check whether the one is bigger than or smaller than the other. So in this case, I'm going to see is small is bigger than or equal to big, which it's not. So it's going to be false. And similarly, I can also see if it's only bigger than. So if these were the same values, this would still be false, because small would not be bigger than its same value. But once we have the or equal to and they're the same value, the value will be true. So we've had a look at the different operators that we can use in Java. These operators work particularly well on integers and floating point numbers. Let's have a look at how to deal with storing text in Java with the use of strings. When we want to store text, we need to use the string type. The string is not a primitive. And this is actually very easy to tell. Here's how we can create a string and an int in Java. All the types that don't start with an uppercase letter are primitives. Int starts with a lowercase letter, so it's a primitive. String starts with an uppercase s, so it's not a primitive. It's a reference type. Strings are a bit of a special type though, but we won't dive into that here. At this point, it will probably confuse you still, but because strings are so common, they store text after all, there are some optimizations and convenience arrangements for it. Let's go back to the string example. So, string is the type, first name is the name of the variable, and Maaike is the value. You can also create multi-line strings with the text block. This will not work if you have any version of Java before 13, but here's how to do it. Use 3 quotation marks, and then you can just use line breaks in your string without it affecting the buildup of your string. If you try to do it with single quotes, it looks a lot uglier. There is an important thing to remember. When you want to compare strings, or any object in general for that matter, it works differently than when you want to compare primitives. Using the equals operator, as we've seen for primitives, does not work the way you might expect it. When you try to use the equals operator for reference types, you are actually comparing the actual reference of the object and not the value. So if it's a different object with the same value, say it's 2 different string objects with both the same value high in there, it will still conclude that it's not the same because it's not looking at the content, it's looking at the reference. So how do we compare objects? We use the equals method. Let's have a look at how to do that in IntelliJ. So let's start by creating a string. And let's create another string. The right way to compare 2 strings is with the equals method. This is how it's done. We say s.equals, and then we insert the other string as an argument. This is how to compare objects. What we are doing here is that we're calling a method. Strings actually have a whole lot of other methods as well. For example, we can use the toUpperCase method to convert the value to uppercase values. So if I'm going to run this, you'll see that it prints high in uppercase. But, and that's very important to note, it did not actually modify s. The value of s is going to be the same. So if you want to change s to uppercase, we would have to go ahead and say s equals s to uppercase. And after this one, the value of s will actually be changed to uppercase. So there's a whole bunch of other methods as well. So for example, one that you'll very often use is the substring method. So let's say that we want to change the string hello to only containing the letter E. Here's how to do that. So I'm going to say s1 substring, and then I specify the begin index. So in this case, I want to start at index 1 because the first index is 0, which 0 would be h, and then E would be 1. But if I don't specify anything, its value is going to be hello without the h. Let me show this to you. Hello. So we only want the E. In that case, we need to specify the AND as well. And please mind, the AND is excluding. So I'm saying 2, which would be the first L, 0, 1, 2, L. But it's excluding. So this is only going to show the E as the result. If I want to get 2 L's in there, I would have to go until 4, because the first L is index 2, the second L is index 3, and 4 is going to be excluded. So let's have a look at yet another method that belongs to the string class. We can also check whether a string starts with a certain letter. So for example, I want to check whether it starts with an H. Well, in this case, that's going to be true, because it does start with an H. So if I print the result of starts with, you'll actually see that it's true, because it starts with an H. And then another one that you find yourself using every now and then is the length method. And the length is going to return the number of characters in the string, and then it just starts counting from 1. So the value of S1 is hello, which is 5 letters, so the length is going to be 5. So there's a whole bunch of other methods. Let's do one more. We can actually check for the character at a certain position. So for example, if we want to get the character at index 3, in this case that's going to be the L, because the 0 is H, E is 1, first L is 2, second L is 3. I could just say char at and then go for the index 3. And as you can see, it prints an L because the character at position 3 is L. There's a lot more string methods though, but I'm not going to cover them all here. We'll see them as we go. In this video, we've learned to create strings to store text. We've seen that this is different from the primitives and that you cannot compare it with the double equal sign. Instead, you'll need to use the equal methods. There are more methods built in that we can use in strings. We've seen just a few, and gradually we'll discover more of them. Next, we're going to be talking about casting. Casting is a process that converts the data type of a value into another data type. There are pretty much 2 different kinds of casting: widening type casting and narrowing type casting. Let's leave programming out of the picture for a second here and move our thoughts to my kitchen cabinets. And let's say I have a jar of pasta. If I have a bigger jar and I want to pour the pasta in the bigger jar, I'm sure this will fit. But if I have a jar with pasta in it and I want to pour this pasta into a smaller jar, I need to estimate whether this will fit or not. If my bigger jar is not completely full, it might fit. But if it's completely full, or at least fuller than what will fit in the small jar, it will not fit. This is a more careful process. Alright, back to Java. The first one, pouring the pasta in the bigger jar, is widening type casting. This does not need to happen explicitly. Java can do this automatically for you. There is no risk of the value not fitting in the new type. An example of this is casting an int value to a long. The value of a long can be bigger than an int, so it will always fit. Narrowing type casting is pouring the pasta of the bigger jar in the smaller jar. This will not always fit, and therefore it needs explicit type casting. This happens, for example, when you want to store the value of a long into an int. This will often fit, but not always. Therefore, this needs to happen explicitly when the programmer is sure that it will fit. On this slide, you see the explicit cast happening. It's the int between 2 parentheses. This tells Java to update the type to whatever is between the parentheses. Fun fact, both types of casting are happening in this example. The first time is when we assign 123 to long. 123 is an int, but we store it in a long. This widening casting happens automatically. The second one is an explicit cast. The int between parentheses changes the type of the long to an int. And in this case, we're sure that it will fit. In the next video, we're going to have a look at some more examples in IntelliJ. Let's recreate our example. Let's say we have some sort of long L and we store a value in here. And then let's say we have an int x and we want to store the value of the long in there. As you can see, we get a compile error. Why? Well, long is potentially too big to be stored into an integer. In this case, I'm sure it will fit, so I'm going to cast it to an int. And as you can see, the red squigglies goes away and it looks good like this. We could do something similar with double and a float. So remember, the double is bigger and more precise. So let's just store some sort of value in a double. And actually, this will also fit in a float. So I want to do this, but I cannot say this because a double might not fit into a float. What I can do, I can cast it to a float. And then IntelliJ is happy again. So what happens if I try to do this, but actually it doesn't fit? Remember that char was an unsigned variable. It cannot be negative. So let's just create some sort of, I don't know, a byte b. And let's store -23 in there. And then I have a char c, and I want to store the value of my byte b. Well, in that case, I need to cast it to a char. Then if I cast it to a char, it will compile just fine. But will this run just fine? Well, let's run it and then find out. So let's talk about the funny thing that's happening here. Why does this work? Well, this has a bit to do with the way Java is working. Java mandates that any of the arithmetic operations on the primitive types is not going to either overflow or underflow. So what's happening here is it's actually being changed into a rather big number. So stay with me when I'm going to do the next conversion here. So well, if I were to print this is not going to be very helpful, but let me show you what this does. As you can see, it shows an arrow pointing to the left. But actually, I'm going to be helped more with the numeric value. That's going to explain it a bit more to us as well. So instead of doing what we're having right here, I'm going to say int I, and I'm going to assign the value of c to it. And then I'm going to print the value of I. You can see the numeric representation of a char. And you can see that, in fact, it's a really big number. So we try to assign -23 to it. And then what happened is that it turned into a really big number. This is because it doesn't allow us to have an overflow. So instead, it goes to the maximum value and starts from there. So just to make sure that this is still clear, so the maximum value of a char would be 65,535. So in here, if we were to add 1 to it, we would now get 0 instead. And this is because the char will not overflow. Instead, it will just go to the other end and continue from there. So this is going to be a problem though, and this is very funny because it's related to casting. So it says require type char provided an int. Well, this operation, it's an int. So instead I'm going to cast it to a char, but I need to put this between parentheses in order to cast the outcome of this to a char. After that, I'm going to print the value of the new char. And as you can see, this is not very helpful again. So instead, let's go ahead and cast it to an int. And now you can see it's 0. So if we're for a primitive at its very maximum, and we try to do an addition that exceeds its maximum, it's going to go to the smallest value and proceed from there. Likewise, if we're at its very minimum, and we try to deduct even more from there, it's going to go to the very end and continue from there. As you can imagine, when they created bank accounts in Java, they did not work with primitives to hold the balance of your account. Let's say unfortunately. We have seen how we can change the type of a value using casting, and that we need to be very, very careful with doing this in order to avoid unexpected surprises. In the next video, we're dealing with another exciting topic: how to store multiple values in one variable with the use of arrays. Arrays are used to store multiple values in one variable. Arrays are storing values of a certain type. So let's say we'd like to store the numbers 1 to 5. Here's how we would do that. We would say int, the type, then square brackets to indicate that it's an array, give it a name, in this case numbers, equal sign, and here we are assigning the values between two curly brackets. They are comma separated. Similarly, we could actually define an array of fruits. In this case, the type would be string, text, square brackets indicate that it's an array, fruits would be the name, curly brackets to specify the values, and they're comma separated. As you can see, we declare the array by adding square brackets after the type. This tells Java that it's not one single value, but actually an array of that type. If we want to get the value out, we can use the index for this. The index starts to count from 0, so the index of the first element is 0. The index of the second element is 1, etc. On the slide, we are getting the first value out, and we store it in a type of string. Since the one value is of type string, the name is first fruit, and we say equals fruits, which is the name of the array, and then square brackets, and in between there we specify the index. In this case, the value is going to be orange. So the index of orange is 0, it's the first element. The index of apple, the second element, has index 1, and the third element, grapefruit, has index 2. So to get the last fruit, we need to use the index 2. Here's how to do that. String last fruit equals fruits, and then between square brackets a 2. It sure looks tasty, this nice grapefruit. We can also get the length of this array by using the length property. For length, we count like normal humans do, so the length of the fruits array would be 3. In Java, the length must be known upon creation. This can be done by specifying the entire array, like we just did. But it can also be done by a syntax that we haven't seen yet. And that's by saying int square brackets, give the name, and then equals new, int, square brackets, and then the length of the array. This creates an array called int array with a length of 5. And you might think that there are no values in this array yet, but they are actually initialized to their default values, which is zeros for ints. We can override this value as well. So we could say int between square brackets 0 equals 2. This is how we override the first element with index 0. You can see afterwards the value is going to be 2. In the next video, we're going to move over to IntelliJ and see arrays in action. Let's start by recreating our example. I'm going to say int square bracket numbers equals, and then I'm just going to give it some values. If I want to get the first value out for printing it, for example, I'd have to use index 0. If I want to override a certain value, I could do it like this. For example, override the last value with 10, like this. Let me show you that it has changed. There we go. So let's run this so you can actually see what is happening. You can see the first time it's printing a 1 because it's the first value of the array, and the last one has been updated to 10. You might wonder what happens if we try to print the entire array. Let me show this. And this doesn't look very helpful, does it? This is normal. If you see this happening, this doesn't mean that you're doing anything wrong. This is because an array is a reference type. And just like the equals method is a bit funky for reference types, same thing goes for when you try to print them. Sometimes it works, sometimes it doesn't. And in the case of arrays, it doesn't work like this. So for now, until we've seen more complex coding constructs, when we want to print the values of the array, we have to specify the index of the element that we would like to print. There is one more thing that I like to show you here, and that's we can get the length out. So please mind, this length is a property, so there's no parentheses coming afterwards. So if we want to get the length of the array, we count like humans, and in this case the length of the array is 5. We've had a look at arrays. We can use arrays to store multiple values in one variable. This actually concludes our basic coverage of variables. In the next section, we're going to have a look at the difference between primitive values and objects. A very important understanding for programming Java is understanding the difference between primitives and objects. Primitives are the most basic data type. They just contain a value, and there are 8 different kinds of primitives. An example of primitive is an integer with a value of 5. A primitive is not composed of other data types and does not contain methods. Objects, on the other hand, are composed of other data types and do contain methods. Or at least, they could. An object is an instance of a class. And a class is a blueprint that's pretty much a collection of properties and methods. You can see an example of an object here. This is the object person. It's a blueprint. Person has a name and person can greet. Greet is the method, name is the property of person. So, objects are more complicated than primitives. As you can imagine, they take up more space, and that's why they're stored completely differently in the Java memory. And this has certain consequences. For example, primitives are immutable. This doesn't mean that you can't change them though, but it does mean that a new one gets created when you override its value. It doesn't change it on that piece of memory, but it creates a new value on a new piece of the Java memory. This is not the case for objects, but objects can be immutable. In order to achieve that, you need to stick to very certain coding patterns. Let me show you in IntelliJ what I mean when I say immutability. So here is our person. And if I'm going to create a new class with a main method in it, and I'm going to call this class just app for now. And in here, I'm going to create a main method. And in my main method, I'm going to create a person object. And I'm going to create another value holding this very same object. So I'm going to say p equals person. And now when I say person.name equals, and I'm going to say Maaike, the actual object has changed. And I can prove this by showing you the value of p.name. Because as you can see on line 6, I assigned to p the value of the person that I created on line 5. If person were immutable, which is not, then p would still not be having a name, so would be null. But in this case, I've updated the actual object. They're both looking at the very same object, and I'm going to tell you a bit more about this in a second, so don't worry too much about it for now. But this is what I mean with mutability. The actual original object has changed. And as you can see, it prints Maaike. So it modified the original object. So to sum up, primitives are just basic values, whereas objects are a collection of properties and methods. This will be nuanced a bit later, but it's good enough for understanding it right now. Let's have a closer look at what objects can contain. Objects can contain primitives. Primitives can just contain a value and are one of 8 data types. Objects can be of an infinite amount of data types, since you can specify new classes that are the type you made up. And these classes can specify properties. The properties can be of primitive types. So for example, when we have the class car, this car can have a property number of wheels, which is going to be of type int. And int is a primitive, meaning that our car has a primitive as a property. Of course, our car could have all other sorts of primitives as properties, but for now, this example should suffice. So, to sum up, primitives cannot contain objects, but objects can contain primitives. Objects can also contain objects. Let's explore that in the next video. Objects can contain other objects as well. An important concept for this is object composition. Object composition is when an object contains another object, and this can go quite some levels deep. For example, we can have an order object, perhaps in a web shop application. And this order can have a customer, which is also an object. And the customer can have an address, which is also an object. Being able to make these steps and draw these lines is key for object-oriented thinking, which we'll see later. So for example, if we want to get the city the order was delivered to, I'd have to take these steps: order, customer, address, and from the address get the city. Let's put aside coding for a second and practice drawing these lines. This is a cat, and it's of type cat. So there's an object which is of type cat. So cat is a class. And the cat has an owner of type person. So person is a class as well. The owner has a car of type car. So car is a class as well. And the car has an engine of type engine. So engine is a class as well. If we want to go from the cat to the HP on the car, we'd have to take the following steps. We go from cat to owner, from owner to car, from car to engine, and from the engine we get HP. And the HP can be of a primitive type actually. For example, 400. Though that's probably a bit much. As you can probably tell, I don't know a lot about cars. Makes sense though, cars are hardware, aren't they? Being able to travel over objects to get a certain value is a very important part of working with an object-oriented language like Java. So practicing this is a good idea. Doing it like this in practice is probably not a good idea. As we have seen, in terms of data, objects can have objects and objects can have primitives. Let's discuss the concepts of storing objects and primitives in the computer memory in the next video. Let's talk about the stack and the heap, two important concepts for storing variables in the Java memory. The Java memory consists of different parts. Two of these parts are the stack and the heap memory. Understanding how this works will help a lot by truly understanding the difference between primitives and objects. Let's start with the stack. The stack holds the variables that are needed for running the program. Let's have a look at this example. We have a main method with an integer x, which is a primitive, and a value 5, and a boolean b, also a primitive, with a value true. These values are stored on the stack like this. First, we have the x, which is equal to 5, and it's of type int. And next, we have the boolean, which is of type boolean, called b, and it holds the value true. If another method gets called from within the main method, another record gets created in the stack. As you can see on the right of the screen, there's a new block, a record, for the method add that's being called from within the method main. And what happens in this case is that we have the add method, so we go ahead and we create a new record, add. We send in 1 and 2, and we call them a and b, so it holds 2 values to start off with. A and B, both of type int, holding the values 1 and 2 respectively. And then in this method, something else is happening. C is being created, also of type int, and it holds the value of 3. Then it's going to return C, and after returning, the add method is done. And this is why the record on the stack disappears again, bringing us back to our main method. After that, the main method is done as well, and the stack is empty. The Java application can only access the memory of the current record the stack is on. That's why it's called a stack. As you can see, when it's in the method add, returning the C on that line, it can only access the variables that are on the stack in the add record. The main is not accessible at that point. This is just like a stack of plates. It can only access the top one. Admittedly, you could grab a plate from the middle, in the case of the actual plates. But let's agree, that's dangerous and wild behavior. So, what about the heap? Well, let's say that our method creates an object, for example, a string. Objects are bigger than primitives, and the stack is not designed to hold all these big objects. That's where the heap comes into play. The object gets created on the heap. And on the stack, we hold a pointer to the memory location on the heap. String is actually stored in a special way that we'll learn more about later. Instead, let's have a look at a person object that has a car object that has an engine object. Perhaps this is the data model of a car insurance company. If we create another object, we create another object on the heap and have the reference to this object live on the stack. If we create a car object in the main method and set it to be the car of the person, we add only one car on the heap. Both the stack and the person object point to the memory location of the car. Next, we create an engine and assign the engine to car. This is what the heap looks like then. There's only one engine that's being created, and both the stack and the car point to the very same object on the heap. If an object on the heap has primitive values, these are stored on the object on the heap. For example, an engine could have an HP. Likewise, as we have seen, if an object on the heap has other objects, the objects on the heap hold the reference to the other object on the heap. This is a very brief version of how the stack and the heap works. It's a lot more complicated in real life, but it's enough for now. Let's see what happens with primitives and objects when we pass them around. When we call a function with input values, we are passing either a primitive or object to the function. When we pass values around in Java, for example as an argument of a method, a copy of the value gets created. This is why Java is pass by value. It means that copies get created when the values get passed around. For both primitives and objects, Java is pass by value. When we send in a primitive, we are not sending in the actual primitive, but a copy. When we send in an object, we are sending a copy of the reference. This has different implications for objects and primitives though. The original primitives can't be altered from within the methods, because primitives can't be altered, but the object can be. Let's look at an example in IntelliJ. We have a main method, and in this main method we call another method on line 8. And we're passing in two values, one primitive integer and one object person. If Java would not be passed by value, it would actually also alter the value of the int I on line 5. But let me prove to you that that doesn't happen. So I'm going to say, let's print I, let's do a space, and then just print the name of P. So remember, copies are being sent in. And these copies would mean that I is not changing. There's also a copy of the reference sent, but there is something funky happening over there. As you can see, the value of I is still 3. A copy was sent, sure. But also a copy of the reference was sent. But as I already mentioned, this is the same yet different for objects. Objects are also passed by value, but that means that a copy gets made of the reference before passing it to the method, but not a copy of the object itself, a copy of the reference. So both the original reference, the one on line 6, and the one that's being used as the input parameter, so it's sent in on line 8, and the input parameter list is on line 12, both of these are pointing to the same object on the heap. So if in that method we use the copied reference to alter the object, we alter the actual object, copy of the reference or not. If I ask the original reference, what is the value of the property of the number, it will be the same as I set it on line 5, a copy was sent in. But if I ask what is the value of this property, it's the same object that was being altered, so the name is being changed for the main method as well. So yes, objects are also passed by value, but the side effects are different. To be sure that you understand it, I've illustrated the steps. So as you can see, on this stack, we have a method main. And this method main holds an example object. On the example object, there's a primitive number and it holds the value 2. Then we're going to call another method from the main, and this method is going to add 1 to the number on the example object. So both the main and the add 1 hold a value that is pointing to the same reference on the heap. So then, when number gets updated to 3, as you can see, both the add 1 and the main have the example pointing to the very same object with the altered number. So after the add 1 is done executing, in the main method, when we go ahead and ask, hey, what's the value of number? It's going to be 3, because we're looking at the very same reference. I know from experience that this is a very difficult topic for beginners, so I'd also like to add a non-code example to explain this copied reference story. Let's picture a locker. If you and your friend have a key to the very same locker, you both have different keys that open the same locker. If one of you alters the locker or the content of the locker, the other one will also see the changes when they access the locker. Alright, so we have seen that Java is passed by value, meaning that it makes copies of the values it sends as arguments. But since primitives are just the values, the copied value doesn't affect the original primitive. This is different for objects. A copy of the reference gets made, so this will affect the actual object that the original reference is looking at. This is where the real fun starts. We're going to be discussing control flow statements. Control flow is which lines of code get executed and in what order. The first one we're going to discuss is the if statement. An if statement is a control flow statement that allows a program to execute a certain block of code only if a certain condition is met. For example, you might want to check if a number is greater than 0 before performing a mathematical operation on it. Because if you're going to divide a number by 0, things will go wrong. Here is the basic syntax of an if statement in Java. The condition must be a Boolean expression. That is, it must evaluate to either true or false. You could also simply insert true or false, but then it's no surprise what's going to be executed anymore. If the condition is true, the code inside the if statements block will be executed. If the condition is false, the code inside the block will be skipped. You can also use an else statement to specify a block of code to be executed if the condition is false. Here's the syntax on the slide. First, the code will evaluate the if condition. If that's true, it's going to do whatever block is specified for if. If the condition is false, it's going to do the else block. Additionally, you can use an else-if statement to check for multiple conditions and execute different blocks of code depending on which condition is met. You can see the syntax here. As soon as it runs into one condition that's true, it's not going to evaluate any others, so the order of the conditions matters. If the first condition is going to be true, it's going to execute the code in the first block, and it's not going to look at the other condition or the else block. If the condition is false, it's going to evaluate the second condition. If that condition is true, it's going to execute the code in the block associated with the else-if condition. After that, it's not going to look at the else, but it's going to continue with the rest of the code. If, in this example, the else-if is false, it's going to skip the else-if block and execute the code associated with the else block. The else block is only going to be executed when all conditions are false. If statements are a very powerful tool that can be used in many different ways to control the flow of a program's execution. In the next video, we're going to have a look at some practical examples of if statements in IntelliJ. Alright, let's have a look at an if statement in IntelliJ. I'm going to create a variable int called input, and I'm just going to set it to 2 for the time being. And as you can guess, I'm going to use this variable for an if statement. So I'm going to say if and then specify a condition. And in this case, I'm going to say if input is bigger than 0, go ahead and print some result, which could, for example, be 2 divided by the input equals, and then go ahead and perform the calculation. Now, if I'm going to run it, you're going to see a result. See what I did there? And as you can see, when we divide 2 by 2, we get 1. That makes sense. Alright, so now I'm going to set it to 0. And I'm going to see what happens now. Go to run it again. And as you can see, there is no output statement whatsoever. And that is, line 8 with the print statement is only going to be executed when input is bigger than 0. So what if I wanted to check for just not 0? Well, easy. I'll just go ahead and do it like this. Exclamation mark equal sign, meaning not equal to. Again, nothing will happen right now. But let me specify an else statement. And I'm just going to say input cannot be 0. And if I run it right now, you will see that the else condition is being executed. And there we have it. Input cannot be 0. So what if I make it bigger? Well, then the first one is going to be executed again, because now 1 does not equal 0, so it's going to do the division again. Alright, let's do another one. We are going to print a greeting based on the time of the day. And I'm going to do this a bit in an easy way. I'm just going to use an int hour, and I'm going to use the military notation. So it's from 0 up to 23. And I'm going to set it to 6 at first. And then I'm just going to say if hour is smaller than 12, and then I'm going to print good morning. In this case, I actually want to have an else if as well, because I want to say good afternoon. When do I want to say good afternoon? Well, whenever the hour is between 12 and 18. So I'm going to check for that. When hour is bigger than or equal to 12 and smaller than 18, then I'm going to be printing good afternoon. Well, if it's not smaller than 12, and it's also not between 12 and 18, I'm going to be printing good evening. So that would be the else statement. So let's see what happens when I print this. And as you can see, it says good morning right now. If I'm going to update hour to 13, it's going to say good afternoon. And when I make it 23, which is the actual hour right now, I am going to get good evening. All right, when we look back at this if statement, we see something striking. Namely, if I'm going to put in some invalid input like 43, it's still going to print good evening. So I decided that I want to refactor this just a little bit and make it more specific. So in here, I'm also going to add a check. And as you can see, I can have multiple else ifs. So I can now say if hour is bigger than or equal to 18 and smaller than 24, I'm going to say good evening. And in all other cases, I am going to say, I don't know that hour. There we go. So if I run this right now, we'll end up in our else statements. There's still one problem. And that's the negative hour. So if I'm going to run this, you'll see that it says good morning for negative 43. That can't be my intention. So I'm going to change this yet a little bit more. I'm going to say here if hour is bigger than or equal to 0 and smaller than 12, I'm going to say good morning. Though arguably you wouldn't say good morning just past 12 at midnight, but that's besides the point here. You could make a special clause for good night. As you can see right now, when we do negative 43, we'll actually also get the I don't know that hour, but good day message printed, which is what we were going for. All right, we have seen some practical examples of how to use if statements in real-life situations. As you can see, they're very helpful for making all sorts of decisions and controlling the flow of the program's execution. Let's talk about another control flow statement, the switch statement. We're going to do this in the next video. Let's switch to a new topic, switch statements. A switch statement is a control flow statement that allows a program to execute a different block of code depending on the value of a given expression. Okay, that sounds a bit complicated. But it's pretty much an alternative to using multiple if-else statements and can make your code look more concise and a lot easier and nicer to read, and therefore more maintainable. Well, let's have a look at this very promising syntax. The switch statement works by evaluating an expression. And this expression is going to be matched against the case labels. You can see the case labels here. The case labels are a certain value. And when the expression matches one of the case labels, the code inside the case block is going to be executed if the expression equals that value. So let's say in this example, our expression equals value 2. That means the code after value 2 is going to be executed. But the code following the matching case label is executed until a break statement is encountered or the end of the switch block is reached. If no match is found, the code following the code label is executed. The default label does not have to be present, it's optional. It specifies the code to be executed if the expression right after the switch does not equal any of the specified values. The expression can be of a few specific types: byte, short, char, int, enums, string, and wrapper classes of the allowed primitives. So, uppercase, character, byte, short, and integer. I want to point out that there's a break statement at the end of every case block. If we would not have this, the code would fall through to the next case label. And that's a bit weird to imagine, but just picture it like this. As soon as we find a match, it's just going to continue till either the end of the switch statement or until it encounters a break. Often we only want to execute the code for that specific case, so it's very common to have a break at the very end of every case. This actually allows us to specify one action for multiple cases by pretty much stacking them on top of each other with no break statement. Here you can see the difference between our first situation where we were checking for 3 different inputs, written using an if statement and written with a switch statement. So the popular opinion is that the switch statement is easier to read and better to maintain than the if statement. Both will do the same thing though. Just like the if statement, switch statements are a very useful tool for deciding how to execute the program and controlling the flow. In the next video, we'll see some practical examples of the switch statement in IntelliJ. Alright, let's start with coding some switch statements in IntelliJ. Let's say we have some sort of string that holds the extension of some sort of file. And I'm going to start with PDF here. I'm going to create a switch statement that's going to check for certain extensions. So it's going to switch over the extension. So please mind that this one cannot be a boolean, but it can be a string or byte, char, int, etc. So we are switching over this extension by creating some case labels. And I'm going to start with docx and just print whatever it is, which is a bit less real world-like, but we'll do the trick for now and help you understand how these switch statements work. By the way, in order to get back to this case level, I need to do a shift tab because IntelliJ is not helping me with that. Let me tell you what I mean. So I do this and I go to the next line and I just do whatever and I say this is a presentation. But now I want to outdent pretty much. And if I do a backspace, I go back to the previous line. So what I do shift tab, which brings me back here and I can write case. But let me go for PDF here. What also works, if you just go to the next line, type case. I can't stand looking at this, so I do shift tab. But now it switched back automatically. And then I can say here, this is a text file. And then default will say we don't support this file. Again, I do shift tab, but you can also just wait for it to pop back. All right, so let's see what happens if I run this code. And as you can see, it now prints all the text pretty much. Why is that? Well, this is because I did not include the break statements. Remember when I said if you don't include a break statement, it will fall through. So here's what happened. It matched with the PDF because that's the value of my string extension. And then it printed, this is a PDF file, which I actually accidentally did with printf instead of println, which is why in the output they are on the same line. But as you can see, it also prints this is a text file because it fell through to the next case, which is not what I wanted because it's even printing. We do not support this file. So what I need to do, I need to go ahead and add all these break statements in order to avoid it from falling through. And now I have a break statement after every case, and if I run it again, you will see that now it will only print this is a PDF file. Alright, so that's how to create a switch statement. I actually want to show you one more, And in this case, I'm going to use an int that's going to hold a month, and it's going to hold 1 for January, 2 for February, etc. So I'm just going to do 3, so it's going to represent March. And then in here, I'm going to say month, and I'm actually not going to print it for every month, but instead I want it to show the number of days in a month. And this is where I can actually stack the case labels, what I was talking about. So for example, January has the same number of days as March, and the same number of days as May, same number of days as July, and August, and October, and December. So what I'll print here is this month has 31 days. And then I'm going to do the same for the 30 days. So it would be case 4, case 6, case 9, case 11. And then I'm going to print this month has 30 days. And then there's one that's left out at this point, and that's for February, who's a bit weird because it has either 28 or 29 days. Okay, so if I'm going to run it, it is again going to fall through, but not in the way you would hope, because I did not add my breaks. So we want to add breaks after block. We want to have a certain fall through happening, but we don't want it to fall through after having stumbled upon the print statement, because after that we're done. So when it's case 1, we want it to fall through all the way to case 12, but then it needs to break. And as you can see, in this case, pun intended, I did not add the default option. It's not obligated. I don't want to have a default option. So this is it. Let's run it. And as you can see, it now prints this month has 31 days, because March does. So at this point, using it for this situation, does it look like pretty code to me? No, it does not. And I would probably prefer to use an if statement for this. Having said that, that is my personal opinion. Well, it's also a bit my professional opinion, clearly. But opinions differ. In this case, I would totally have gone for the if statement. Some people like this syntax better. None of this is right, probably. I would definitely say I like the switch statement better than the if, else if statement. So before we end our discussion on switch statements, I actually want to admit something, and that there is nowadays a lot more possible with the switch statement. But this is a very complicated syntax and we don't need it right now, so we'll see it later. I just want to warn you that you might come across it on the internet, and then that's the syntax I'm talking about. We'll see it later when we discuss more advanced code. Next up, we're going to have a look at how to repeat code using the while loop. Let's talk about loops. The first loop we'll be discussing is the while loop. It allows us to repeat a code block. The while loop is a control flow statement that allows a program to repeatedly execute a certain block of code as long as a given condition is met. This is useful for situations where you want to perform an action multiple times, and of course you want to avoid repeating code. This could include tasks such as reading a series of numbers from a file or generating random numbers until a certain value is reached, or even searching for a specific value. Here's the basic syntax of a while loop in Java. The condition must be a Boolean expression, just like for the if statement. So it must evaluate to either true or false. And if this condition is true, the code inside the while loop block will be executed. Then, after the execution, the condition will be evaluated again. And the process will repeat. The code will be executed, and the condition will be evaluated again, until the condition becomes false. At that point, the loop will terminate, and the program will continue executing the code that follows the while loop. Here's an example of a while loop that generates random numbers until a value of 10 is reached. In this example, the while loop will continue to generate random numbers and print them until a value of 10 is generated. Then the if statement will evaluate it true, and not found will become false. This causes the loop to terminate and the program to continue executing the code that follows the loop. Just like if statements and switch statements, while loops are a very useful tool, but this time they're a tool for repeating actions in a program. But it's important to use them carefully, as the slide might make you guess already. If the condition in a while loop never becomes false, the loop will continue to execute indefinitely, potentially causing the program to crash or the computer to run out of resources. Therefore, it's important to include a mechanism for terminating the loop, such as the if statement or perhaps a break statement, to assure that the loop will not run forever. In the next video, we're going to have a look at some more examples using the while loop. Alright, let's start by exploring our sample from the slides. This sample is supposed to be looking for the number 10. Let's see what happens when we run it. And as you can see, it's looking for the 10 for quite a while already. In fact, this is very, very long, and I'm starting to get suspicious, so I'm going to kill this code and inspect what's going on. So looking at this code, we think we have a way of ending our while loop, right? On line 9, 10, 11, there's an if statement specified, and as soon as the random number generated equals 10, we set not found to false, and we enter a loop. That's true, we would in case we would ever achieve the number of 10, but we don't. Why is that? Well, let's have a look at this random function. So random returns a double value with a positive sign greater than or equal to 0 and less than 1. Wait, less than 1. Meaning it would never become 10 this way, because it will be multiplied by 10, and then the int is just going to chop everything after the comma off to get the integer value, so it will never be 10. So there's multiple ways to fix this. If we're really looking for 10, we would have to generate the value differently, for example multiplying this by 11. This way it will reach 10, won't reach 11, and we would be good to go. So if I run this again, you should now see that the loop actually ends at some point. In this case very fast, the second option was already 10, and sometimes it takes a bit longer. So here I really want to illustrate the necessity of diving into the fact, is my loop actually ending at some point? Am I not going to be stuck in some infinite loop? Because this happens more often than you think. And it's especially dangerous if you're relying on external input for the condition of your check to get out of the loop. So be very much aware and test this in all ways possible to avoid getting stuck in an infinite loop. Alright, so that's the not found example. I'm going to comment it out for just now, and I'm going to add another example in. And this is going to be a bit simpler of an example. So what I want to do, I just want to have some sort of, well, let's say an int I, and I'm going to set it to 0. And then let's just say I want to go ahead and for all numbers between 0 and 100, print the value of I squared. So what do? I'm going to say while I is smaller than 100, go ahead and print the value of my number squared. So I'm going to say I and then 2, because this is going to use the math class to go and raise it to the power of 2. And then after that, and this is very important, I must increase I. If I don't increase I, I'll be stuck in an infinite loop again. So I'm going to run this. And as you can see, the latest value is going to be 99 times 99 equal 9801. So this is how easy it is to work with a while loop. And as you can see, it's incredibly fast. There's a lot more things you can do with a while loop. In some cases, when you feel the need to copy-paste a snippet of code, especially when you want to copy-paste it underneath each other, this is quite a good indication that you should be using a loop instead. So we've seen the while loop, and we know that we can specify a condition, and that's going to execute a piece of code until that condition becomes false. But there's actually more types of loops. One of them is the do while loop, and we're going to have a look at it in the next video. Our next topic is the do while loop. It's a lot like the while loop, but there's one major difference. In Java, it's also a control flow statement that allows the program to execute a block of code repeatedly. Again, until a certain condition is met. So it's very similar to the while loop, but it guarantees that the code inside the loop's block will be executed at least once, even if the loop condition is initially false. So here's an example of the do while loop. In this example, the do while loop will execute the code inside this block at least once before checking the loop condition. So it's going to start with count ++ and then printing the value of count. If the condition is true, which it is, the loop will continue to execute and the code inside the block will be executed again. If the condition is false, the loop will terminate and the program will continue executing the code that follows the loop. In this example, the loop will execute 10 times, with a value of 1 for count on the first iteration, a value of 2 on the second iteration, and so on, up to a value of 10 on the final iteration. At that point, 10 is not smaller than 10, and the loop will finish. So the do while loop is very useful when the code inside the block needs to be executed at least once, regardless of the initial value of the loop condition. It's also useful when the loop condition depends on the result of the code inside the loop's block, as the condition will be checked only after the code has been executed at least once. For example, when you would like to create a connection to a database or something else. In the next video, we're going to have a look at some practical examples with the do while loop. Alright, let's make this a bit more real-world-like. So we're going to use input. And to use the input, we're going to use the scanner from the Java util package, which you can see has been imported on line 3. And I'm going to make this a new scanner and it's going to read from our system in. So what do I want you to do? Well, I'm first going to initialize some sort of variable to store the user's input in. And then I'm going to need some code to execute the input at least once. So I'm going to say do. And then in here, I'm going to just print a message to give the user some instructions like enter your name. And after that, I'm going to ask for some input. I'm going to say scanner, next line. And it's going to store the string that the user entered in my input. After that, I'm going to check whether the length is smaller than 2. Because if that's the case, I don't consider it a valid name. So if the length is smaller than, well, actually 2 might be a name already. So let's say if it's smaller than 2, just one character, that's not enough for a name. So if that's the case, we want to go ahead and repeat our block of code. So let's see what happens if I run this. As you can see, it prompts for a name. So I'm first going to say just one letter. It's going to ask for it again. And if I enter nothing, it's going to ask for it again. But if I enter my name, that's longer than 2, it's going to stop executing the program. So this is an example of where the do while loop comes in handy. We need to get some sort of input, and we need to do this at least once. And it's possible that the first time it's not according to our standard, so that we need to do it again. Alright, so that's it for the do while loop. In the next video, we're going to have a look at the new loop, the for loop. Did you think we've seen all the loops? Well, think again. We have 2 more types of loops to discuss, The first one is the for loop. The for loop in Java is a control flow statement that allows a program to execute a block of code multiple times with a different value for a loop variable each time. And this is what the syntax looks like. And this can be a bit intimidating, so let's go over it bit by bit. So it starts with the word for, sure, but then. The initialization section is executed once at the beginning of the for loop. This is typically used to declare and initialize a loop variable, or even variables, which will be used to control the loop's execution. The condition is a Boolean expression that's evaluated before each iteration of the loop. If the condition is true, the code inside the for loop will be executed. If the condition is false, the loop will terminate and the program will continue executing the code that follows the for loop. The for loop will continue to execute until the condition becomes false. At that point, the loop will terminate and the program will continue executing the code that follows the for loop. The iteration section is executed at the end of each iteration. After the code inside the loops block has been executed, this is typically used to update the loops variable, for example to increment or decrement its value. Here's an example of a for loop that prints the number 1 to 10. In this example, the loop variable I is initialized to a value of 1 in the initialization section. The condition is set to I smaller than or equal to 10, so the loop will continue to execute as long as the value of I is less than or equal to 10. The iteration section is set to I++, which means that the value of I will be incremented by 1 at the end of each iteration. As a result, in this example, the for loop will execute 10 times, with the value of 1 for I on the first iteration, a value of 2 on the second iteration, and so on up to a value of 10 on the final iteration. Each time the loop executes, the current value of I will be printed to the console. For loops are a construct that I use a lot when I'm coding. This control flow statement is very convenient to iterate over a sequence of values or to execute a block of code a fixed number of times. They are very often used in combination with arrays or other data structures to perform operations on each element in the sequence, especially when we also need to index for it. In the next video, we're going to have a look at some practical examples with the for loop. Alright, let's have a look at an example for a for loop. Let's say we have some sort of array with a bunch of numbers in there. Let's give it the numbers 1 up to 10. And let's say we want to look for a certain number, maybe the number 7. And we also want to find its index. So what we're going to do is we're going to create an index variable and I'm going to set it to -1. And this way I know that if it's still -1 after executing the for loop, it means that the value was not found, since -1 cannot be a valid index. Alright, so what to do? Well, I'm going to create a for loop and I'm going to initialize an int I starting at 0. This is going to be looking for the element with that index in the array. And then it needs to be smaller than the length of numbers. Why? Well, otherwise I'll get an array index out of bound exception. And I'm going to increase I by 1 after every iteration. So what I'm going to do? Well, quite simple. I'm just going to check whether the value at I of numbers is equal to our search value. If it is, I'm going to store that in my index. At this point, if the value occurs more than 1 in the array, we'll have the last value in our index. I accept that feature for now. I just want to show you the result. So, and then here I'm going to be printing the index. All right, let's run this. Let's check out the result. And as you can see, the value of 7 was found at index 6, which makes sense because I started at 1. So 1 had index 0, 2 had index 1, and 7 had index 6. So this works. Something else that you can do is that you can also nest loops. And there's multiple applications for nesting loops. You don't want to do this too often because it's also some sort of code smell. I'm going to comment out this code for now. And I'm going to create the nested loops right here. So what I want to do, I want to generate a multiplication table. So I'm going to create an outer loop for the rows. Just going to start at 1. And I want to do it up and including to 10. So I'll say smaller than or equal to 10. And I'll do row plus plus. All right. So what do I want to do for each row? Well, I want to loop over yet another loop for its column. This is how I get the table. So I'm going to say for the integer column, also starting at 1 until the column is equal to 10. And of course, increase column by 1 after every iteration. And in here, I'm actually going to print the formatted string this time. And here's how I'm going to do that. All right. Then I actually want to move on to a new line after each row. So after this inner for loop, I'm just going to do a new line with nothing on it. And now I'm going to run my code and have a look at the result. And as you can see, we can get quite a nice multiplication table. For example, if you look up 5, you can see that 5 times 5 equals 25. Or that 7 times 5 equals 35. Or perhaps 8 times 2 equals 16, etc. In the next video, we're going to have a look at the last loop we're going to discuss, the for each loop. Last but not least, let's talk about the for each loop. The for each loop is sometimes also called the enhanced for loop. And they're a type of control flow statement in Java that allows a program to iterate over the elements in a collection or array. They are very similar to the for loops, but they are more concise and easier to read, as they do not require the programmer to specify the loop control logic, such as the initial value, the loop condition, the iteration step. Here's an example of a for each loop that prints the elements in an array of strings. In this example, the for each loop will iterate over the name array and print each element to the console. The loop variable name is declared before the colon symbol and is automatically assigned to each element in the array in turn. The loop will execute once for each element in the array, and the code inside the loop's block will be executed using the current value of name in this situation. Please mind that we could have named name anything. X would also have worked, but I choose name because that makes more sense. What I always do to myself that kind of helps reading for each loop is for every string X in names, or for every string name in names, go do the following. I use for each loops a lot, and they're a very, very powerful and useful tool for iterating over the collections or arrays, and doing so in quite a nice and readable way. They are especially interesting when you're not interested in the index of an element, but only in the element itself, since you will not have access to the index as I just showed you in the previous example. In the next video, we're going to have a look at some practical examples with the for each loop. Alright, let's have a look at some examples of the for each loop. Let's start with the basic example. I'm having an array of numbers here. And I'm going to start with a very easy example. I'm just going to iterate over the numbers here. So I'm going to say for every int number in my array of numbers, and what I'm going to do here is I'm just going to be printing the number for now. So if I run this, it's going to print every number that is in my numbers array, as you can see. All right, but let's do something more interesting. Something I also would not need the index for. So perhaps I would want to sum. I would initialize my sum to 0. And in here, I would just do sum plus equals the current number that I'm iterating over. And afterwards, I'll print the sum is followed by the sum. All right, let's run this again. And as you can see right now, it sums up the numbers leading to the sum of 45. And this can be done in a very, very easy, nice manner with the for each loop. Clearly, this could also have been done with the for loop, but it would have been a bit more work. So now we have seen the practical examples of the for each loop. It's time to continue with another topic, and that's break and continue. We've seen break already, but we haven't seen continue just yet. So let's see how we can use these with loops. Let's continue by talking about break and continue. In Java, the break and continue statements are used to control the flow of execution in loops and switch statements. The break statement is used to immediately exit a loop or switch statement and continue execution of the code that follows this loop or switch statement. Here is an example of a loop that we have seen. And there was a problem with this loop. I mean, not necessarily a problem, but if we wanted to only find the first occurrence, this loop would not do it. What we would have to do is we would have to break the loop here. We could do this by adding the break statement right here. So after it found the value that we are looking for, it would write the current index to the index of the value that was found, and then it would break the loop, meaning it would stop directly. So let's say I would have another 7 right there, since we were looking for the value of 7. If I'm going to run this again, it is still going to be 6. But without the break, it would have been the last one. So let me show you this. I'm going to comment out the break statement and run it again. And you will see that now it finds 9, the last occurrence of 7. So with the break, I can actually break out of the loop as soon as I found the value. The continue statement is somewhat similar to the break statement, but instead of exiting the loop completely, it causes the loop to skip the rest of the current iteration and just continue with the next iteration. So instead of jumping outside of the loop, it jumps back to the top of the loop. Let's have a look at an example. I'm going to comment this out for now. And I am going to be creating, again, a small list of numbers. And this time, I actually want to go ahead and loop over all these numbers. I'm going to use the for each loop for this. And in here, I will then say if the number is an even number, so I'm going to say %2 = 0. I don't want to do whatever I was planning to do, so I'm going to be continuing. If it's not an even number, I want to print it for now. So if I run this, it's going to not print it for the even values, because it's continuing back to the top of the if statement, meaning line 6. So in this case, it's only printing 1 and 3. Let me show you by enabling debugging mode what's happening here. So I'm putting a breakpoint on line 5, and I'm going to use the bug icon to start the program. And then it's going to pause, and we can actually see what happens as soon as it hits continue. So right now it's paused at line 5, and I'm just going to step to the next line. Here, this is where the loop starts. And the first time we're looping over the value is 0. Well, 0 modulus 2 is 0, so it's going to hit continue. And continue is going to bring us back to the top. Then for 1, it is again going to check, is the modulus 2 0? That's not the case. So it's going to skip the if statement, print 1, and then goes back to the top. Then for 2, it is again 2 modulus 2 is 0, so it's going to continue. It's going to jump back to the top, etc. So break and continue are useful tools for controlling the flow of execution in loops and switch statements, and you can use them to exit the loop in the case of break, or you can skip the current iteration and go back to the top of the loop. But there is a point that I'd like to make still, and that's that you should use break and continue as little as possible. Let me show you what I mean. For example, in this situation, I'm using continue, but it would have been way prettier if we would have written it like this. Don't have the continue statement, only print it whenever the value does not equal 0. For number modulus 2, same result, cleaner code. I do kind of think the break in the other example is okay, but there's another example that we have seen that I'd like to show you again that we could also have written with a break statement. And that's this one, the one we used for a while. So it's actually not too uncommon for people to do this loop very differently. So sometimes you'll see a loop like this being written like this, while true, and then just break out of this infinite loop whenever you found the value of 10. And of course this works and it does the exact same thing, and now you don't need to define a variable not found, but you would have to look at this code a little bit longer to figure out what it is doing. And therefore, I would say the original version looks a lot prettier, is better readable and better maintainable. So be careful when you use break and continue, and always think, can I use something else instead? Let's talk about an exciting building block in code, methods. Methods are the equivalent of functions and subprograms in some other languages. We just call them methods in Java, though you might hear me or someone else call them functions sometimes. Technically, Java only has methods. Alright, so what are these methods, you may wonder? Well, methods are blocks of code that perform a specific task. These blocks of code have names, and that's how we can call them. Calling them will make the method perform its task. This is how you can define a simple method. This very specific one is defined as public void print message. A lot of these things we'll be discussing later, but here's what we're looking at. We start with the keyword public. This means that it is accessible from anywhere within the application. There are other options too. These will be discussed later when we talk about access modifiers. The second word, void, means that the method is not having a result. It just does something. What the method does are the lines of code between the curly brackets. This is called the method body. The method body only has one line in this case, and it just prints the message "Hello Java people" to the console. The word print message is the name of the method. This is what we need when we're going to call the method. The last part is two parentheses. If the method requires input parameters, that will be specified here. And that's actually exactly what we'll discuss next. But before we do so, I remember struggling with recognizing methods and distinguishing them from variables when I just started Java, which is almost 15 years ago now, and I feel very old telling this. But if you feel the same way at this point, I mean not old, but the confusion about the variables and methods, don't worry about it. At this point, I have no clue how I managed to confuse those two, and you will have the same experience if you continue working on your Java skills. Things will become clearer if you stick with it. Alright, so now we got that out of the way. This can be difficult, no worries. We have seen how to create basic methods without input parameters, but things get more interesting when we add input parameters to the mix. So let's explore how we can make them more dynamic by adding input parameters in the next video. We can make our methods more interesting by providing input for them. Methods need to be defined in a way that they accept this input. This is done with the parameter list. To specify input parameters for a method, you include their type and name in the method's definition. For example, here is a method that takes two input parameters, an int and a string. This is the parameter list. In order to add parameters, you need to specify the type and the name. When calling this method, you would need to pass in two arguments, an integer and a string. You can then use them throughout the method. These arguments will be assigned to the input parameters number and message respectively. And we can use them in the method to perform a task. So let's say we call it with the arguments for and hello. Then the variable values will be for and hello. So within the method, when we're talking about number, the value will now be for. In the method, when we're talking about the message, the value will now be hello. The terms arguments and parameters are often used interchangeably. However, they are slightly different concepts. Parameters are the values that are defined in the method definition and receive the values that are passed to the method when it's called. Arguments are the actual values that are passed to the method when it's being called. Here's an example to illustrate the difference between arguments and parameters. In this example, number and message are the parameters of the printMessage method. When the method is called from elsewhere, the values passed to it are the arguments. Another thing that's important to note is that the number and type of input parameters must match the method definition. If you pass the wrong number or type of arguments to a method, you get a compile time error. So right now we have seen methods with and without input parameters, but all the methods we've seen were not returning any results. In the next video, we're going to have a look at methods that produce results. Let's talk about returning values. So far, our methods have not been returning anything. This was indicated by the void keyword. In Java, a method can return a value to the calling code when it has finished executing. This is called returning. The type of value that the method returns is specified in its method definition using the return type. So void is a return type. This void return type that we've seen is used to indicate that the method does not return a value. A method with a void return type simply performs a task and does not return a result to the calling code. And that's the case here. Our example, with the void return type, just prints a message to the console. When a method has a non-void return type, such as this one which is returning an int, it must return a value of the type to the calling code when it finishes executing. This is an example of a method that has an int return type and calculates the sum of two numbers, a and b, and is returning the result of a plus b. The return value can then be stored or used as input for another method. Here's another example of a method, but this one has a string as a return type, and it concatenates two strings. In this example, when the concatenate method is called with the arguments hello and world, it returns the value hello world to the calling code. The value can then be stored in the result variable. It's important to note that when a method has a non-void return type, it must return this value. If the method does not include the return statement, or if it returns something of the wrong type, you will get a compile time error. Alright, so now we've also seen how to return values. There's one very important thing left. Let's see how we can actually invoke the methods. Alright, we've seen how to create methods, but when we just create methods, nothing happens and nothing is being executed. What we need to do to execute the method is to invoke the method. This is also phrased as calling the method. How to do this? Well, you call it by its name and pass any necessary arguments to it. Here's an example. The text in bold shows how to call the method printMessage that takes no argument. As you can see, you must provide the empty parameter list. Without the parentheses, Java will be looking for a variable. When a method takes up a parameter, such as this one which takes up a string, you need to specify an argument when you're calling it. In this case, we're invoking the method by passing in the argument hello world. The value hello world will be then assigned to the message parameter. And the result of this method will be hello world in the console. Here's another method. This one returns an int. When you invoke this method, you would pass an argument to it, since it also has an int as a parameter, and then use the result in an expression. So in this case, we are assigning the return value to the int result. And this is what will happen. When we call it with add 42, 42 will be assigned to a. So a is going to have the value of 42, and 42 plus 1, which equals 43, will be returned. 43 is going to be the result of the function, and that's going to be assigned to result, so the value of result is going to be 43. And yet another example. This method takes two input parameters, and we're calling it with the arguments 3 and 4. 3 is going to be the value of a, and 4 is going to be the value for b. So a is 3, b is 4. Then the result of a plus b, which is 7 in this case, is going to be returned. So the result of the method is going to be 7. And this means that the result, int result, is going to be 7, since we assigned the result of the function to a variable result. Again, I have an important note to make, and that is that the number and type of arguments and their order must match the parameter list. If you pass the wrong number or the wrong type of arguments, you might call another method than you intend to call, or if it doesn't exist, you'll get a compile time error. Alright, so we have seen how to create a method, how we can send input to it, and how to return a value. And also how to capture the result of a method. Earlier in this section, I talked very briefly about the public keyword. This is an access modifier. In the next module, we're going to be talking about access modifier and the static modifier. And yes, those are very tough topics, but no worries, I'm going to guide you through this. Access modifiers decide from where you can access class members. Class members can be fields, methods, constructors, and other classes. So in Java, access modifiers are keywords that you can use to control the visibility and accessibility of these class members. There are 4 access modifiers in Java. Public, which means that they can be accessed from anywhere within the program. Private, this is the most restricted one, and it means you can only access this member from within that very same class. Then we have protected, and that means it's accessible from anywhere in the same package and its subclasses outside the package. And then we also have default. This is when there's no modifier, and this means that it can be accessed from anywhere within the same package. Here are some examples of how to use access modifiers in Java. We have 4 fields here, an int x, int y, int z, and int w. X is public, y is private, z is protected, and w is default. In general, it's a good practice to use the most restrictive access modifier that's appropriate for a member. This helps to encapsulate and hide the implementation details of your class and prevent any unintended modifications from outside. The access modifiers can actually also be applied to inner classes and interfaces, but we won't see that for now. The rules for visibility and accessibility are similar to what I'm going to explain in the next few videos, but there are a few differences in how they're being applied. These nuances will be skipped here, but it's definitely something you can find out when you play around with them yourself. We're going to play around with each of the 4 modifiers in the next few videos. Let's start with public. Let's start with the easiest and most accessible access modifier, public. The public access modifier is used to indicate that the member can be accessed from anywhere within the program. Members with the public access modifier are visible and accessible to all ports of the code. It doesn't matter in what package or class they're being defined. Here's an example of a class called myClass with a public int x. To access and modify the value of x from another method, you would write something like myClass object, just to give it a name, say equals new myClass, and then on this name object we can just go .x to assign a value to it, and wherever we need it we can just access it with object.x. We are updating the value of x here, and we are accessing it to assign it to a new variable y. Methods can also be public. A public method is a class member that can be called from any part of the program. So, if we want to call this public method print message, elsewhere in a method we can then create an instance of myClass, and on this instance, which we call object here, we can go .print message in order to call the method in the instance. Let's see all of this in action in IntelliJ in the next video. Alright, here I have a class person, and as you can see, person has a public field name and it has a public method say hi. I can call this from anywhere within the program. As you can see on line 7, so within the same class, I'm using the public field name. But I can also call it from outside my class. In order to do that, I need to create a new person object. And then I can address the name and I can set it to something. I can say the name is Maria. And then in here, I can actually trigger the method say hi, since say hi is public. So I'm going to run this, and as you will see, it's going to print, hi, I'm Maria. Well, hello, I'm Maria. Close enough. Alright, so I can access this from anywhere within the program. And to prove my point, I'm also going to access it from outside the package. So I'm going to create another package. I'll just call this more access modifiers. And in here, I'm going to create another class, call this one app. And it's going to have a main method. And again, I'm going to be creating a new person object. And as you can see, I'll be able to access the name. But something goes wrong. Well, not really. But since I'm outside the package, I need to import this class. So let me import the class. And I'm importing it with import access modifiers.person, because that's where it is. And now I can actually access it. So I'm going to set it here to Bob. There we go. And now if I call it here, you can see that we can still access the say hi, and this time it's going to print hello, I'm Bob. Alright, so this is the public access modifier. The public access modifier is the most permissive access level. Let's talk about the most restrictive access level next, private. Let's talk about something private. Nope, not like this. I mean Java private. The private access modifier in Java is used to indicate that the member can only be accessed from within the same class in which it's defined. When members have the private access modifier, this means they're not visible or accessible from other classes or other packages. So remember, it's only accessible from within the same class as the private member. So this code over here, where we create an instance and then access the field directly, is not possible from outside the class. We can access it from within the class though. As you can see happening on the slide here, we have a private int x and we can use it in the method that's in the same class. To access and modify the value of x from outside the my class while keeping x private, you'd have to add getters and setters that are accessible. So you could create two public methods, one for setting and one for getting the value of x, and this would make it possible to access x from outside the class. So these methods, setX and getX, they're used to set and get the value of x. We call these getters and setters. From another class, you would not be able to access the value of x directly, but you could do so using the getters and setters to get the value. At the bottom you can see how you would do that. You would create an instance of the object and then call the function setX to set the value and call the function getX to get the value. A private method is a class member that can only be called from within the same class. So this one, the print message that's private, can only be called from within the myClass class. From another method, you would not be able to call the print message directly, as it's marked private. But you could call it from another method in the myClass, as being done here. In the print hello, we have access to the print message, so we can call it. The private access modifier is the most restrictive access level in Java. It is used to protect the implementation details of a class from being accessed or modified from outside the class. This can actually help to prevent any unintended modifications, and it promotes encapsulation. It's important to note that the top-level classes and interfaces cannot be private. They would be of no use, since they could not be accessed from anywhere anyways, so we might as well not create them. Let's see for ourselves how private is working in IntelliJ in the next video. Alright, I've expanded our person class with two private members, a private string secret on line 5 and a private methods on line 11, private void tell secret. The main thing I'd like to show you is that I cannot use this from outside this class. So let's move over to my main.java and let's try to see whether a person Maria we can access the secret. And as you can see, we can't. If we hover over it, it tells us why. It says secret has private access in the access modifiers.person class. And it comes up with a solution, and that's pretty much changing the access modifier. That's not what we want. And the same goes for the tell secret. We cannot call it because it has only accessibility inside the class person, so we cannot say tell secret. And again, it will tell us that it has private access. So alright, let's get rid of this. Let me tell you from where we can access it. Well, only from within this class, starting with the curly bracket on line 3, ending with the curly bracket on line 14. So on line 12, you see that we use the private field. We use it in the private method. And we could call the private method from within the say hi. And right now, we would be able to tell the secret from outside, but only via the say hi method. So let's move back to our main and let me show you that you can actually use it right now, but there is going to be a little problem. I'm going to run this code and say hi is going to call the tell secret method, but there is no way we can set the secret from outside. So the secret is null. It has not been set, and this is why it prints the value null. We can only access it from inside the class, not from outside the class. So let me get rid of this one. And here you can see it once more. So private means only accessible from within the class, and public means accessible from anywhere. There's two more access modifiers we need to talk about, and the first one we're going to be discussing is the default modifier. When you don't specify an access modifier, you implicitly still specify an access modifier, namely the default access modifier. The default access modifier makes members only visible from within the same package. It is also known as the package private access modifier. It's used to indicate that a member, such as a field, method, or constructor, can be accessed from within the same package, but not outside this package. So from outside, you cannot access the default members. Here's an example. Members marked with the default access level are not explicitly marked with any access modifier. As you can see, we just have int x. Nothing is being specified. To access and modify the value of x, we can specify the following code in the same package in a method. So we can create an instance of my class, and then we can just access x like we did before to assign a value to it. And if we want to retrieve the value, we do so with the name of the instance, in this case object.x. Methods can also be default. And a default method is again a class member that can be called from within the same package as the class, but not from other packages. So to call the default print message method from within the same package as my class, we simply write my class, give the name object, in this case, equals new my class, and then we can say object.printMessage and just access it. The only important thing is that this must be in the same package, otherwise the print message is not going to be accessible. So our package private access modifier, the default access modifier, is used to control the visibility and accessibility of a class member. When there is no explicit access modifier, it gives the default access, which means that it can be accessed from within the same package. Let's have a look at a practical demo of the default modifier in IntelliJ in the next video. In order to demonstrate the default access level, I'm going to remove the publics here. So once I remove the publics, they now have default access modifier. And IntelliJ is giving away the clue already. Yes, there is a related problem. So from within the same package, there's no problem. We can still access the name and the say hi method like we were used to. But the problem is inside the more access modifiers. It's over here. Since it's now package private, it's default. We cannot access it from outside the package, and it says so when we hover over it. It says name is not public, cannot be accessed from outside the package. And it says the same thing for say hi. It cannot be accessed from outside the package. And the solution would be to make it public. Alright, so that's the default access modifier. In this case, it can only be accessed in the package access modifiers because that's where I have my class person, and that's where I specified the default class members. The default access modifier is less restrictive than the private access modifier. The private access modifier only allows access from within the same class. The default access modifier is more restrictive than the public access modifier. But the default access modifier is also more restrictive than the protected access modifier. We haven't seen this one yet, and we're going to have a look at the protected access modifier in the next video. Alright, the last access modifier is the protected access modifier. This one is a lot like the default modifier, with one difference. It's only accessible from within the same package and from subclasses outside the package. So you can access the protected members in the child classes that are outside the package. Here's an example of how to use the protected access modifier on a field. We have protected int x. To access and modify the value of x from within the same package, you would write, again, my class, give it a name, in this case object equals new my class, and then we can just access it directly. This cannot be done in unrelated classes outside the package. We can also have protected methods. In this case, we have protected void print message. And we can access this one just like we could for the default level, with the addition that we can also access the print message in a subclass. So we have seen 4 access modifiers in Java. Before we check out protected in IntelliJ, I'd like to show the access modifiers from least strict to most strict. What I think is a bit counterintuitive is how default is more restrictive than protected. The word protected sounds stricter to me. Just remember, it isn't. Since you can access the variables in one more place, namely the child classes. This is a concept that we have not seen yet, but we'll see soon. I'm actually going to show it to you in the next video, where we're going to see protected in action in IntelliJ. Alright, let's have a look at the protected string name and the protected void say hi. The field is on line 4 and the method on line 7. As you can see, there's one related problem. But we can access it from within the same package. So if we move over to the main class, we can see that there's no problem here. It's in the same package as the person, so we can just access the protected fields. But there's a problem in the more access modifier package. Here is the app. And I told you that it's accessible from within the same class and in subclasses. So let's make app a subclass of person, and this is not going to solve the problem. Don't worry too much about this whole subclass thing. I'm just saying that it's going to have all the properties and methods that person has too. But as you can see, it's still not accessible right now. So what we mean with accessible in a child class, an app is now a child class, is that it can use the fields as if they were its own. So let's say I'm going to have another method in here, just let's say it's called greeting. And in this greeting, I can access the say hi methods and I can access the name attribute. What I cannot do, I cannot access the protected fields on objects that are not its own object. This is a bit complicated and it might actually make more sense after the next video. So for now, just remember that protected means it's accessible from within the same package, just like what we're used to, and it's accessible in subclasses as if it were its own members. In the next video, we're going to talk about another modifier, the static modifier. It's not an access modifier, but it's a very important modifier for Java. Let's talk about static. And I don't mean static like this, or like this. I mean the static keyword in Java, which is used to indicate that a member belongs to the class and not to the instance. And before we continue, I'd like to give another tough topic warning. This topic is typically hard to understand for beginners, so please do not worry if this one is hard for you to wrap your head around. This is normal and it will become logical to you eventually if you stick with it. I promise. So before I go back to static, I want to repeat the difference between classes and instances. A class is a blueprint. It contains things that define the actual objects. And an object, also called instance, is the actual embodiment of an object of that class. Alright, so back to static. In Java, the static keyword is used to indicate that a member belongs to the class itself and not to an instance. And that might be hard to wrap your head around, so let's look at a non-code example. If we look at the blueprint of the houses will all have the same architect. This is the person who made the blueprint. Arguably, the architect belongs to the blueprint and not to the instance. Even if there are no instances of the house built, the architect will be the architect of the design or blueprint. And let's look at another code example. Let's say your friend is going to get a puppy. At this point, your friend doesn't have the instance of the puppy just yet. But there are some things you can do for the puppy before it arrives. In Java terms, things you can do, methods, that do not depend on the instance, because you don't need the actual puppy just yet. For example, you could buy the puppy a toy. But you cannot walk the puppy yet. This method really belongs to the instance. In other words, you need a puppy for this. So getting things for the puppy can be considered static. And walking the puppy can be considered non-static. We need the instance to be able to do this. Having static members means that you can access and modify static members without having to create an object of the class. Here's an example of how to use the static keyword on a field. We say public static int x. So a static field is a class member that is shared by all the instances of the class. To access and modify the value of x, we could write something like this. We can go myClass.x directly, so we do not need to create an instance. We can also have static methods. Here's an example. We have public static void print message. To call this method, we don't need an instance. We can call it directly on the class, so myClass.printMessage. The static keyword is used to indicate that a member belongs to the class itself and not to any instance of the class. This can be useful when you want to define a member that's shared by all the instances, or when you want to define a nested class that does not depend on the outer class. And then I want to make an important side note again, and that's that these static members are not associated with any particular instance of a class, so they cannot access or modify the non-static fields or methods of the class. Non-static members, on the other hand, can access and modify both static and non-static members of the class. And this is because we cannot access the non-static context from a static context. For all we know, it's not there. Think of the example of the houses. We can't be sure there's a front door when we talk about the blueprint and an architect, because maybe the house is not being built just yet. In general, it's a good best practice to use static members sparingly, as they can make your code more difficult to understand and maintain. However, they can be useful and a clean solution in certain situations, such as when you want to define utility methods or constants that are used throughout your program. Let's have a look at some examples of static in the next video. Alright, so I've created a class mathUtils. It contains a static field and it contains a static method. The static field is pi. The static method is subtract, and as you can see, it's a very simple method. It just takes two numbers and then returns the result of subtracting a by b. Alright, so let's see how to call this. So I'm going to move over to our main, and in here I do not need to create an instance of mathUtils to be able to get the value of pi, so let me just print this value to prove my point. And I don't need to create an instance to actually call my subtract method. Then I can actually assign the results to a variable called result. Oh, it's of type double, of course. And now I'm actually also going to print the result, and as you'll see, that's going to be 7. So let me run this. And as you can see, I have the value of pi and I have 7. This is not the only way to access them though, and please mind this is not a best practice, but I do want to show you this. I could create an instance of mathUtils, which is a bit of a weird thing to do, but I could. And then on here, I could also access the value of pi. Like this. Please mind this is not a best practice, but you can do this. And I can also call the method. And as you can see, it's not even suggesting it because it's not something that's considered best practice to do, but it will work. It's a bit reluctant though, but it does work. So if I'm running this, it will show you the results too. But what is important to know, that if pi is changed at any point, it's changed for all instances. So I am going to create another instance of these mathUtils, which is a very weird thing to do, but I will. And I'm going to say here m1.pi equals 12. Of course, pi does not equal 12, but I just want to prove my point here. And right now, if I'm going to print the value of pi in different ways, so I'm just going to do it like this. Also on the mathUtils one, like what you should be doing, and yet another space where I'm also printing it on M1, you'll see that it's going to be changed for all the places. So let me run this and show it to you. And as you can see, it is 12, 12, 12. So once it's being changed in one place, since it's static, it's being replaced everywhere because there's only one pi and it belongs to the class mathUtils. You can access it via the instance. You shouldn't, but you could. Alright, to sum up, static means that the field or method belongs to the class and not to the instance. We have seen the string class and quite some text variables already, but we did not talk enough about it and all the built-in functions just yet. Before we start, I want to repeat that the string class in Java is a class that represents text, which is a string of characters. String objects are created using string literals or the new keyword. Here we're showing both. Both of these statements create the string object with the value maker. There is a subtle difference between them that we'll discuss in a bit. In the first example, I'm using the string literal. In the second example, I'm using the new keyword. You can concatenate two strings using the plus operator. For example, string greeting equals hello plus world. This will create a string object with the value hello world. Alright, so strings are the data type for holding text. They come with quite some convenience methods for working with text, which we'll see in the next video. String class comes with quite a few methods that are commonly used to work with text. This helps dealing with strings. We're going to discuss a few of the string methods that are commonly used in this video. The first method is to determine the number of characters of the string. It's the length method. The length method returns the length of the string in terms of a number of characters it contains. For example, let's say we have a string str that contains the text hi all with an exclamation mark at the back. When we want to get the length of the string, we can say int length, to store the result, str.length. And if we then print the length of the string, we'll see that it's all the characters. In this case, that's 7. The space and the exclamation mark are characters as well. The next method we're going to have a look at is char add, and this takes an int index as an argument. This method returns the character at the specified index in the string. The first character has index 0, the second character has index 1, and so on. Let's see this for ourselves in IntelliJ. If I'm going to print the first character of a string, that's going to be the uppercase H. There you go. Alright, another one related to index. But this one determines the index of a string in a string, and it's done with index of, and then it takes a string as an argument. The index of method returns the index of the first occurrence of the specified string within the calling string. That might sound like a lot, so let's move over to IntelliJ and see it for ourselves. So let's go ahead and use the index of to find the string all. And there we go. It is returning 3, because it starts counting at 0, 0 is H, I is 1, the space is 2, and the A is 3. This is where the substring starts. It's the first occurrence, in this case also the last occurrence. So this is how the index of works. If the specified string with index of is not found, it will return -1. We can also create smaller strings using the method substring and then specifying the begin index and optionally the end index. This method returns a new string that is the substring of the calling string, starting at the specified begin index and extending to the end of the string or the specified end index. This does not modify the original string. Let's have a look at this example in IntelliJ. So if I'm going to say str.substring and then I specify the begin index 3, it is going to start there and go on until the end of the string. I'm also going to do something similar, but now I specify an end index as well, and I'm going to specify 5. And this is quite a subtle, important thing to know. So the first one, you can see here, it's just going to continue until the end of the string. The second one, you might be thinking, 3, 4, 5, that should have been the full word all, but it's just AL. Well, the thing here, it's an exclusive range, so it's going to continue until the end index -1. Again, it's an exclusive range. Next, we have the methods toLowercase and toUppercase. These methods do what they promise. They return a new string that is a copy of the calling string with all the characters converted to either lowercase or uppercase. So let's go ahead and do toUppercase. And then followed by a toLowercase. Please mind that also this does not modify the original string. As you can see, we have a hi all uppercase, and then hi all lowercase. The original string still has an uppercase H and the rest lowercase. The last one we'll mention is trim. This method returns a new string that is a copy of the calling string with leading and trailing white space removed. So let's move over to IntelliJ for another example. In order to demonstrate this, I first need to have a new string with some trailing and ending white spaces. So there we go. I'm just going to say space, 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 blah, 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 and some ending spaces. And right now, I am going to print str1.trim. And as you can see, this just prints the string without the leading and trailing spaces. Of course, the original one still has them. It's not being modified. So far, we've seen a few common methods. There are more methods, but this will give you a great start. Whenever you need to do something that feels like, this sounds like something you do a lot with text, there's probably a built-in method for it. Let's talk about a very nice feature of the string class, immutability. We're going to do so in the next video. Strings are a special type. They are immutable. This is because string is an immutable class, which means that once you create a string, you cannot change the value of that string. If you assign a new string value to the same variable, a new object gets created, and the variable now holds the reference to this new object. This can be beneficial because it allows you to use string objects in a thread-safe manner, without having to worry about another thread modifying the string while you're using it. Okay, we have not seen threads yet, but this will make more sense later. Let's prove that this is how it works, right here in IntelliJ. I'm going to create a string s1, and I'm going to set it equal to hi. And now I'm going to say string s2 equals s1. So s1 is also going to get the value of hi. And then, just to make sure that this is what's happening, I'm going to print both s1 and s2 separated by a space. Alright. And now I'm going to override s1 with a new string hello. If the string were immutable, then right now, if I would print it again, s2 would also have changed, because I've set s2 equal to s1. So let me go ahead and print this again. Another space and plus s2. Alright, let's run this. As you can see, the first time we get hi hi. The second time we get hello hi. This is because the string object is immutable. A new object gets created instead of overriding the value on the old object. Let's contrast this with a mutable object. For mutable objects, the original object gets altered instead of creating a new object with a new variable. I have created my own type here, and it's called text. Text has a variable description of type string and is a private variable. I have created a getter and a setter to access and modify the variable description. Let's see how this is different right here. So I'm going to create one text, call it T1, I'm going to say new text. On T1, I'm going to set the description, well, let's make it high as well. And then now I'm going to create a text2, and I'm going to set it to T1. And I'm going to do something similar. I'm going to print both. So I'm going to say T1 get description plus a space, and then I'm going to say T2 dot get description. Alright, And now I'm going to do something similar as I just did. I'm going to alter T1. I'm going to update the description. I'm going to say set description, and I'll make it hello. And then I'm going to copy this line and do this again. And what you'll see this time is that both the ones have changed to hello, because we're looking at the very same object in the memory here. So let me run this again. As you can see, the second part, I get another high, which is both for T1 and T2. After updating T1, both of them are hello. Let's make sure that this is clear by drawing the memory of what is happening for both scenarios. So let's first look at the immutable string. So here we have the code snippet. We have string s1, we set to high, and then we set our s2 equal to s1, and we update s1 with hello. Here's what's happening. In the first step, we create s1, and an object on the heap gets created, and we store the reference to this object on the stack in s1. On the next line, we set s2 equal to s1, so s2 is holding the reference to the same object on the heap. In the next step, we're actually creating a string hello and make s1 point to the string hello. But as you can see, s2 is still pointing to the original object, which has not changed. Hence, we get hi and hello in the outputs. And this is what's happening for text. We start with creating a new text field, and the description of type string is then null still. What we do next is that we update the description to be high. So the description on the object on the heap is actually pointing to another object on the heap. In the next step, we set T2 equal to T1, so both T1 and T2 are pointing to the same object on the heap. And finally, we update that object on the heap to hold another value for description. As you can see, a new string gets created, and the object on the heap is now referencing to this new string object with the value updates in this situation. And as you can see, both T1 and T2 are still pointing to the very same object, even though that object is now pointing to a new object. And this means that once we go and ask for both T1 and T2, hey, what's the description? They're looking at the very same object, they're holding the same reference, and of course, the description is then going to be the same thing. So if one of them changes, both of them changes, because they're actually looking at the same object still. Alright, now hopefully we understand how immutability works. It's tough, don't worry if you understand it for like 80% at this point. It will come, I promise. Having done this though, it's time to talk about comparing strings in more detail. Let's talk about how to compare strings, or objects in general actually. When we were comparing two primitives, for example ints, we would do this with the double equal sign, like this. We would have an int x, we would have an int y, and then we could create a boolean to check whether they were the same by saying x equals y. In this case, it would be true. When we compare objects this way, we're actually not comparing the value, but the reference. So let's walk through this example that applies to objects. We first create a string. As you can see on the slide, we create a string s1 and it holds the value of high. And we create a second string, using a new keyword also holding the value of y. So we have two strings on our memory. And these strings are having the exact same value, but they're stored in different objects. They have different references, so even though we might want to say that equals should be the same, it will conclude that they're not the same, because they don't have the same reference. The value of the boolean will therefore become false. The string is not a primitive value, but an object, so this is true for strings, but it's actually also true for other objects. If we want to compare objects for equality, we need to use the equals method that you can see on the slide. This will not look at the reference, but at the content of the string. If both strings hold the same text, it will conclude that it's the same as opposed to what the double equal sign did. But then strings are a bit more special than other objects. Since strings are so common in Java, they are stored in a special way for memory optimization. Strings are stored in the string pool. And this has unfortunately nothing to do with the swimming pool. The string pool is a special memory area where strings literals are stored. When you create a string using a string literal, the JVM checks the string pool to see if an identical string already exists. If it does not, the JVM will create a new string object and store it in the string pool, then return a reference to it and store that on the stack. If it does exist already, which is happening in the second case here, where we're creating hi again, the JVM will reuse the existing string object and return a reference to it. In this code, the JVM will create a new string object with the value hi on line 5. It will store it in the string pool. And it will assign the reference to the s1 variable. On line 6, it's going to look at the string pool and will find the string hi there already. It is then going to reuse this object and return the reference to s2. So when we are comparing for a reference here, they will be the same. So if I'm going to say here s1 equals s2, you'll see that these are actually the same due to the string pool mechanism. They are holding the same reference. If I would have created this one with a new keyword, it would actually have created a new object, and then the equal sign would go ahead and produce the result false, because they would not be the same reference, as you can see in the console now. The string pool can be helpful because it allows the JVM to reuse string objects, which can save memory and improve the performance of your program. However, it's important to remember that the string pool only applies to string literals and not to strings created using the new keyword, as I just showed you. So, how should we compare strings if we want to make sure that we're actually comparing the value? Well, we need to use the equals method. If we would want to know whether s1 matches the content of s2 and we don't care about how they're created, we would have to use the equals method. And we do so with the dot equals and then specify the one that we want to compare it to. And if I run this now, you'll see that it's true again, even though I created one of the strings with a new keyword and one of them with literal. So again, use equals when you want to compare, because right now it doesn't matter how the strings are being created. All that matters is whether they have the same value. Strings are a bit special in Java because of the string pool and the immutability. If you want to change a string a lot, many objects get created, and this is actually against the memory optimization mechanism. In this case, it's better to use the string builder. We will see the string builder in the next video. As you know, the string class in Java is an immutable class, which means that once you create a string object, you cannot change the value of the string. This can be limiting if you need to build a string by concatenating multiple smaller strings together. That's where the string builder class comes in. The string builder class allows you to create some sort of mutable string, which means that you can modify the value of the text after it has been created, without creating a new object. To use the string builder class, you first need to import it from the Java lang package. You can then create a string builder object using the new keyword, like this. String builder SB is new string builder. You can also specify an initial value for the string builder object by passing a string to the string builder constructor, like this. Once you have a string builder object, you can use the following methods to modify the string. You can use append to add a string to the end of the string builder. You can use insert to specify where to insert a certain string in the index of the value of the string builder. You can use delete to delete part of the characters of the string builder. You can specify the start and the end index for this. And you can use replace, specifying what you want to replace from where to where and by what. Let's move back to IntelliJ and see some examples of how you might use the string builder to build a string. Alright, so we have the beginning of our string, and I'm going to append a piece of text here. And I can turn it into a string by using the toString method. And then I can catch the result in a string. And now there is a string with the content, Micah loves Java. Of course, I could also append multiple things. Let's have a look at this one. I'm going to create a new string builder object, call it sp1, and I'm going to say new string builder. And let's start with hello. And I'm going to append multiple things to it. So first time, I'm just going to append a comma and a space. On the second line, I'm going to be appending, of course, world. And then let's append an exclamation mark as well. And eventually, let's store this in a string named greeting. I'm going to say sp1 toString. Whoops, I actually used sp over here. Let me quickly update that. All right, so let's explore what happened here. This code created a string builder object with the initial value of hello. Then it appended a comma and a space to it, and world to the end of the value. Finally, it appends the exclamation mark. And then it converts the string builder to a string using the toString method. The resulting string object has the value hello world. String buffer is another class in Java that is used to create mutable strings. Like string builder, string buffer allows you to modify the value of a string after it's been created with similar methods. One key difference between string buffer and string builder is that string buffer is thread safe, while string builder is not. This means that multiple threads can safely use a string buffer object at the same time without having to worry about synchronization issues. So far, we've only looked at single-threaded code. That means that only one path of execution is happening at the same time. When we get to concurrency, we'll explore multi-threading, and this is where multiple things are happening at the same time. Then you'd have to worry about thread safety. Just one more side note. The added thread safety of string buffer comes at the cost of a slower performance compared to string builder. In general, you should use the string builder unless you really need thread safety of string buffer. In most cases, the performance difference between the two classes is not significant enough to justify the complexity of using string builder when you need thread safety. Let's talk about dates. Just to avoid any confusion, when I say dates, I don't mean the edible date or the enjoyable date. I mean dates in Java, though they're quite enjoyable. It's a way of dealing with the calendar system. And the first one I want to start with is the class localDate. LocalDate is a class in the Java Date and Time API that represents a date without a time or a time zone. It is part of the Java time package, which was introduced in Java 8, and it's a really nice replacement for the old Java util date and Java util calendar classes. Dealing with those was quite a nightmare. To use localDate, you first need to import it from the Java time package. You can then create a localDate object in a few different ways. Let me show you in IntelliJ. Alright, let's have a look at how to create a few dates. So I'm just going to say localDate LD, and of course I need to import it from the Java time package. And I'm going to say localDate now. And that's going to return the localDate that my system is on. If I want to have another localDate, I could actually also create it with the off method. So I'm not using the new keyword here, I'm using the off method, and this one is internally calling the constructor of localDate. So I can specify the year, so perhaps 2000, and a month, the 4th month, and let's go with the date, the 1st. Both of these methods create a localDate object. The first one represents the current date, and the second one creates a localDate object of my specified year, month, and day of month. There's actually one more way to create a localDate, and that is by parsing. And by parsing, I can just insert a string, like this one, 20, 23, 01, 01. And this will create the date January 1st, 2023. All right, let me print them so we can see the results. Plus a space, LD1 plus a space, and LD2. And as you can see, the dates have been created. Once you have a local date object, there are a lot of built-in methods for accessing and modifying the date. You can see we have ones to get the year part, month part, day of the month, but also to alter with plus and minus methods. Let's have a quick look at those in IntelliJ. So let's say I want to alter today's date. And this is quite important because this might not think how you think it should work. So you see a lot of methods exist, but I'm going to use the plus days. And I'm going to be adding 5 days. So it's January 8 right now, so you might think, oh, well, then we should end in January 13. But look what happens. If I go ahead and print LD right now, you'll see that nothing has changed. And this is because it's actually not altering the local date object, but it's creating a new local date that's holding the new value, just like with the string objects. So I'm going to say here, local date LD3 equals local date plus days 5. And then if I print LD3, you'll see that this is actually the new date with the plus 5 days. You can do the same thing for minus days, minus years, minus months, etc. They all return a new date object with a new value in it. If I were to do the getYear method on this one, it will actually show me the year and leave out all the other details it has on local date 3. As you can see, we then get 2023, and when we're doing get day of month, you'll actually see that it's going to return the 13th. As you can see in IntelliJ, there are more methods and dates, but this will give you a good grasp of local dates, and you probably have an idea of where to start. But what if we want to talk about times? Well, we use local time, which is what we're going to have a look at in the next video. When we're dealing with times, we use a built-in class called local time. Local time is, just like local date, a class in the Java Date and Time API that represents a time without a date or time zone. It is part of the Java time package. To use local time, you again first need to import it from the Java time package. You can then create a local time object in a few ways. Let me show you in IntelliJ. Alright, I'm going to do something similar. I'm going to create a local time. And in order to work with local time, I need to import it. I'm going to call this one LT1, and I'm going to say local time now. This is going to represent the current time of my machine. I could also create a custom local time. I could use the of method again. So I can say local time of, and then I can specify the hours. So maybe I go for 6 and perhaps 30 minutes and 12 seconds. And again, I can also parse a local time. I can use LT3 and then say local time parse. And then again, I'll use a sequence of text. And then again, I'll use a char sequence, which is a lot like a string. So there we go. All right, so let's print all these and see what they look like. I'll add a space in between again. There we go. Let me show you what we've created. And as you can see, we get the current time, which is, well, around 9:30. Then we get my custom time, which is 6:30, and we get just before midnight. Just like for the local date, there are methods built in that you can use to access and modify the time. Let's go over some of them. So first of all, we have the gets. We can get the hour, the seconds, the minutes, etc. This will just return a part of the time. It will not convert the time to minutes or something like that. We can also use the plus hours, plus minutes, and plus seconds. So for example, I can add 1 hour. But just like the local date, this one will not change. It's going to return a new local time object with the added hour to it. So I'm going to create an LT4 out of this and then show it to you. So the plus and minus methods, they don't alter the original object. And as you can see, this one has 2241. And again, there are many more methods, but you'll find them whenever you need them. This should definitely get you started. We have seen now how to create local dates and local times, but what if we needed to combine these two? It sounds a bit too obvious, but we're going to need the class local datetime to do so. Let's have a look at this one in the next video. When you want to meet with someone, you would need both a date and a time for this. This is where the local datetime class comes in. The local datetime is the class in the Java date and time API that represents the date and the time without a time zone. It's part of the Java time package. Let's move over to IntelliJ and create some local datetimes. You might guess this already a little bit by now, but we would need to import it first. And then we could use the now method to create the current local datetime. There I go. And I can also go ahead and use the local datetime of. And this one has quite a few overrides. And the first one that you can see is local date, local time. And this actually means that we can use a local date and a local time object to create a local datetime. Well, I don't have them available here, but I could. Instead, I'm just going to enter the year, the month, the day, etc. So I'm going to start with 2015, the 6th month, the 12th day, and then the 15th hour, 10 minutes, and 32 seconds, like this. There's a lot of override. I don't want to add those. And of course, we can also parse. But this parse looks a bit less obvious than the others, because you need to stick to certain formats, and this is one that you could use. So let's create another date, 2004, the 11th month, and the 30th day. And then I need to specify the time, and I separate them by a T. And I go and I say 20 hours, and I don't know, 10 minutes and 23 seconds. There we go. So let's go ahead and print all these. Of course, again, with a space in between. And let's run it. I actually haven't showed this yet, but this could be more readable with a line break in between instead. And I can create these with \n. So if I run it right now, you'll see them on different lines. And you can see what we have created right here. Now that we have the local datetime object, it will probably not surprise you that there are built-in methods for accessing and modifying the date and the time. Let's go back to IntelliJ and see some of these. Of course, we would need to store the result in a new local datetime object. So there we go. And I'm just going to use this one to show you what's all there. And you can see that if I say get, there's a whole list of options. I can get different parts of my local datetime object. I could get the day of the month, the hour, just day of the week, day of the year, all sorts of things I could get the nanos, get the seconds, etc. I would actually have to store these in mostly ints, sometimes in month objects. So I can't start it in the local datetime, so this is only going to give me one piece back. And again, it's not converting, it's just grabbing that element of the local datetime. And then we also have all these minus methods, and you can see I can do minus days, hours, months, minutes, nanos, etc. So instead, right now, I'm going to go minus weeks, and I'll do minus 2 weeks. And I'm using local datetime now, and minus 2 weeks is pretty much just going to subtract 14 days. So let me show you the results of LET4 right here. And you can see in the very bottom that this was Christmas last year, which is exactly 2 weeks ago, so it all matches up. Alright, we've seen the basics of local date, local time, and local date time. But what if you wanted to meet with a friend in another time zone? The local date time would not be specific enough. We would need to add a time zone. This is what we're going to have a look at in the next video, zoned date times. If you need to pick a universal moment rather than a time, you have to go with zoned date time. The zoned date time is a class in the Java Date and Time API that represents a date and a time with a time zone. It is also part of the Java time package, like the others. Let's move over to IntelliJ and see various ways of creating a zoned date time. So I'm going to create a class for it, and what you may have noticed is that I prefixed them all with example. And well, I could have gone for more creative things, of course, but what's important for you is that you need to be careful that you don't use the exact name that Java does for your class, because then things can get tricky. Java might think that you're actually trying to create an instance of your own class and you complain to me, hey, these methods are not available for me, but you're looking at your own class. So always make sure to call your own classes not the exact same thing as the Java ones. Alright, back to what I was actually doing, and that's creating some zoned date times. Of course, we can create one using the zoned datetime now method. So I'm going to go ahead and say zoned datetime now. And this way, I'm creating a zoned datetime with the very instance of right now. And then it might not surprise you, but we could also use the off method. But this is where things are somewhat different though. Because for the off, well, I have a bunch of options. I can specify local datetime, or a local date, a local time, etc. But what I would need to add in all of these cases is the actual zone ID that I'm using right here. So let's go ahead and specify the local datetime of now here as an input. Let's say local datetime now. Then the next argument would be the zone ID. And there's actually different ways of grabbing a zone ID. And I'm going to go ahead and I'll just use Europe, Paris for this. And of course, we also need to import zone ID. So that's why it's showing up in red right now. And of course, we could also parse them, but I'll show that later. If you want to see which zone IDs are available, you can actually ask Java, and here's how to do that. I'm just going to use the for each loop, and I'm going to say print every string zone ID that we're having on my system. Get available zone IDs, there we go. And I'll print them here. So I'll run this code and we'll see all the zone IDs. And please mind you, there are a lot of them. You can see them right here, and you can see on the scroll bar on the very right that this is a long, long list. So if you which zone ID to use, you can also look them up in this very list. Alright, so that's how to get all the zone IDs. And of course, there's also methods on the zone datetime object. You can use these built-in methods to do all sorts of things with zone datetimes. I just want to demonstrate a few that we're having. So, just like for the others, we can use the gets to get a part of the zone datetime. Well, since the zone datetime has a lot of parts, there's a lot of gets. We can get the zone, the hour, day of the month, week, year, etc. We can also use the minus method, and of course this will not alter the original zone datetime, but it will just create a new one with the updated zone datetime in there. And we can also do something very similar for plus, and this will not alter the original object. There are two that I would like to say something about. And the first is this one. So I'm going to create a new zoned datetime, ZDT3, using ZDT1. And I'm going to use the with zone same instant. And what this method is going to do is going to return a new zone datetime object with the same date and same time as my ZDT1, but with a new time zone. So I can specify a new time zone here. So, and I remember seeing Egypt as a time zone, so I'd go ahead, set zone ID of, and then specify Egypt like this. And then I can go ahead and print result right here. And as you can see, we get the updated time, but now for Egypt time, which is a little bit ahead of me. At this point, it will probably not surprise you that there are more of them, but we've seen enough methods for now. In the next video, we're going to have a look at duration and period. This will help us to express amounts of time in Java. When we want to express an amount of time, we can use the duration and period classes. Duration and period are classes in the Java Date and Time API that represent a length of time. Duration is typically used for amounts of time less than a day. It represents time in seconds and nanoseconds, while period is for more than a day and represents a length of time in years, months, and days. Let's have a look at how to work with the duration class in IntelliJ. Let's start off with creating a duration object in a few ways. So for example, we could create a duration called d1 with the of nanos method. And then in there, we need to insert a long of nanos that we want the duration to be. So for example, this one. We could also create a duration of seconds. Like this. And as a second argument, we could possibly also add the nanos that we want to be added to our duration. There's actually quite some other ways to create duration. I'm just going to show them to you because this might get a bit boring. So I'm going to say durations of, and as you can see, we can go for days, hours, millis, and minutes. So if you want to create a duration of a week, we could go ahead and say duration of days and then specify 7 days, which would equal a week. All right. Let's now see how to work with periods. It's actually quite similar. We can go ahead and create a period by using the of methods. So we can start with of, and then we can specify years, months, and days that it should take. So for example, like I said, it should be 10 years, 2 months, and 3 days, like this. But I also have a bunch of other options. So I could go ahead and say period, and I'm just not going to do it all again. I'm just going to show you the options we're having. So we could go of days, of months, of weeks, and of years. So there's quite some ways to create a period object. And we can then specify the number, and using the method, we will know which amount of periods we would be creating. So for example, if we would create periods of 12 weeks, I will go ahead and say of weeks and specify the number 12. Once you have a duration or period object, you can use a whole bunch of methods to access and modify the length of time. For example, we could create a new duration, d4, using our d3 object. So as you can see, we can go make it a negative amount of time, we can divide it by something, we can do minus, and then you have a whole bunch of options. Minus another duration, but also minus days, hours, millis, minutes, and more. And as you can imagine, we can also do plus whole sorts of things. So plus another duration, but also plus days, hours, millis, etc. So let's just add this other duration to it. And it's good to mind that this is not going to change the original duration. So D3 is not going to be altered, but this is going to return a new duration with the added amount to it. And likewise, we can do something similar with periods. So we can go ahead and say period, and then we can add something to it we can get a certain unit out of it. We could also get the specific unit, so either the days or the months. And please mind, this is not converting it. This is just going to give you the day part. So for example, if we grab the days of the first one, and I'm just going to print the output so you can see it. And what you might expect at this point is that it's going to convert the 10 years, 2 months and 3 days to a total number of days, but that's not what it's doing. So I'm going to run this and you're going to see that this is just going to print the day part. It's going to print 3 on our screen. And that is because our day part of the period P1 is 3. It has 10 years, 2 months and 3 days. So you may wonder, then what about the weeks? Well, weeks consist of 7 days. So if I'm going to do P2 and then get weeks, it's going to be 7 times 12, and that's going to be equal to 84, as you can see in the output. So the day part here equals 84, the year part and the month part are 0. And of course, you can also do all other sorts of, you can do plus, and you can also go ahead and go minus. You can even do some divisions and some multiplications. But there's actually more to calculating with dates and times. So duration and period are just about specifying a certain amount of time, but we can actually do more when we're going to be calculating with dates and times, and that's something that we'll see in the next video, and we are going to use duration and period for that. We can use duration and period for calculations with dates and times, as we've already seen in the previous video. You can also use 2 local dates and calculate the period in between them. Here's how to do that. We would first grab a start date and an end date. In this case, I'm grabbing the local date now, and I'm going to grab just a date in the past, 2015, 4th month, 15th day. And then I'm going to create a period. I'm going to create it with the period dot between. And we're going to specify start date and end date. And that's going to give you the period between these 2 days. You can use the plus duration and minus duration methods of local date time to add or subtract a duration from a date and time. And you can use the plus period and minus period methods of local date to add or subtract a period from a date. Let's explore this in IntelliJ. Here's an example of how you might use duration and period to calculate with dates and times. I'm going to create a local date time, and I'm going to call it now. And as you may guess, I'm going to create it with local date time.now. It's going to grab the current local date and time. And then I'm going to calculate the local date time 1 hour from now. And I'm going to use our now and go ahead, say plus, and then say duration of hours 1. And what this will do, this will return a new local date time 1 hour further than now is. So literally 1 hour from now. And as you can guess, I can also use of days and then plus 7 to go a week from now. But first, let me show you that this actually works. I'm going to show you now. And then I'm going to show you 1 hour from now. Let me run this and show you how this is working. And as you can see, 1 hour from now is 1 hour later. So great, this works. I want to show you something else. I want to show you that we can do also something with local date. So I'm just going to call this today. And I'm going to create this with local date.now. And then I'm going to create a new local date 1 year ago. And I'm going to use today and go ahead and subtract 1 year from this. So this is one way to do it. I'm going to create another local date 1 year ago, 2. And I'm going to say today minus. And then in this example, I'm going to use a period of years, 1 year. So as you can see, there's multiple ways to go ahead and calculate with dates and times. Just to prove you that this works, I'm going to print both. So I'm going to print today plus 1 year ago. And I'm going to do this again, but then with 1 year ago too. And let me run this for you, so you can see that this is the same result. And as you can see, both of them print the same result. So it's important to note that calculating with dates and times can be done in different ways to get the correct and same result. There's just a bunch of convenience methods for you that make it easier to write and also read your code. And it's definitely convenient. Calculating with dates is a lot nicer since Java 8. Before we used different classes that were a lot more complicated to work with. You can recognize these new date and times by that they're part of the Java time package. Let's see how we can modify the string representation of our dates in the next video. So far, we've seen one way of printing dates, but we actually have a lot more influence on their format, and we can also parse dates. Formatting a date means converting a date object to a string representation, while parsing a date means the opposite, converting a string representation to a date object. The Java Date and Time API provides several classes for formatting and parsing dates. We'll be using the datetime formatter and the datetime formatter builder. The datetime formatter allows you to specify a custom pattern for formatting and parsing dates and times. The datetime formatter builder allows you to build a datetime formatter object using a Fluent API. We'll be using the Java time format package for this. So let's move over to IntelliJ and see how you might use the datetime formatter to format and parse a date. As you can see, I have two dates. One is a local date time called now, and the other one is a local date. I'm going to format the dates with a custom pattern. And here's how I'm going to do this. I'm going to say datetime formatter and import it from the Java time format package. Call GTF. Then I'm going to say datetime formatter and I'll go off pattern. And then I can specify the pattern. And this pattern is something that you need to know. You can find this in the Java documentation actually. I'll show you that in a second. But for now, trust me when I say that uppercase M means month, lowercase d means date, and lowercase y means year. So to write it like this, I can go ahead and format my date like this. So I'm going to print the result, and I'm going to say dtf.format, and I'm going to specify my now in there. And I'm going to do something similar. I'm going to say dtf format, and then I'm going to specify my today in there. All right, let's run this. And as you can see, both dates are now specified the way I told it to. First one is using 2 digits, second one is using 2 digits, and the last one is using 4 digits. So what happens if I add more months? Well, it's actually going to create a word, or in this case, a short one. So let me just update this a little bit so you can see what is happening when I do this, and I will run this again. And as you can see, I mean, this is a very ugly format. Let's not deny that. But as you can see, it's now using the short word for the month. So instead of having 01, it's now having Jan. And then the date is 29. That remains unchanged. But I removed 2 Y's to represent the year. So now I only get 23 instead of 2023. All right, so maybe you want to get the full month. You would add yet another one in there. And maybe you also want to get a date. And if you don't want to get the leading 0, you're only going to insert 1D. In my case, it will still show 29. And as you can see now, it says January 29, 23. All right, so that's roughly how to do that. Let me now show you where you can find all the letters that you can use. And here you can see all the letters that you can use. So, for example, I can tell that the lowercase h would be hour, and lowercase m would be minute, lowercase s would be seconds in a minute, and then uppercase s would be milliseconds, etc. So there's a bunch of numbers you can use. And knowing where to find this will make sure that you can create your custom datetime format patterns. So what's even cooler is that we can actually also convert a certain string back to a date. So let's use the pattern that I've just shown you with the month fully written out, then the day and then the year. Okay, so what I could do, I could actually go ahead and parse a string like that and convert it back to a date. So let's go ahead and create a local date called LD. And then I'm not going to say local date of here, but instead I'm going to say local date parse. And in here, I can then specify the sequence that I want to parse, and optional as the second argument, the datetime formatter that applies. So what I'm going to use here is the one that I just specified. So it's a very weird and ugly one to actually prove you that this works. So I'm just going to say 20 of, well, let's go with 21 as the year. But in order for this to work, I will have to add the datetime formatter. Otherwise, it cannot make sense of a weird string like this. But since we have a formatter in place, this should be no problem. All right, let's go ahead and print this. And as you'll see, it is not using our new format. It's just using the default format here. And as you can see, it created the year 2021, second month, and then February the 20th. So the last one is 20. Yours might look different. It depends on your system. We have seen now that we can use the formatter and then the format method on it and then the date to get the string representation. Well, we can also go ahead and grab the dates and use the format method and then specify the input formatter to get that actual result in that string format back. So this time I'm going to use one of the built-in ones. So in this case, I'm going to go with ISO and then let's go with something special. Week date. All right. And now I'm going to run it and you will see the results. It is going to be printing 2021 week 07 6. So that means it's the 7th week of the year and then the 6th day of that week. All right, one last thing, and that's the datetime formatter builder class. This class can be actually used to create the datetime formatters. And it is actually quite a nice way of creating a formatter. So, for example, if I want to go ahead and create a datetime formatter builder like this, DTFB, I would go ahead and just create a new instance of this one. And then I can go ahead and create a new datetime formatter using my builder. For example, I could start with a literal. I can go ahead and say append literal, and then I could do something like this. The date is. And then in here, I can go ahead and chain all the options I'm having for my formatter. So I could, for example, say append value, and then do something like this, chrono field, and then, well, let's go with the day of the month. And then after that, we can go ahead and specify something like append value and use the actual month. There we go. And now I actually have some red squigglies because I have a datetime formatter already. So I'm going to make this 1. And as you can see, after that, you get a whole lot of red squigglies. And that's because I'm forgetting one very important method here. And that's that I need to convert my builder object to the formatter. And I do this with the toFormatter methods. All right. Let's now go ahead and use this datetime formatter. And you can see I can use it exactly like the other one that I've been using already. So we're going to grab our local date that I created. And I'm going to say format, and I'm going to do so with DTF1. And then you will see the result. And now it's going to say the date is 22. And that might look weird because it says 202 actually. And that's because I did not specify anything in the middle. So I just said append to value, append to value. So if I want to get something nice in there, I could, for example, do something like append literal and then just put a slash in there. And this would actually give me somewhat nicer look and feel saying 20/2. So that is how we can use the datetime formatter builder. And this can actually be nice to create longer types of datetime formatter with actually some sentences in there, because it's quite easy to make a hiccup, and this is breaking it down in rather nice parts. Also, not having to use the m's, the uppercase m's, lowercase m's, etc. makes it less prone to errors. So these are the basics of parsing and formatting dates, and you can do quite complex things. But it's typically just a combination of the basics that we've just shown. You'll come across these when working with dates and times in the wild. The next topic is very exciting. We're going to be talking about OOP, but you should probably take some time to work with dates and times first. Okay, before I'm going to start, I'm going to do my best to contain myself here, because I'm so excited for this part. Teaching OOP, object-oriented programming, is my favorite. Let's start with introducing the concept of OOP and its four main pillars: abstraction, inheritance, encapsulation, and polymorphism. After this video, I'll zoom in on each pillar in an individual video. But first, in general, OOP, object-oriented programming, is a programming paradigm that is based on the concept of objects. An object can contain data and code that manipulates the data. We've seen objects already, so that's not new for us. And we practice with OOP when we were making connections between objects and talking about objects containing objects. This is key in object-oriented thinking. So, for example, we could have a cat object which has an owner, which has a car, which has an engine. OOP is designed to model real-world objects and their interactions, making it a powerful tool for building complex and modular software systems. Something that resembles an object in real life, such as a user, can be defined with a class in Java. The class is the blueprint for the object. An object is a collection of properties with a value and methods. In this case, you can see that the general properties, email and username, etc., they're actually having a value for the user object that you can see right here. And also it can contain methods, such as sign up and login. And yes, I just called myself an object, but I'll only agree with calling myself this in the OOP context. Let's see another non-code example. Let's talk about furniture. Tables, to be more precise. So, when in real life we think about a real thing, such as a table, we can recognize a table very easily, whether it's a side table, a desk, a makeup table, dinner table, etc. And that is because table has a certain set of properties that we recognize when looking at objects. It has a tabletop, this has a certain surface, it has a certain shape, it has a number of table legs, it has a color, etc. So when we have a table object, an instance of the table class, these fields are set. For example, this one has a color table black, the tabletop shape is rectangle, the surface of the tabletop could be 2 square meters, and the number of legs could be 4. A table is very concrete, but also more abstract things make sense as objects in our day-to-day lives. For example, mail. Mail has a sender, a receiver, a topic, a date, and content, amongst others. In coding, this is not a lot different. When properties together are one object, it should be an object. But object-oriented programming goes a bit further than this. And just like real life, we can group certain objects and call objects by multiple names. This is where the 4 main pillars of OOP come in: inheritance, encapsulation, abstraction, and polymorphism. In the next few videos, we're going to see all of them. First up is inheritance. In this video, we'll be focusing on the first and probably the most famous pillar of OOP, inheritance. Inheritance is the ability of a class to inherit properties and methods from a parent class. This allows you to create a hierarchy of classes, where child classes can inherit and extend the functionality of their parent classes. Let's say we have a cat and a dog class. Both these classes have a lot in common. They would both have properties for name, age, color, weight, breed. And they probably have some common methods, such as eat, breathe, play, etc. Without inheritance, we would have a lot of duplicate code. Why is that? Well, because the dog class and the cat class have a lot in common. They would contain the same code. And if we would add other classes that also share things for dogs and cats, such as horses, cows, and probably others, we would get even more duplicate code. I'm actually not sure if cows play, but they probably do. Anyways, you can probably sense that the solution to this duplicate code is going to be presented soon. And you're right, we can solve this using inheritance. This requires us to come up with a category that all these classes would fit in. And there is a rather obvious one: animals. Using inheritance allows us to inherit the properties and methods from another class. So we can create an animal class and give it all the properties and methods that are shared amongst animals. This saves a lot of duplicate code. Instead of adding all the properties and methods to each of the classes, we just define the animal class and say that the others inherit from animal. In Java, we specify inheritance with the extends keyword. When we create a class, we can specify one class that it inherits from. For example, we can say public class dog extends animal. Let's move over to IntelliJ and see what this would look like in Java. I'm not going to add all the mentioned properties and methods for the sake of keeping this example short and easy to read. But I am going to give animal a name and an age and a method eat. Alright, so how do we make our dog class and our cat class inherit? Well, that's easy. We simply add the extends here. So I say dog extends animal, and I'll say cat extends animal. Okay, I'm going to create a separate class in which I'm going to add the main method, and I'm just going to call this class app. And I'm going to give it a method main. And in this method, I'm going to create a dog. And I'm going to create a cat. And as you can see, both dog has a field age, name, and a method eat. So I can call the method eat here. And cat also has a name, an age, and a method eat, which I'm also going to be calling. So if I run this, it's going to print animal eating twice. Why is that? Well, in this example, the cat class is a child class of the animal class, and it inherits all of the fields and methods of the animal class. It is important to note that inheritance is about the is-a relationship. A cat is an animal, a dog is an animal, horse is an animal, and a cow is an animal. Object composition, that we have seen already, is about the has-a relationship. For example, a dog has an owner. And since there is an is-a relationship between cow and animal, we can just as easily add a cow class. And make it extend animal too. This is the key to inheritance. Properties and methods are inherited by the child class, and this saves duplicate code. Also, if we need to add a certain property for all animals later, for example, something silly like number of eyes, I'm going to go ahead and say public int number of eyes. I can just go ahead and add this to the animal class only, instead of having to add it to all the individual classes. Maintenance and updates become less troublesome when inheritance is used well. So inheritance allows us to categorize objects, and this avoids duplicate code. It actually has some more benefits that we'll see later. But this is it for inheritance for now. In the next video, we're going to be exploring the second pillar of OOP, encapsulation. In this video, we'll be focusing on the second pillar of OOP, encapsulation. Encapsulation is the concept of bundling data and methods that operate on the data within a single unit or object. This helps to hide the implementation details of a class from other objects. And this makes the code more modular and easier to maintain, which is great. We have seen the access modifiers, and we can use access modifiers like public, private, and protected to control the visibility of fields and methods in a class. And these are exactly what we need to achieve encapsulation. A very common approach is having private properties combined with public getters and setters. Let's have a look at our animal class again. In this example, the name and age field are public. This is against the principles of encapsulation. It can be edited from everywhere outside of this class. So instead, I'm going to make these fields private. And this means, now they're private, that they can only be accessed within the animal class. To access these fields from outside the class, I'm going to create getter and setter methods. Well, let's say I'm going to make IntelliJ create them for me. So I'll go to generate, and I hit getter and setter, I select them all, there we go. So having these getters and setters method allows us to safely read and modify the values of the fields. The class itself is in control of this. As you can see, the getter method, for example the getName on line 8 to 10, returns a string because the name is of type string, and it's called getName. This is a convention. It's get plus the name of the property. Then we also have a setter. The setter does not return anything, and it's called setName, which is set plus the name of the property. It does take a parameter, string name. And this parameter is used to set the field of the class. So it becomes this.name equals name. This refers to the very instance we're on. So this means the instance's property, which is defined on line 4, name, is going to be equal to the parameter name. A common question I get a lot at this point would be something like, but Maaike, this is exactly what we had. We can still access and modify the properties from outside, but now we just need to use the getter and setter to do so. And if that was your question, well, great job, because you get it really well. Let me answer it. Encapsulation is an important aspect of OOP because it allows you to create well-defined, self-contained objects that can be easily reused and maintained. Objects cannot be modified in unexpected places as a result. If you want to prevent fields from being set again, you just do not create the setter afterwards. You only allow the getter. And also, it's possible to provide certain checks before setting a value. So let's refactor our age to be of type int instead of type string. I'm going to right click and say refactor. And then I'm actually going to say here not rename, but I'm going to say type migration. And I'm going to migrate it from string to an int. And I'm going to do so in all places. Alright, and what I can do now is I can say I'm only going to set it to age if the provided age, so the parameter age, is bigger than 0. Because I don't want the age to be set to -1 or lower, because that would not be a valid age. So let's move this up. And right now I've built in some validation. This was also not possible when we just had a public field. Alright, so encapsulation is all about having private properties and public getters and setters. In the next video, we'll be exploring the third pillar of OOP, abstraction. In this video, we'll be focusing on the third pillar of OOP, abstraction. Don't worry, it's not as vague as it sounds. Unfortunately, it's not as artistic as it might sound either. Abstraction is the pillar in OOP that allows for the simplification of complex systems by focusing on the essential features and hiding away the unnecessary details. Well, that might sound very abstract. In Java we get there by using abstract classes and interfaces. This makes our programs maintainable and easier to understand, once you understand abstract classes and interfaces, that is. Okay, I get it. Chances are that I'm leaving you a little puzzled right now. Let's talk about a non-code example. My car. I can steer my car, or at least sort of, definitely not an expert here. You should only see the rims on my car, but that's beside the point. The point is, when I steer my car, I honestly have very little clue of what is happening with all the parts I can't see. But somehow my wheels go into the direction I'm steering. I don't need to know how it's working, and that's an example of abstraction. I know how to use it, but I don't need to know how it works. Yet, I can still use it. At least, sort of. Alright, I know this is a bit abstract still, but knowing that abstraction allows for being able to use it without having to know the exact implementation, that's enough on abstraction for now. In the next video, we're going to have a look at the fourth pillar of OOP, polymorphism, which is Greek for many shapes. Alright, let's talk about the last OOP pillar, polymorphism. And don't worry, it sounds more intimidating than it actually is. It's a Greek word, or two for that matter, poly and morph, meaning many and shape or form. And that's exactly what it is about. One class can have many shapes. For example, the dog class. I have an instance of the dog class at home. His very original name is Bobby. I can refer to this instance of the dog class in multiple ways when I talk about him. I can call him dog. I can call him canine. And I can call him animal. And this all makes some sort of sense because a dog is a canine, and a dog is an animal. So sure, polymorphism is the ability of a class to take on multiple forms. But how does this work and why is it relevant? First of all, polymorphism can be achieved through inheritance, where a child class inherits the properties and methods of its parent class. Or through something we'll see later, namely interfaces. This all establishes an is-a relationship between classes. Let's go back to our example. We have a parent class animal with an eat method and a few child classes, amongst which cat and dog. Let's create another method eat in both the dog and cat class. So in here, I'm going to say public void eats, and I'm going to say dog is eating. I'm going to do something similar for cats, but you may guess this, I'm going to say cat is eating here. So I'm going to go back right there. What I just did is something called overriding. We'll see this in more detail soon. But both my classes dog and cat now override the behavior of eat. And overriding allows us to create different behaviors for the different subtypes of animals. So let's run this and you will see the more specific method being executed. So is there polymorphism happening here? No, not yet. But if I change this type to animal, now there is. Because what I just did is that I'm referring to my dog with the type of animal. So it's a bit like saying I'm bringing my animal instead of saying I'm bringing my dog. Of course, saying that you bring your dog is more specific, and when you know that you're going to bring your dog, that actually makes more sense than saying I'm bringing my animal. But imagine that this was a sort of crate with a type of animal in it, and I would not know what would be exactly in there. I could have any instance of animal be in a crate and it would work. So this is polymorphism, but if I would give dog a specific method, for example, bark, right now, I can no longer call this on dog. Why not? Well, I only have the methods from animal available. Why is that? Well, because IntelliJ right now doesn't know that my animal is a dog. It knows it's an animal. An animal does not have the method bark. It only has the getters and setters, and it has the method eat. So in order for the dog method to be available, I either must create the instance as dog like this, and then right now I can go ahead and have my dog bark. But if I would change this type to animal, you'll see that it's no longer recognized. It now turns red. Why? Well, there is no bark in animal. What we could do though is we could cast dog to animal. It would look like this. So I need to actually put brackets around this, otherwise it's going to try to cast the void of bark to animal and it can't. And right now I can do this again. But if there's no dog inside this object, this would give a class cast exception. What I can do is I can cast this dog to an actual dog and not to a type of animal. So I would do this like this. I need the extra brackets. Otherwise I'm going to try to cast the result of the bark, which is a void, to dog, and that's not possible. But since it sees that dog is an animal, this is possible. And right now it will actually work if I run this. It's going to show woof woof. Oh, and the eating, of course. But let's say that at some point somewhere else in the code, something happens to the dog and it gets overwritten by, well, let's say a new cat. And remember, this is allowed. It's very ugly code, but it is allowed. And it is allowed because dog is of type animal, as you can see on line 5. And cat extends animal, so cat is an animal. So in this dog variable, I can actually store a new cat. So this line will go wrong because it's not going to be able to cast my cat to a dog. And what happens then is that we get a class cast exception. OOP cat cannot be cast to class OOP dog. So let's compare it to what I just did. So if I would tell I bring my animal, people won't be able to think of the dog specific methods. They can only think of animal specific methods. So animal will probably eat, for example. The people listening would not know that I'm talking about a dog. They might even think I'm talking about my pet tarantula. Well, they would only think this if they wouldn't know me that well. We can use polymorphism to create code that can deal with all the subtypes of a certain type. For example, after uploading documents. The documents might all be of type document, but have their own subtype and have different ways of scanning for problems with the files. The name of the method can be the same, but the implementation can differ. Thanks to polymorphism, we can get away with less lines of code when dealing with this problem, and force all classes of type documents to have a scan content method. Alright, that's enough on polymorphism. It means that we can refer to a class with all its parent classes as well. Let's talk about overriding, overloading, and hiding in more detail in the next video. Alright, buckle up. In this video, we'll be discussing some advanced concepts related to inheritance and polymorphism, overriding, overloading, and hiding. And before we do so, we need to make sure that we understand what method signature is. The method signature is the name of the method and the parameter list. The names of the parameters in the parameter can differ, and it's still the same signature. But their types cannot differ. I mean, they can, but it's no longer the same signature. It's a new method signature now. Overriding is the process of providing a new implementation for a method that is inherited from a parent class. We have seen this with the eat method. The child classes dog and cat made a more specific implementation for their case, And when the method would be called on an object of type cat, the id of cat would be used instead of the one in animal. In Java, you can use the @override annotation to indicate that you are overriding a method, like this. And if you paid close attention, you could already see that we were overriding. You see, next to the 5 here, there's this O with the arrow that's pointing up, and that's indicating that it overrides a method. And it actually specifies it when you hover over it. It says overrides method in animal. If I click it, I'm taking to the method that it overrides. And you can see here that it's being overridden because it has the O next to it and the arrow pointing down. The annotation is making sure that I'm overriding a method here. Whenever someone would try to go ahead and alter the method signature, for example, by adding a parameter, it will no longer compile, because the annotation will lead to a compile error. It will simply notice that I'm no longer overriding, whereas I say that I am. And this is a problem. So this is why it no longer compiles. It says method does not override method from its superclass. Without the annotation, we were also overriding, but we would no longer be warned whenever someone comes by and changes their signature to a different parameter list, for example. Therefore, it's good to always add the annotation override when you're overriding. So, long story short, overriding is when you have the same method signature in the child class as you have in the parent class. Let's talk about overloading. Overloading is the process of providing multiple methods with the same name, but different signatures due to a different parameter list. And this can be done within the same class or between child classes and parent classes. It allows you to create multiple versions of a method that can be called depending on the number or type of arguments passed to it. For example, we could make another eat method. I could make an eat method that's going to take a string as an argument, like I already did just now. And then in here, I can go ahead and say dog is eating, and then specify the food the dog is eating. Right now, this method is overloaded. And I can call both methods, but it chooses which one to pick based on the arguments I'm providing. So right now, when I'm going to change my dog back to dog, remove the dog as new cat because that was silly anyways. Right now when I say dog.eat no arguments, it's going to print dog is eating, but when I do provide an argument, it's going to use my newly made method. Let's say it's going to be eating meat. So right now when I run this, you'll see that both implementations are being called. First time dog is eating, second time dog is eating meat. And lastly, we need to understand hiding. Hiding is the process of hiding a static member of a parent class with a static member of the same name in the child class. Both properties and methods can be hidden. This hiding can be achieved by declaring a field or method with the same name in the child class and using the static modifier, of course. For example, in IntelliJ, I could give my public class animal a public static string. And then let's just go ahead and give it a type here. And I'm going to say the type is animal. I can go ahead and hide this type in my cat class. I can go ahead and say public static string type equals, of course, it's going to be a cat here. And of course, you need to spell string correctly in order for this to work. And I can go ahead and hide it in dog as well. So I can go ahead and say public static string type and then make it dog over here. And then of course you probably want to see what happens when I go ahead and print them. So I say dog.type and I'm going to say cats.type. Please mind this is static, so it would actually be better to not do it on the instance as I'm doing it right now, but do it on the class like this. And you'll see that's going to print the more specific version because we're hiding one from animal. In a very similar way, we could do this with a static method with the same name and same parameters. Whenever we call these static members, we'll see the version of the specific class we're calling them on. But when we call them from the animal class, we'll just get the version defined in the animal class. So overriding is between parent and child classes, where the same method signature exists in both. Overloading can be between parent and child classes, but can also happen within one class. It's when methods have the same name, but a different parameter list. Depending on with which arguments the method is called, a certain method gets triggered. And lastly, hiding is very much like overriding, same name between child and parent class, but then with these static fields and static methods. Alright, so this is it for the basics of OOP. Make sure to get plenty of practice before we're going to move on with another very fun topic, namely constructors. When we create objects, we use the constructor to do so. We've actually seen them already, at least sort of. When we were creating new objects, we did it, for example, like this. %p equals new person. Here are we actually calling the constructor of the person class. A constructor is some sort of special method in Java that is used to create an object of a class. It has the same name as the class and it's used to initialize the instance variables of the object. Here's how to recognize a constructor. As I said, it has the name of the class. And it starts with a capital, because it has the name of the class and that one should start with a capital as opposed to methods. Also, a constructor has no return type. If it has a return type, it's not a constructor. It's a method. It's a normal method with a very poorly chosen name. Please do not do this. Here's an example of a class with a constructor. You can see it on line 7. It has the same name as the class, student. And as you can see, it has no return type, but opposed to the other constructor, this one takes 2 arguments, one name and one age. And it's using these arguments to set the fields of the class. To create an object of the student class, we can use the following syntax. Student S1 equals new student, and then, for example, John and 20. The new keyword is used to create a new object. And the constructor is called to initialize the object's instance variables. As I already mentioned, something is new here compared to how we used to do it. We are sending in arguments. We only have used constructors without arguments so far. At this point, you might think back to when we were creating classes and don't remember seeing any constructors. And you'd be right. We have been using the default constructor that gets added by Java so far. Except for this one time right now where I was creating the student constructor, of course. Let's explore the default constructor in more detail in the next video. All Java classes have a constructor. If you don't create one, Java adds one for you, and this is called the default constructor. The default constructor is a constructor that takes no arguments. If a class does not have any constructors defined, the Java compiler automatically creates a default constructor for the class. Here's an example of what the default constructor would look like for a class student. But if you create the class looking like this, it is not the default constructor. This is because you added the constructor. The default constructor only gets added if you didn't add a constructor yourself, like this. Now let me show you what's happening in IntelliJ. So let's say our student class does not have a constructor at all. Right now, there's no constructor in here, as you can see, just a name and an age and the getters and setters. So I'm going to create a quick program creating a new student. And I'm going to run this. nothing happened. Well, that's not the point. I want to show you something, and I want to show you what has been created. I'm going to open up the target folder. This is where all the class files are at, and if I'm going to be opening up the student, it's actually giving me a warning because this is the first time on this computer that I'm doing this, and it looks very interesting, but I can just accept it. It's not too important. You can see here the decompiled class file. And as you can see, on line 12 and 13, there's this magic constructor that was added. This is the default constructor. Alright, so the default constructor is the one that gets added when you didn't create a constructor. Let's see how you can add your own custom constructors in the next video. When we create our own constructor in a class, this can be considered a custom constructor. I just mean constructors other than the default constructor here. A custom constructor typically is a constructor that takes one or more arguments. Here's an example of a class with a custom constructor. It might look familiar. You can see the custom constructor public student here, and it's taking two parameters, a name and an age, and these are used to set the properties of the instance. To create an object of the student class using the custom constructor, we can use the following syntax. Student s1 equals new student John 20. The John argument gets passed to the parameter name, and 20 gets passed to the parameter age. This might be weird if you're a 20-year-old John watching this. I can guarantee you this is 100% coincidence and no funny AI stuff at all. Classes can actually have more than one constructor, as long as they have a different signature. And a different signature means different parameters when we talk about constructors. So let's say that our student class also has a student number. We could then have an extra constructor that also sets the student number. Let me show this to you in IntelliJ. It gets too big to go on this slide. Alright, so I'm going to be starting by adding a student number here. And it's going to be of type string. And maybe we don't always need to initialize the student number when we create an instance of student. And that's why we also want to have the option to have the constructor with only the name and the age. So I'm going to be adding a constructor here, say public student, string name, int age, and then say string student number. And in the body of the constructor, I'm going to say this name equals name, this age equals age, and I'm going to say this dot student number equals student number. There we go. So as you can see, classes can have multiple constructors. And remember, when a class has a custom constructor, the default constructor won't be added. So if I'm going to run this app again, and then inspect the decompiled class, you can see that we no longer have the default constructor in here. Why not? Well, we have two custom constructors. It no longer creates the default noargs constructor. Let's explore two important ways of calling constructors from constructors in the next video. From within a constructor, we can call other constructors with the this and super calls. In a class hierarchy, the super call will call a constructor in the parent class. In this case, there are no arguments, so it will call the no argument constructor in the parent class. The this will call another constructor in its own class. In this case, the no args constructor in the same class. Both the super and the this call can only be used from within a constructor, and only as the very first call of the constructor, meaning we can never use both of them at the same time in one constructor because only one of them could be the first call. So let's say we have a class person, and we're going to give person a name and getters and setters for this name. and actually a constructor that's going to be using this name as an input. And I'm also going to be adding a default constructor. Alright, so simple class person has a property name, has two constructors and a getter and setter for name. As you can guess, our student is going to extend person. And I'm going to remove name from here. Also remove the getters and setters, of course. And instead of saying name, that's no longer possible, I'm going to be calling the super constructor name. So I'm going to say super, and then I'm going to send the name that was passed in as an argument to student to the constructor of person. And I'm going to do the same thing right there. So what I'm going to do now is that I'm going to run this in debug mode. So I'm actually creating a new student with name and age. And I'm going to run this in debug mode. So instead of the play icon, I'm going to click on the bug icon. Might be even safer to click it here so you know you're really starting the right application. There we go. And it's now going to pause as soon as the execution hits the student line. And well, that's actually pretty much the first line, so it stops right away. And then you see a bunch of buttons right here. This means step over, and I would go to the next line inside my main method, which there is not. This one is the one I'm looking for, step into. And this way it's actually going to jump to other classes and showing the code that's going to be executed right there. So I'm going to click. And as you can see, it brings me to the student constructor with two arguments. And as you can see, it's going to call super with name. So I'm going to hit step into again. And that takes me to the person constructor name. And actually in this case, that shows me something I forgot. Namely adding some code right there, because I would definitely want to go ahead and say this name equals name, like this. And then I'm just going to step over the code. This time it actually skipped the line I just added because it was already compiled previously. But the next time I'll run it, it would set it. Anyways, there is no output, so it doesn't make a difference right now. My main point is that you can actually see it jumping from the child class to the parent class when you run this. Let me show you how we can use the this constructor. So instead of here going to be calling the super name, I'm actually going to be calling the own constructor in the same class. So here I'm going to say this, and I'm going to send the name along. I'm going to specify the age argument along, and then in here I'm just going to specify a default student number 0. And right now, if I'm going to step into debug mode, it's going to do a few more steps. So let me show you. Again, I'm going to start the app in debug mode. So watch what happens. I'm here calling the student constructor with two arguments. Sure, I'll step into. And here it's calling the student constructor with 3 arguments. So if I say step into, you can see it actually jumps to the other constructor, which is calling the parent constructor. So if I hit step into, it takes me to the person class. Then it's actually going to set the name. And then right now it's going to jump back to the constructor with 3 arguments. It's going to set the age and the student number. And then next step, it's back at the end to the 2 argument constructor. Now it jumps back to my main method. And then it's done. As you can see, the arguments go between the parentheses after this or super. If a constructor doesn't take any arguments, there are just 2 parentheses there. So we can use this to call another constructor that's in the same class, and we can use super to call another constructor that's in the parent class. There's actually a little bit more to tell you about super and inheritance, and we'll do so in the next video. I promise there are some fun and important things to know about constructors and inheritance. Or maybe I only said important, but it's definitely fun as well. Since super is a way to call a constructor from the parent from within the child constructor, you may have guessed it's related to that. Let me show you something in IntelliJ. Here's a class vehicle, and here is a child class car. At this moment, they both don't have a constructor, but I'm going to give both of them a constructor. So I'm going to say public vehicle. And in this constructor, I'm actually going to print a line in vehicle constructor. And I'm going to do something similar in car. I'm going to create a car constructor with no arguments. And I'm going to print in constructor car. So now I'm going to move over to app, get rid of the student stuff. And I'm going to be running the following code. Car C equals new car. And as you may expect, this is indeed going to be printing the in constructor car, but there's more. It is printing both lines. You would think, how's that possible? Well, it means that both the car constructor and the vehicle constructor are executed. And as you can see, the vehicle constructor was executed first. Let me show you what is happening by walking through this in debug mode. So I'm going to hit debug. And I'm going to step in 2. And as you can see, I'm first going to go to the car constructor. So you think, but wait a second, I said vehicle first. Well, watch this. I'm going to step into first. Now it's jumping up to the vehicle constructor, printing that line. Then when it's done, moves back to the car constructor, prints that line, and then back to main and done. And that's why it actually prints both of these constructors. This is because the first call in a constructor is always to another constructor. Also, there cannot be a call to another constructor later than the first statement. You might think I'm losing it because you don't see the call to the constructor, and we definitely created constructors like this. Well, guess what? It gets added by Java. Java adds the super when there is no constructor call explicitly. And remember, this can only happen as a first statement. So the first thing a constructor does is actually always call its parent constructor or another constructor in the class. As we could see when we went to the car constructor, it jumped to the vehicle constructor first. But this is also where things can get problematic. Let me show you how we can break the previous example. Let's add a custom constructor to our vehicle. Or actually, let's just modify this one, and that will break it. If I'm going to try and run my application right now, you'll see that it will not compile. Why? Well, there is an implicit call to the super. And this implicit call to super is without arguments, so it's calling a no args constructor that used to be there. But now that we added a custom constructor, there is no args constructor anymore. And as a result, our code is not compiling because we're calling it implicitly from the child class. We have two possible solutions: adding a no args constructor in the parent, vehicle in this case, or calling the custom constructor from the child explicitly. I'm going for that last option right now, so I'm going to say super, and I'm just going to call it car, like this. And right now, our code will compile again, because it's no longer relying on a constructor that is not there. So, to sum up, in inheritance, the constructors of the superclass are not inherited by the subclass. However, we can call the constructors of the superclass from the subclass using these super keywords, as we've seen in the previous video as well. If we don't call a constructor explicitly, Java will add the super at the beginning of the constructor. But this will only work if the parent class has a no args constructor. If that's not the case, you should add one, a no args constructor to the parent, or call the custom constructor from the child's constructor. Alright, that's it for constructors for now. I know it can sound like a lot, but it will very quickly become your second nature. Our next topic is going to be enums, but make sure to get some hands-on practice first. Let's talk about a special subject, enums. With enums, we declare a set of named constants. Enums can be thought of as a special type of class that has a fixed number of instances. A common use case for enums is representing a set of values. For example, the days of the week, months of the year, or a suit in a deck of cards. Something I typically use to simplify this explanation is that it would be something that typically fits a drop-down menu on a website. But please keep in mind, not everything that fits a drop-down menu would be a good enum. They should not be used for a set of values that change a lot, since adding or removing a value from the enum requires a restart of the entire application. They really represent a set of constants. Using enums for the right cases comes with a set of benefits. First of all, they provide type safety, meaning that you can only assign a value to a variable of the enum type that's defined in the enum. Another advantage is that they make the code more readable, as the meaning of the constant is clear from its name. They help to prevent bugs, as the compiler will catch any attempt to use an undefined constant. Another benefit is that they're more memory efficient than creating an instance with the same variables every time. Let's have a look at how to create basic enums in the next video. So great, enums are a way of defining a group of constants. Let's see the more exciting part, how we create them in Java. To declare an enum in Java, use the keyword enum, followed by the name of the enum, then a list of constant values, and closed in curly braces. It's a convention to have all the values of the enum be in uppercase. This is also the case for some other constants amongst other programming languages, so this makes quite some sense. Once you've declared an enum, you can use it to declare variables of the type. The name of the enum is the type, just like for classes. And then you can use one like this. If your name of the enum is days of the week, it goes days of the week today equals days of the week dot Sunday, for example. Unlike classes, you can compare enums using the equality operator, the double equal sign. I'll explain why in a later video, but here's how to compare two values of an enum. We can say if today equals day of week dot Monday, we'll print today is Monday. Otherwise we'll print it's a good day. This hate of Monday reminds me of someone. Enums always have a few methods that are built in for enums. These predefined methods are toString, ordinal, and values. toString returns a string representation of the enum constant. Ordinal returns the position of the enum constant in the enum declaration. Values returns an array of all the enum constants in the enum. Alright, let's summarize this by having a look at all this in IntelliJ. So here's the enum day of week, and as you can see, they're all grayed out because I'm not using it yet. So I'm going to move over to my app.java, and I'm going to be using one. So I'll specify the type day of week, and I'm going to call this day, and then I'm going to say day of week dot Sunday. And I'm going to make another one, day of week, day 2 equals day of week, Friday. And then if I want to know whether these are the same, I can go ahead and say day equals day 2. And then I'll print the same day, if that's true, and else, which is the case for this one, it's going to print not the same day. Alright, let me run this. And as you can see, it prints not the same day for all of them. So what happens if you print the ordinal? Well, it's going to print the numeric value of the enum. So for example, if I go day.ordinal, then it's going to print 6 in this case, because it starts from 0 and the first position was for Monday, that was 0, last one was Sunday, meaning that becomes 6. Alright, so now we know how to create basic enums. Let's see how we can expand these basic enums with fields and methods in the next video. Creating enums for the right use case is a powerful building block in Java. We've already seen how to create enums, but we can do even more with it. In this video, we'll be talking about enums with fields and methods. You can add fields to an enum in Java. Each constant in the enum can have its own set of data. Here's our day of the week enum example. But we've added an extra field to it. As you can see in bold, after every constant we have two parentheses, and between these parentheses we have a string. This means that now our enum has an extra field of type string. There are a few things you should notice for creating an enum with a field. First of all, we need to have this as a field in our class. And the constructor needs to accept this type as input parameter. Before we didn't need to add our own constructor because the default one was good enough. Please mind that this constructor doesn't have an access modifier. You are allowed to add private before it, but it will be private by default and there are no other options. The constructor in an enum is private, period. As you can see, we've also made a getter method for our field to get the full name. Let me show you how we can use this field now. We can access the fields of an enum constant using the dot notation and the getter that we made. So here we're creating a today with the value of Monday, and then we're using this today variable by in the system out print line saying today.getFullName. And our output is of course going to be Monday. We could add more fields and follow the same procedure, add it to all the enums, and add the field to the class and adjust the constructor, like this. So first I'm going to add it to all the enums. So for example, I'm going to give a number to this day, which is one higher than the ordinal. And of course, it's a forever discussion whether Monday should be 1 or 2, and I don't have an opinion, but it's on top in my example, so I'm going to go with 1. There we go. So right now, I'm going to be adding the private final int number of day. And I'm going to be adding this to the constructor. And of course, in the constructor, I'm going to set the value as well. And after this, you can see the red squigglies go away and now it's happy. So I can add an extra field by providing all the parentheses with the extra field. Then I need to add the field to the class and I need to adjust the constructor accordingly. In addition to fields, you can also add methods to an enum, just like we did for the getter method for full name. But other methods are allowed too. Here you see an example of a method that determines whether the day of the week is a weekend day. And it's using the equal comparison for enums as we're used to by now. Alright, so this is how we can give enums more data fields and even custom methods. They provide a lot of benefits over using other data types for constants. If you're curious to find out how this all is working underneath the hood, go check out the next video in which I'll explain how enums work beneath the surface. I love these kind of topics. Let's take a deep dive in Java. We'll be talking about how enums work under the hood. First of all, it's important to know that enums are actually classes in Java, a special kind of class. Let me prove to you in IntelliJ that this is the case. First of all, we can go ahead and give our enum a main method. And then we can even run our enum. Please don't ever do this, but all of this screams class. So I'm actually going to run this and you'll see it's actually going to be a class. Run our enum, there we go. But it's not just a class. As you can see in the decompiled code, it's still specified as enum. It is really a special case. So you may wonder, if enums are some sort of classes, can enums extend other enums or classes? And that's a great question, and let me show you this. The answer is no. If I'm going to say public enum day of the week extends app, it's going to give red squigglies, and these red squigglies will say no extends class allowed for enum. Sure, this is not allowed. Why not, you may wonder? Well, enums, they do inherit from a special enum class already. Enums extends the abstract base class Java lang enum that's built in Java. Amongst other things, that's where they get their ordinal method from. Since Java has a single inheritance principle, they can't inherit from other classes. So you may wonder whether we'd be capable of extending the enum itself in another class. And once again, that's a great question and I love the curiosity, but again, the answer is no. It is a bit confused though. If I move over to app and I'm going to say that it's going to extend the day of the week, it's going to give me a false reason. If I hover over these red squigglies, it say there's no default constructor available in enum's day of week, but that's not a problem. So in order to demonstrate this, I've created another enum which is completely empty and is called example. If I'm going to say extends example, it's going to be more precise. It's going to be less red squigglies and it's just going to say cannot inherit from enum's example. And there's a really good reason for this. This is because the number of instances of an enum is fixed, and inheritance causes an is-a relationship. So with inheritance, we'd be able to create new instances outside of the enum, and that's definitely not what we would want. If Java would allow that, our constant wouldn't be so constant, so that's why you can't extend an enum. Great, so we've learned some extra rules, but what happens when we use an enum? All the constants you define become an instance of this very special class. So each constant in the enum is an instance of that class. Java converts each enum constant into a static final instance of the enum class. Once you use an enum for the first time, all the instances get created. Let me show you this in IntelliJ. So what I did in order to prove this is that I added a system out print line to our constructor in the enum. I'm saying in constructor enum plus the full name of the day of the week. So in app, when I'm going to be using day of week, it's actually going to create all of the instances. And we can see this in the output. Let me run it for you. As you can see, all the instances get created as soon as we use the first one. The Java virtual machine also generates a lot of boilerplate code for each enum that we're not going to be talking about here. Just remember that an enum is a special class and that all instances get created once and then can be used. Alright, that's a brief overview of how enums work beneath the surface in Java. Make sure to get some practice with enums and then you're ready to move on to interfaces and abstract classes. It's time for a new topic, interfaces. This topic can be tough, so don't worry if it feels tough to you. It's perfectly normal. I want to start by introducing you to a problem that we would have without interfaces. Let's say that we have for some reason all these animals inside our application. A fox, a parrot, a rabbit and a ladybug. And we have even more classes. We have the class animal, mammal, bird, insect, fox, rabbit, parrot and ladybug. Let's say the diagram looks somewhat like this. There are 3 layers. Fox inherits from mammal directly. And mammal inherits from animal. So a fox is a mammal and a fox is an animal. Sure, but let's say I'd like to add 2 classes to the diagram, a prey and a predator. Because some animals eat other animals and some animals are vegetarian. So where would I put them? prey and predator. I can't put it right under animal, because then all the animals in the underlying groups would be either prey or predator. I could do something like this, but it is terrible. Think about all the duplicate code and maintenance work you'll have to do. You'll always have to do the work twice. Or we could go ahead and do it one layer higher. Have prey and predator mammals, prey and predator birds, etc. But next to the duplicate code we still have, it leaves us with a problem. Because we have animals who are both, such as the bird eating this worm, while a cat is watching him. So the bird could be prey and predator. So we could create 3 options: prey, predator, and prey-predator. This is all horrible, right? I mean, the cat and the bird definitely think so. So let me tell you the more elegant solution here. You may have guessed it, but interfaces indeed. Interfaces are somewhat like classes, but not really. An interface can be considered a certain contract for behavior. The main thing of interfaces is that we can obligate the class that implements them to implement certain methods. To stick with our example, if one of the classes implements the prey interface, they must implement the run and hide method. When a class implements an interface, we can say there is an is-a relationship between the class and the interface. So in this example, the rabbit is a prey. So is the bird, and therefore the parrot as well. The insects are also preys, and so is the ladybug, because the ladybug is an insect and an insect is a prey. Very much like normal inheritance. But here's the difference. A class can implement more than one interface. So this allows the class to be both prey and predator at the same time. Both directly, such as the fox, which is implementing the predator and prey interface. But also indirectly, such as the ladybug, which is prey via insect and the predator directly. So an interface in Java is pretty much some sort of contract for a class that specifies what methods a class should have. Let's have a look at how to create interfaces in the next video. Let's have a look at how to create interfaces in Java. Interfaces act like a contract for a class. Here's an example of an interface. To create an interface, we use the interface keyword, followed by the name of the interface, in this case my interface. Please mind that names of the interface start with an uppercase letter. The methods in an interface don't have a body. You can see that it ends with a semicolon and that there are no curly braces in place. They only have a signature, which is the method name, return type, and parameters. In fact, we can even leave the word public out, because they're public by default. So, interfaces are created with the interface keyword, and they contain method signatures of abstract methods. Let's have a look in IntelliJ at how we could create the prey and predator interface. Alright, so here I am in IntelliJ. And in order to create an interface, I'm going to right-click on the package that I want to create the interface in. I'm going to say New and then select Java class. In the drop-down, I can select interface in here, and I'm going to call my interface prey. And as you can see, it now made an interface. If you accidentally clicked class, don't worry, you can just type interface and it shows up as interface. You can also see that in the project overview, instead of the blue C, I'm having a green I now. So I can easily see that this is in fact an interface. Okay, let me close this project view, it's only distracting. In my prey method, I'm going to give the method run and hide. Well, technically, these should probably be 2 methods, but but that's a later topic. Alright, so I've given it a method run and hide. I'm also going to be creating a predator. So again, I'm going to go here, interfaces, right click, new Java class. Let me on purpose select the class right now and I can show you how easy it is to fix this. So I'm just going to type interface here. There we go, I fixed it. And then this is going to be catch and eat. Oh, I must specify void, of course, because that's the return type. There we go. So that's how to create interfaces. Use the interface keyword instead of the class and specify the method signatures. I can add public, it will compile, but it's redundant because it's public by default. You cannot see, it also shows up gray. It's not necessary to add this, I'm going to leave it out. A class needs to implement an interface, and that's exactly what we'll be doing in the next video. We know what interfaces are and how to create them, but we don't know how to use them yet. Let's have a look at that in this video. We're going to be implementing interfaces in our classes. When a class implements an interface, it does this using the implements keyword, followed by the name of the interface, in this case, my interface. The class must provide an implementation for all the methods in the interface. If the class does not provide a body for a method in the interface, the class must be declared as abstract, but this is something we'll see in more detail in a later video. Classes can also implement multiple interfaces. Let's move over to IntelliJ and implement some interfaces. So I'm not going to do this for all our classes, because that's going to be very repetitive and boring for you to watch. But let's do it for Fox. Our Fox extends mammal, and after the extends, we can add the implements keyword. And we're going to say implements predator. Right now, you can see a lot of red squiggly lines here, and that's because we're not implementing the method in predator yet. Predator has the method catch and eat. And as you can see, there's one related problem, namely that our Fox class does not implement the catch and eat method yet. Let's change this. By the way, you could also use quick fix for this, but I actually want to show you what I'm doing here. So I'm going to say catch and eat. And then I'm just going to print a lay message saying Fox is catching and eating prey. All right. So I've now successfully implemented this interface. As I mentioned, a class can implement multiple interfaces. You can just comma separate them. So I'm going to add prey. Again, red squigglies. Why? Because I did not implement the run and hide method. Let me show you how to do this with the quick fix right now. So I'm going to hover over this, and then I can say implements methods, select the method, hit OK, and you can see it shows it here. What I did also add is actually the add override, which is good practice because we're overriding the no implementation from the interface. So let me also add this to catch and eat in a bit. So go ahead here and add override. This way, no one can come around and change our catch and eat and then break our code. So we're implementing interfaces with the implements keyword. We then must override all the abstract methods in our interface. Abstract methods are the ones without a body. Interfaces can actually also have methods with bodies. One of the ways to do that is default methods, which is what we're going to be having a look at in the next video. In this video, we'll look at default methods in interfaces. Java 8 introduced the concept of default methods in interfaces. A default method is a method that has a default implementation in the interface. This means that the method does have a body, and instead of the semicolon, it has the curly braces with the implementation in between. Here's the syntax for a default method in an interface. You can see it uses the keyword default to indicate the method will have a body. Without this keyword, the code won't compile. Classes that implement the interface do not need to provide a body for the default method, but they can override it if they choose to do so. This was added so that we can go ahead and add a method to an interface without breaking the code. If we would add a regular interface method, so one without a body, we would need to implement this method in all the classes that implement the interface. And this could be a lot of work. We don't need to do this with the default method, since it has a default implementation already. We only need to override it when we have to. Here's an example of a class that implements an interface with a default method. Here, the class myClass implements the method called myMethod. But it does not provide a body for the default method. There's a body already, so it doesn't need to. However, it's allowed to override it. This works just like another override. We don't use the keyword default in the class that overrides it, but we must use the keyword public, since it's implicitly public in the interface. Let's add a default method eat, prey, to our predator interface in IntelliJ. So I'm going to go ahead and say default. It's not going to return anything. It's called eat, and it's going to be eating something of type prey. So that's going to be the inputs. And then in here, I'm not going to do anything interesting. I'm just going to say eating. And let's specify the class of the prey. So here's how to add a default method. Default methods are methods in an interface with a body. And we can create them by using the keyword default. We can override them in the implementing class if we want to, but we don't need to. Default methods are not the only option we're having for a method with a body in an interface. In the next video, we'll take a closer look at static and private methods in interfaces. As we've just seen, interfaces can have methods with bodies when we use the default keyword. In this video, we'll look at another way to do this, namely with the static and private methods in interfaces. Java 9 introduced the concept of private methods in interfaces. Private methods are normally only accessible in the class. It's similar here. Private methods can only be called within the interface. Here's an example of a private method in an interface. Classes that implement the interface cannot access the private method. This is only accessible from within the class, so only other methods in the class can use this private method. Private methods were added to avoid duplicate code in interfaces and at the same time hide the implementation details from the outside world. Static methods in interfaces are similar to static methods in classes. These methods can be called without creating an instance of the interface. You might think, but wait, I thought we couldn't create instances of the interface, and you're sort of right. We cannot create instances directly. We cannot say new my interface, for example. But when we create an instance of the class that implements the interface, this would be considered an instance of the interface. Here's an example of a static method in an interface. It's called myStaticMethod. Static methods in interfaces can be called using the name of the interface. So for example, myInterface.myStaticMethod. This can also be done in a class that is not implementing the interface. Personally, I don't use this a lot, but I do use Java code that is implemented like this a lot. Understanding what is possible and how it works really helps you eventually for understanding Java and becoming a better Java programmer, even though these techniques might not be the best practice in very many situations. So we have different ways of having interfaces with implemented methods: default, private, and static. In the next video, we'll take a closer look at implementing interfaces with conflicting methods. Let's talk about some fun, rare cases: implementing interfaces with conflicting methods. It is possible that when you're implementing multiple interfaces, a class may run into a situation where the methods in the interface have conflicting signatures. In this case, the class must provide an implementation for the conflicting method. Here's an example of conflicting methods in interfaces. In this example, my class implements both the myInterface1 and myInterface2 interface, both of which have a method with the same signature. These are methods that are implemented, but due to the limited space on my slide, they're empty. That doesn't change the situation here though. There's a conflict. To resolve the conflict, the class must provide an implementation for the myMethod method. Let's have a look at our example in IntelliJ. I'm going to give both prey and predator a default method run. And I'm going to do something very similar in prey. So I'm actually copying the method, but instead it's going to be prey is running. And you can immediately see there's one related problem. And the one related problem is in Fox. This time there's red squigglies, but they're smaller. Let's hover over them. It says that Fox inherits unrelated defaults for run from the interfaces, predator and prey. And we must fix this. The solution would be to override the run method here. So let's go ahead and here say add override, then override public void run, and then give it our own implementation, which would be Fox is running. And as you can see, the red squigglies went away, and interestingly enough, it's not showing an I on the left side, but an O from override, because we're now overriding instead of implementing. And as you can see, the red squigglies are gone. There's no longer a problem because we say what implementation Fox needs to use. Alright, so that's what happens when two interfaces have implemented conflicting methods. The class that overrides both must specify its own implementation. It's time for a related topic, abstract. In the next video, we'll take a closer look at abstract and what it means for classes and methods. In this video, we'll look at abstract classes and abstract methods. Don't worry, it's not as vague as it sounds. Let's start with abstract classes. Abstract classes are classes that cannot be instantiated directly. They serve as a base class that other classes can inherit from. Why would we want that? Well, sometimes things might be too abstract to instantiate. For example, let's say we're talking, and this is a non-code example, and you want to meet up. We agree to meet next week. Next, I ask you if it's okay to bring my animal. You'd probably say, what animal? And also, I would not really just have an animal in mind. I would have something more specific in mind, such as a dog. I actually do have one. He's lovely. So, arguably, animals are too abstract to instantiate directly. And what we can then do is mark the class with the keyword abstract. Like this. Now we can no longer instantiate the class because it's abstract, but I can still define behavior that all animals have in common in my abstract class, such as the need to eat something, for example. So I could say public void eat, and then just specify, again, something very vague, animal eating. So even though the class is abstract, I can add functionality and also properties to say, hey, this is what all animals have in common, and it serves as a really good base class. So let's also give animals a weight. So not being able to instantiate it with the new keyword is already an advantage, but it comes with some more functionality. I can give an abstract class abstract methods. Abstract methods don't have a body. We've actually seen these in the interfaces already, but just like they're implicitly public, they're implicitly abstract as well. Here's an example. The method is made abstract with the modifier keyword abstract. Abstract methods can only exist in abstract classes. Otherwise, you'd have some weird non-finished object without an implementation for a specific method. That's not possible, luckily. When a class inherits from this abstract class, it must implement the abstract methods. Here's an example. The myAbstract class is an abstract class that has both a concrete method and an abstract method. The my class extends the myAbstract class and provides an implementation for the abstract method. Let me show you how to do this in IntelliJ. So let's give our animal an abstract method, breathe. As you can see, we now have 3 related problems. And that's because we have 3 classes that inherit from animal and they don't implement breathe. So let's go ahead and open them up. I'm going to use mammal, insect, and bird. So let's just say that for some reason on bird we can specify how to breathe because that's the same for all birds. Please, this is not a biology class. This might be very inaccurate. I honestly have no clue. Do let me know though if you know. So let's just here say bird breathing. And then on insect, we'll be like, now that's actually, we can't say here. An insect might be too vague anyway, so let's make this class abstract as well. And as you can see, the red squigglies go away here, but we have one related problem. Right now, it's our ladybug that would have to implement the method breathe. So let's go to ladybug. And then here, override the methods. Alright, and now let's go back to mammal, and let's just for simplicity assume that all mammals breathe in the same way as well. I mean, I bet they don't, but that's not the point here, okay? I just want to not have to override it on both fox and rabbit. So what is the point? Well, abstract classes, they can actually have both implemented and unimplemented methods. And if you're not able to implement the methods on a child class yet, you'd have to make this class abstract as well, like we did for insect. And then the first inline concrete class would actually have to implement all the abstract methods from the parent. Okay, one more thing to do. Let me show you that we can indeed no longer instantiate animal. So I'm going to give this a quick main and then create a main method in here. And I'm going to show you that I can say this. And I'm also going to show you what happens if I try to do that. So in here it says animal is abstract, cannot be instantiated. I could instantiate a child of animal, like fox. So abstract classes can provide a common implementation for methods that are shared across multiple subclasses. And they can contain abstract methods that must be implemented in the child classes. The abstract classes cannot be instantiated. In the final video of this module, we'll deal with the final keyword. In this final video of this module, we'll look at another Java modifier, namely final. So the final keyword is another modifier, and it slightly changes the behavior of the class, method, or variable that it's on. Let's first talk about what the final keyword does when it's placed on a class. When a class is final, it means that the class cannot be extended by other classes. So for example, if I would make the class mammal final, we would get problems. Why? Because it has 2 children. And as you can see, it says here that it cannot implement mammal, cannot inherit from final interfaces mammal. Okay. By the way, the interface is the package that we're in, okay? So this is not related that it should be an interface or something, but I've just made a package interfaces for this. So mammal, the fix would be make mammal not final, which is actually what I'm going to do because I don't see a use for mammal being final here, but I just wanted to demonstrate the error that we would get. When a method is final, this means that the method cannot be overridden in a child class. And a variable can be final too. This means it can only be assigned a value once. So on a variable, it indicates that a variable is a constant and cannot be modified. So let's create a final int. I mean, this is a nonsense int at this spot, but I just want to show you that I cannot give this a value for the second time because it's final. As you can see, we get red squigglies and it says cannot assign a value to final variable x. So that's a problem. The obvious solution would be to make it not final. But let's remove this for now. I just want to demonstrate the functionality. And then one more thing. There's a concept called effectively final. And this means that even though a variable is not marked as final, the code would still compile if it was marked as final. This means that this variable only gets a value assigned once, otherwise it would not compile with the final keyword on it. Alright, that concludes a quite tough module on interfaces, abstract and final. I can imagine this is really hard, so please don't give up. Get some practice with it and you'll see that you improve your understanding of these concepts by working with them. In this section, we're going to be dealing with generics and collections. We're going to start with the concept of generics in this video. Okay, first things first. This is probably not a topic that you'll be using on a daily basis to create your classes. Usually you don't create your own class with generics. Sometimes you do. But one thing's for sure, and that you'll be working with classes that use generics a lot. Because you need to understand generics, because you're going to be working with collections later in this module. So, what are generics? Generics allow you to write type-safe code in Java without having to worry about typecasting. And you may wonder, I thought Java was type-safe already, and you'd be kind of right. But these provide a way to declare classes and methods that work with different types of data. At this point, you might actually also be totally confused and think, what is he saying right now? And I would totally be with you. Let's switch to IntelliJ and show you the problem that it's going to solve. Alright, I'm going to be creating some classes. I'm going to start by creating a laptop class. And then actually I also want to have a laptop bag. And the content of my laptop bag is going to be of type laptop. So I'm going to say private laptop contents. And I'm going to generate getters and setters for the content of my bag. Let's just give the laptop a name so that I can show you this later. Alright, let's create another class. And this time I'm going to create a Chihuahua. I mean, there's always a reason to use a puppy in my example. And I'm also going to give our Chihuahua a name. And create the getters and setters for it. And of course, I want to have a bag for my Chihuahua. I mean, that's the entire point, right? And as you can imagine, the content is going to be quite similar. It's going to have a private content, but this time of type Chihuahua. And I'm going to create getters and setters for this one too. So let's also go ahead and create a class book. And let's also create a bag for books. And this time the content is going to be an array of type books. and I'm going to create getters and setters for it. Okay, looking at this example, what is striking? Well, first of all, there's a lot of duplicate code. Yikes. This can be simplified with a generic class. In this case, for bag. That would mean that we know it's a bag, but we're just not sure what will be inside of the bag just yet when we're writing the class. It will be clear what kind of bag it is when we're using the class bag to create an instance. It could be used for Chihuahua, a laptop, or for books. Here's what a class for the generic looks like. We can declare generics using angle brackets and a type parameter. We can then use this type as the type for our class's properties. Here's how we would do that in IntelliJ. So I'm going to create yet another class, but this one is going to be replacing a lot of our classes. And this one is called bag. And I'm going to give it a generic T. And I'm going to give the content as well. That's going to be of type T. I can create getters and setters for this. And also these getters and setters will specify the type T. And this way I can get rid of 3 other classes: books bag, Chihuahua bag, and laptop bag. But you may wonder, what is the type of this content of the class? Well, I don't know. It depends on how the class is created. And that's exactly what we're going to explore next. How can we use classes with generics? So join me for the next video. In this video, we'll look at using classes with generics. The generic can be replaced with any data type, except for primitives, so any object type. In this case, the T-type parameter can be replaced with any data type, such as an integer, string, or double, when the class is created. Here's an example of how to instantiate the bag class. We specify the type for the generic between angle brackets. And we repeat these angle brackets before the parentheses on the right-hand side. T is then being replaced by laptop, to some extent. And we're only allowed to use type laptop for the property content. Let me show you this in IntelliJ. So I'm going to be creating a main in which I can instantiate the class. Give it a main method. Right, and in here I'm going to say bag, and then, well, let's do one with the Chihuahua type. And we'll call it Chihuahua bag. It's just the variable name equals new bag. And then I don't need to repeat Chihuahua type, it's between the angle brackets, but it would be allowed. And then let's also create a Chihuahua. And let's give our Chihuahua a name as well. Let's call it Rocky. And then right now I've created the bag with the generic Chihuahua, and I'm going to add the Chihuahua to the bag. So I'm going to say Chihuahua bag dot set contents, and there goes Rocky. Alright, so we can do something similar for laptop. Let me show you. So I'm going to give the name, of course. Mine is called Lappy right now. And I'm going to be setting the content of my bag to be my laptop. There we go. But let me show you something. I've now created 2 instances of the bag class, one with Chihuahua type and one with the laptop type parameter. The value of the T type parameter is set and retrieved using the set value and get value methods. And this actually means I cannot go ahead and try to add a Chihuahua to my laptop bag. Let me show you that this doesn't work. So if I'm going to try to add the Chihuahua, it's going to say that it cannot convert these types. It says required type laptop provided Chihuahua, and that's a problem. And this is how we can make it type safe. We can make a class with a generic, and then upon instantiation, we specify what that generic should be, and then it's type save again. There's actually a little more to say about generics, but this is enough to get you started with collections soon. So this is it for the video on generics in Java. In the next video, we'll take a closer look at classes with generics. We're going to be working with the collection framework, the list one to be more precise. We're going to be talking about lists in this video. It's the first interface of the collection framework that we're going to be talking about. Collections allow us to store more than one value in one variable, and they're packed with handy built-in functionality, a bit unlike the arrays. The Java collection framework provides a set of interfaces and classes that can be used to store and manipulate collections of objects. There are 4 core interfaces in the collection framework: list, set, queue, and map. The list interface is one of the core interfaces in the collection framework, and it's used to store a list of elements. The list interface extends the collection interface, and it provides additional methods for manipulating elements in a list. A list is really just that, a list. Think, for example, of a list of items to buy at a grocery store. This would be just words, so strings on the list. We need to specify what we're going to be putting on our list. This helps to avoid that everything becomes one big mess. And of course, this is done with generics. The list interface and several classes that implement list can be used to create a list. Let's first create a shopping list. I'm going to specify the generic string. As you can see, I need to import Java util list. And I'm going to call this shopping list. Then I need to say new something something list. Remember, list is an interface, so I cannot instantiate that. But array list is a very common implementation of the list interface that we can use. Now I can go ahead and add some items to my shopping list. This is done with the add method. So you say shopping list, which is the name of my variable, dot add, and then in there I specify the string I'd like to add, like this. And I can do this a few times. There we go. That's it. That's my shopping list for now. 3 items only. And I could also create a list of integers. But remember, I was not allowed to use the primitive, so I'd have to use the wrapper class. So let's just create a list of numbers here. Like this. There's actually multiple ways to initialize the list as well, but for now, I'm just going to do it with add. I'm going to be adding 1. And I'm going to be adding 10. And I'm going to be adding 100. It's not that I can only add 3 items, that's just all that I'm willing to type at this moment, and it's enough to demonstrate that I can add multiple items on my list. So again, since list is an interface, we cannot instantiate it. In these 2 examples, we're instantiating the array list instead. ArrayList is a built-in class that implements the list interface. There are multiple options out there, but we'll be only using the ArrayList here. One nice thing about the class in the collection framework is that they have a nice toString method. Remember when we were printing an array, we could not make a lot of sense of it. But actually when I'm printing my shopping list and when I'm printing my numbers, I actually get quite a neat output that even tells me what's on there. As you can see, I get the words that are on my list and I get the numbers that are on my list. Very readable. Alright, so I mentioned there's multiple nice items to go ahead and manipulate the list, so let me show you that. So first of all, I can use the get and then the index to get the value out. So the first item I added is going to have index 0. So x is index 0. There we go. So if I go ahead and print this, we'll get x. I'll show you that in just a minute. What we can also do, we can go ahead and delete items from our list with the remove method. And I can either remove by index or remove by object. So in this case, I'm going to say remove pasta, and that's going to remove the second element, which is index 1. And let me, after this, print shopping list again. Well, there's even more things you can do. As you can see, there's a lot of suggestions when we hit the drop down. You can use add all, which is going to be for adding an entire collection to it. And this way you can add multiple items all at once. You can use dot clear to get rid of all the items on the list. But, and this one is quite nice, you can see if it also contains some object. So if I want to know if my list contains bananas, I can go ahead and check if it contains bananas. So let me store this in a boolean, because this is going to return true or false. There we go. So let me output this as well. And there's more methods on the list, and you'll see these once you need them. But just keep in mind, whenever you feel like, this is something that people would need more often, there's probably something smart built in for this. So let me show you once more what happens if I run this. And as you can see, the 0th element is eggs. Then after removing pasta, we only have eggs and bananas left. And when we see whether it contains bananas, it prints true. Please mind, we could also use more complex objects. So our own custom-made animals, users, all sorts of accounts, anything that is an object can be the generic of a list, even another list. So lists are only the first interface of the collection framework that we have a look at. In the next video, we'll have a look at the set interface. Let's move on to the next topic on our list, sets. In this video, we're going to have a look at sets. The set interface is also a core interface in the collection framework. And it's used to store a set of elements, where each element is unique. This is the main difference with the list that we've just seen. The list can contain duplicate items, a set cannot. There's another important difference. Elements in the list can be retrieved by their index. The set is unordered, and the elements don't have an index. But just like list, the set interface extends the collection interface and provides additional methods for manipulating elements in the set. Alright, enough talking. Let's see some code examples of using the set interface. So I'm going to create a set of type integer right now. And just like list, I need to import set. It's in the Java util library. And then I'm just going to call this int set. And then I'm going to create a new hash set. Now let's add some numbers to our set. And let's actually add the number 10 twice, because as I mentioned, it can only have unique values. So you can guess what happens if I'm going to be adding it twice. And then I'm going to print the set. And as you can see, it contains 110, not even in the order that I added them, and 10 is only in there once. In this example, an instance of the hash set is created, which implements the set interface. The add method is used to add elements to the set. And the set can only contain unique elements. If you add a value twice, it won't crash, it'll just keep it only in there once. The helpful methods on set are very similar, so instead I want to show you something else. We can use it for each for the collections in the collection framework as well. So let's just say for integer I in our integer set, go ahead and print it. And this will now go ahead and iterate over the elements of the set and do the specified action, which is in this case iterating. Alright, all set to work with sets. Next in line is the video on the queue interface. In this video, we'll be dealing with the queue interface. Just like set and list, the queue interface is also a core interface in the collection framework, but this one is used to store elements in a queue. A queue is a data structure where elements are added to the end and removed from the front. It's a bit special in that sense, just like queues for a counter in a show. There's actually also special queues, where you can also add to the front or remove from the end. Queues are great whenever you need to work with the first in, first out or last in, first out structures. Let's explore them in IntelliJ. Alright, let's create a queue. And I'm going to create a queue by saying this, and I'm going to make a queue of strings. And then I'm going to say new array deck. Often also called dq, but since it only has one UE, I think we should say deck. But, well, I don't know. You can call it whatever. I'm going to say array deck. So how to use this array deck? Well, it actually has this special quality of a queue that we can both remove and add from both ends of the queue. So it's a very special queue in that sense. It's double-ended. So what can I do? Well, I can go ahead and I can say add, and then I can go ahead and specify some sort of string. And I can go ahead and add another element. Let's go ahead and add Python in as well. And let's add one more. So right now, I only have limited options available, only the ones that are available in queue. Why? Because on line 8, I made it type queue. And actually, our array deck is of deck type. So we can also choose to update this to be of type deck. And then we actually have some more methods available, but these are not available on all the queues. So you can see right now we have a add first and a add last to modify where to add those. But as you can see, there's also other methods. We have pop. So with pop, we can go ahead and grab the last one that was added. But we could also use peek, and peek we can see which one is on the top, so which one we would be removing. And with push, we could go ahead and add to the top of our queue. So these are some important methods to work with on queues, and it probably takes some practice to get used to these. Just like the list and the set, we can use the for each on the queues as well. We can also use the remove methods. So right now, I want to go ahead and show you what the queue looks like at this point. We have Java, Python, and C#. So let's see what happens when we go ahead and we pop one element and then print it again. As you will see, the first element, so the element on top, was removed. So let's now go ahead and use the add first. And let's just insert Java again as the first, and then do another add last here. And I'm going to be inserting Rust. So I'm going to print it and run it again. And as you can see right now, the Java is actually in the first position because we used add first. Python and C# are in the middle, and at the very end is Rust because we did add last. So if you go ahead and do pop right now, Java is going to be popped and not Python, even though it was first in line just before we did this add first. We can also go ahead and do a peek. So I'll say peek. And after that, it's still intact. So we still have all the elements in our list. Let me show you. It's just printing the first element that would be popped. And instead of pop, we could also use poll. We could go ahead and say poll. And we actually have the option poll first and poll last here. So poll first in this case would go ahead pull Java, poll last would pull Rust. And then let's go ahead and print it again. And as you can see, Rust was pulled, and then after that we had our original list back. So classes that implement a queue interface allow us to create collections that we can work with in a last in, first out or a first in, first out way. The next video is the last one on the collection framework. We'll look at the map interface. Maps actually work a bit different than the other collections we've seen so far. Let's discuss the map interface. The map is a little bit different. The other interfaces in the collection interfaces inherit from the collection interface, but not map, because map works a bit differently. Where the other interfaces were made for storing multiple values, map is made for storing key value pairs. Multiple ones, of course, but key value pairs instead of single values. The map interface is also a core interface in the collection framework, and it's used to store the key value pairs. A map allows you to look up values based on a key. The map interface provides methods for adding, retrieving, and removing elements from the map. And as you can imagine, adding key value pairs is a bit different than adding a single element. That's why it's a separate interface. Let's see map for ourselves in IntelliJ. Alright, let's start by creating a map. So, since map has key value pairs, I need to specify two generics. So in this case, I'm going to specify a string and an integer. And of course, I need to import map as well. It's in the Java util library. So, okay, I'm going to call this one my name ages map. And then I'm going to say new hash map. Again, map is an interface, so I cannot instantiate this. Hash map is an implementation, and I can instantiate that one. So I'm not going to add, I'm going to put. And I'm going to specify a string, in this case my own name, and my current age. Okay. And let's do this again. Put, and this time I'm going to do another one. And let's add a third one as well. And it says 25. Okay. So, as you can see, it takes two generics. And of course, I must make sure that when I put it, that the generic match. So I can't, for example, say 2 and then high, because the order is string integer, not the other way around. You can also not add anything else, because it's going to check the key must be a string and the value must be an integer. We can get values out by their key. So, for example, let me first print this map, but then if I want to get one value out, for example, my age, I would go ahead and say get, and then insert my name, because that's now the key to get it. Okay, let me run this and show you what the output looks like. As you can see, it prints the values on the map as key value pairs separated by the equal sign. And then when I go get the value from Micah, it prints 31. So that makes sense, because I associated the key Micah with the value 31. So since map is a bit different, some things work a bit differently. For example, iterating over it works a little bit differently, because I can't just really iterate over my map. I need to be a bit more specific. So what I could say, that I'm going to iterate over all the values, that would look like this. The values are integers, so I'd have to say integer I, for example, and then go name ages map dot values. And then I could go ahead and print all the values. As you can see, map is also unordered. They're not in the order that I stored them in. It has to do with the hash map. Spare the details for now. So what I could also do, I could also loop over the keys. And this would give me back a key set, and I could print all the keys. And with the keys, I actually have access to the values as well. So I could go ahead and say something like this. Dot get, and then insert s. So that's also something that can be done. Let me show you the output. And as you can see, we get the keys and the corresponding values. Then there's one last way to loop. So in this case, I'm going to be looping over the entry set. So here's how that's done. it will be an entry, which is on the map interface, and I'll have to specify the key and the value, or at least their types. And then, well, let's just call this entry for now, and then go name agesMap dot entry set. And this is going to return key value pairs. And I can go ahead and use these, well, to just work with the keys. So the first one is going to be of type string. So I could go ahead and just print it here. I just could say entry dot get key. And the second one is of type integer, which I can also just print. But you can see it actually knows the types because of the generics we specified. Alright, so there's more that we can do with map. For example, we could also go ahead and remove items. So if I grab the name age map and I'm going to be removing, I would have to use the key for that, so the name. So in this case, we're going to remove Lola. But I could also update something. Say it has been my birthday and I turned 32, which would be a logical new age after 31. I go ahead and I just do put and then the same key again, and now it's just going to update Micah to be 32, since the keys in the map must be unique. Well, think about that for a second. That's not too weird. I'm actually not printing the new map just yet. Let me add that too. So it's not too weird that the keys must be unique, since we use the key to retrieve the value. That means that without the key, we couldn't get the value. And if there's a duplicate key, there would be an ambiguous value. So that's not possible. So the keys, they must be unique. And it just assumes when you're going to put something with the same key that you want to override the value that you provided. So in this new version of the map, you can see that we now have 2 left because we removed Lola and Micah, her age, got updated. Well, that's actually it for the map interface in the collection framework. We can use it to store the key value pairs. And this concludes our series on the Java collection framework. Before you move on to the next topic, make sure to get some practice. You'll use these a lot in real life as well. Let's talk about exceptions. Java throws an exception when something goes wrong. Exceptions are not supposed to happen, but they happen on the unhappy path. They're a mechanism in Java for handling problems that occur during the execution of a program. When a problem occurs, an exception is thrown. Exceptions are an important part of the Java programming language, and it's important to understand how they work and how to use them in your own programs. Exceptions are special Java objects. They are used to signal that something unexpected has happened, such as a divide by zero or a missing file. The goal of handling exceptions is to allow the program to continue running after the problem occurs, rather than halting immediately, meaning crashing the program. When you handle an exception, you specify what needs to happen when the exception is thrown. It's like a protocol for emergency situations. There are 2 options for exception handling. The first option is to add it to the method signature. This forces whoever calls the method to deal with the exception. Or you specify a protocol for the exception using a try-catch block. The better option depends on the situation. We'll see both these things in detail later. Before we do so, let's have a look at how we can throw exceptions. This comes in handy when we want to see how to handle them. Let's break stuff. In this video, we'll look at how to throw exceptions in Java. Throwing an exception is done with the throw keyword. We can actually throw anything in Java that implements the throwable interface. But even though you can throw it, it definitely doesn't mean you should. But you should throw any exception object, including instances of the built-in exception classes or instances of your own custom exception classes whenever you need them. So when we want to throw an exception, we use the throw keyword. It's just used to throw the exception, but what's very important is that it's followed by the exception instance that you'd like to throw. Alright, so let's say we would say this right here, throw new exception. At this point, we actually get a problem, And I'm going to deal with it, but I'll explain you what this does later. I'm going to run my code now. And as you can see, we get an exception. Why? Well, I threw it myself, so I know why. But sometimes you actually want to have slightly more meaningful exception in a more specific situation. So let's say that we also have a method here, and this method is called divide. I'm going to make it static for my convenience, so I don't need to create an instance. And it's going to accept two integers, a and b. And what is going to be done here is that we're going to print a result. And the result is a divided by b. But if b is 0, this would actually throw an exception. So let me specify that. If b equals 0, so it would throw the exception, but instead we are going to throw it ourselves here. There we go. And then right now, all I need to do is go ahead and call my method. And of course, I'm going to call it with b being 0. So, okay, go ahead and run this program. And right now, we again get the exception as expected, and our message cannot divide by 0. But we also get the stack trace. You can see that the first line says it happened in the divide on line 10. And before there it says we pretty much called this method, and that's the main method. So from the main, the divide was being called. So that's the stack trace that we're looking at right there. So right now, I don't have any proper exception handling in place. There is something I need to tell you in the next video why we actually would not need it here either. But it's a nice illustration of when to throw an exception. In this case, when we see that it is going to be problematic, when b is equal to 0, we throw the arithmetic exception. Honestly, this is not necessary, because dividing by 0 would throw this exception in itself already. So even if I comment this out and I run this code, we'll get the arithmetic exception. But this one, you get a different message, the built-in one, slash by 0, dividing by 0. We can deal with exceptions, we can catch them, and we'll see this very soon. But it's also very important to create a general handler, or alternatively, we could let them propagate up the stack until they meet a catch block that deals with them. Eventually, exceptions need to be handled. But that's it for how to throw exceptions for now. Before we're going to see how to handle exceptions in more detail, we really need to see that Java has two main types of exceptions, the checked ones and the unchecked ones. Let's explore these in the next video. Java has two main types of exceptions, checked and unchecked. Let's start with some non-code examples. Let's talk about the building of your company. There needs to be an evacuation protocol. Why? Well, because it's not within your control, or the company's control, or whomever's control, that something that requires evacuation can happen. Terrible things like fire, threats, and more can happen, and they require evacuation of the building. Evacuation is the backup plan to get out of a terrible situation with minimal damage. So, if there's a plan, this can limit the damage. Hazards like these are so common that most countries require an evacuation protocol being in place. Some other things don't require a protocol or backup plan. For example, think of stairs. So, a step of the stairs can break, and that makes it prone to falling off the stairs. But there doesn't need to be a big pile of pillows under the staircase for when it randomly breaks down. Why not? Well, when we would need that, we could better fix the staircase instead. These sound like two random situations, the building and the stairs. Let me tell you how all this relates to exceptions. We have two kinds of exceptions, checked and unchecked. Checked exceptions are exceptions that the Java compiler requires you to deal with. You have two options for this. Handle the exception with try-catch, or declare the exception in the method signature using the throws keyword. Checked exceptions are like the problem that requires an evacuation protocol. It's out of your control, and you need to have a backup plan in place because it simply can happen. Let me give you a code example. Assume your code is reading a file. An example of an exception that can happen when you try to read a file is the situation that the file you'd like to read is not there. That is not within your full control. The file can be moved or removed by an external program or user. We'll discuss the exact details of exceptions that can happen with files later. Let's first discuss the unchecked exceptions. The compiler doesn't check for those, and they need to be solved by writing better code typically. These are like the staircase and the pillows in that sense. You should not handle these with a throws or a try and catch. That would be like having pillows under the poorly functioning staircase. Instead, you should go ahead and fix the staircase, which in this case would be code. If you feel the need to put a pile of pillows underneath your code, write better code. Examples of checked exceptions are SQL exception and the I/O exception. Both of these deal with external dependencies. I/O is for everything input and output, such as reading and writing files. And SQL deals with databases. The unchecked exceptions include the null pointer exception and the illegal argument exception. Instead of dealing with a null pointer exception, it's better to avoid the null pointer. For example, by working with the optional class, or by checking whether a value is 0. So you may wonder, how do I know whether an exception is checked or unchecked? Some of them are rather logical, but there's a way to know for sure by looking at the code of the exceptions. The checked exceptions don't extend from the runtime exception. The unchecked exceptions do. They happen at runtime. That's why they inherit from the runtime exception, either directly or indirectly. All exceptions extend the exception class. Some of them directly, other indirectly. It's important to understand the difference between checked and unchecked exceptions, as they require different approaches to handling and declaring. Checked exceptions need to be dealt with in the code. You can specify a protocol, or you have a warning for the calling code. Unchecked exceptions usually mean that your code isn't robust and solid enough, and that it needs fixing. That's it for this video on checked and unchecked exceptions in Java. There are two ways of handling them. In the next video, we'll look at how to handle exceptions using the throws keyword. There are two ways of dealing with checked exceptions. First, we'll look at how to handle exceptions using the throws keyword. When a method possibly throws a checked exception, you can indicate this in the signature. This way, you don't need to deal with the exception in more detail. This will have to be done by the code that calls the method. Indicating that the method might throw an exception is done with the throws keyword. If a method signature indicates that the method might throw a checked exception, the calling code needs to deal with this. That means that it must either handle the exception within the method using a try-catch block, or also declare the exception in a method signature using a throws clause and leaving it to their calling code. Let's have a look at an example in IntelliJ. So I already mentioned that we did not really need the throws clause on line 4 for the arithmetic exception, and that is because it is a runtime exception. But instead, if for now, and this is definitely not a good practice, we would instead throw a I/O exception. An I/O exception is a checked exception. So our code is going to give an error. If I hover over this, you can see it. It says unhandled exception. And then we have options. We could either work with a try catch, or we could add the exception to the method signature. And we do that by specifying throws and then the type of the exception. And as you can see, it's all good right now. It's a good practice to be so precise as possible. So don't specify exception here, because this way you allow all exceptions to be undealt with. So really only specify the ones that you need to have any throws clause. So right now, if we would not have the throws exception here, our calling code would have a problem. Let me hover over it to show you. It says unhandled exception. Because I'm throwing a checked exception, the compiler can now tell that the method may throw an exception. And therefore, I have two options. You can guess them probably by now, try catch, or add it to the method signature. And I'm going to go for this last option. Alright, let's have a look at another example. So this time, I'm going to work with a file. So I'm going to say file, and of course I'll import file. It's coming from the Java IO package. And I'm just going to say equals new file. And that's going to be sample.txt. So right now, if I'm going to use this file in a file reader, I'm going to get an error when I don't have any exception handling in place. And this is because the file reader may throw the file not found exception. So I could either work with try catch, but this time I'm going to do again add exception to method signature. And as you can see, my code will compile right now. And I can run this, and you'll actually see that we'll simply throw the exception and no real handling is happening here, because the file is not found. We don't handle the exception, we only declare that it might throw the checked exception. And this way it will be propagated to the caller of the method. And the caller of the method must handle it or declare it using the throws keyword. In this situation, we're calling it from the main. And as you can see, it's going to throw the file not found exception because it doesn't anywhere on its way come across a proper handling method. So this is why we get this method as we get it, and our program is going to stop. As you can see, this is a terrible practice because our program stopped running and it crashed. We could have used a better way to deal with the exception. Please mind that you can also throw unchecked exceptions, but the rules are somewhat different. Since it's unchecked, it doesn't need to be handled, and since it's unchecked, the code doesn't necessarily need to be able to throw it either. Using throws should only be done if you can't specify how to deal with the exception on that level. So it's time we're going to have a look at how to handle exceptions using the try-catch block. We've just seen how to postpone dealing with exceptions by using throws. In this video, we'll look at how to handle exceptions using the try-catch block. The try-catch block is used to handle exceptions that are thrown in a try block. Here's what the syntax of a try-catch statement looks like. Code that might throw an exception is put in the try block. If the exception is thrown in the try block, the program immediately jumps to the associated catch block, which can then handle the exception. If the exception doesn't get thrown, execution continues after the catch block after completing the try block. Here's how we can update our example in IntelliJ. I'm going to get rid of the throws class here, and instead I'm going to surround this with a try catch block. So first I'm going to put a try around this one. And then I'm going to catch the file not found exception. I'm going to call it E. And then in here I'm normally would do some logging, but I'm just going to say file not found. And right now we know the file is not found. So instead of going to go ahead and have the throws file not found exception declared on the main and then crashing our program, we're now actually just printing the message file not found. And as you can see, there's no red on our program. Our program actually just continues to execute code afterwards, which it wasn't done before either. So right now it's just going to print done and carry on after the catch block with the normal flow of the program. This is the main advantage of using try-catch blocks. Instead of crashing the program can continue execution after the catch block. We can also add a finally block to our try-catch. This is typically used to clean up any resources. The finally block is always executed, whether or not an exception was thrown. So, for example, if we needed to close the file reader, we can do this in the finally block in IntelliJ. You can use multiple catch blocks to handle different types of exceptions, each with its own handling code. We'll see an example of this when we're dealing with files in the next module. We'll skip the details on this for now. You'll run into them when you need them. For now, just know that code that may throw an exception is in the try block. And if the code indeed throws that exception, whatever is in the associated catch block will be executed to deal with the exception so that afterwards a program can continue. That's it for this video on handling exceptions using the try catch block. In the next video, we'll look at how to handle exceptions using the try with resources statement. We have seen that we can use try catch to handle exceptions. In this video, we'll look at how to handle exceptions using the try with resources statement. The try with resources statement is a try statement that declares one or more resources. The resources are automatically closed at the end of the statement. You should say that's a nice try, right? Here's an example of how we can use the try with resources statement. The resources are declared between the parentheses after the try keyword. And you can go ahead and specify multiple resources. Multiple resources are separated with a semicolon. When the code executes, they're open from left to right. So R1 is opened first in this example, and then R2 is opened. At the end of the try with resources statement, they are all closed automatically, and they're closed from right to left. So R2 gets closed first, and then R1 gets closed second. This is because sometimes, or actually rather often, the second one depends on the first. So we first have to close the second before we can close the first. Let's have a look at our previous try catch example again. We're now going to update it to use try with resources. So let's change this into a try with resource. So I'm going to be opening up my file reader within the parentheses after try. And then I'm going to say equals new file reader. And I'm going to just specify the path. And that will do. And I can actually comment this out, and you can assume that there's logic for reading the file between here. And as soon as it's done with the try block, it's going to try and close. But as you can see, there's a lot of red squigglies. If I hover over it, it will tell us why. It says an unhandled exception from the auto-closable resource, the Java I/O exception. So what happens is that when this file reader gets closed, the I/O exception can be thrown. So instead of having the file not found exception, we could go ahead and change this to I/O exception, or, and I like this better, I'm going to catch the more generic I/O exception as the second one. And this is important. The more generic ones always need to be later in there, because if we do catch I/O exception and then catch file not found exception, we would actually never get to the file not found exception, because file not found is an I/O exception. As you can see here, when we hover over it, it says extends I/O exception. So this is why the I/O exception needs to be second in the list, because file not found exception is an I/O exception, and we could actually deal with it at first, and then therefore file not found would be unreachable code if it were the second catch. Anyways, the file reader is now automatically closed at the end of our statement, even if an exception is thrown. So that's quite a nice way of doing it. We can use the try with resources statement to simplify exception handling for resources that must be closed. And we'll see this in the next module a lot, but for example file streams, and later you'll see that you can also use it for databases and network connections. Often we don't need to finally block anymore for cleaning up. When we have a normal try, the catch block is obligated, but for the try with resources, catch is also not obligated. You can just have a try block for the try with resources. You could say, all you need is to just try. Okay, I promise I'm done with delaying word jokes for now, at least for the try statement. On a more serious note, please mind that not all the resources are auto-closable. And in these other situations, you may still need to finally block to close resources. So resources that are auto-closable are actually very easy to recognize because they implement the auto-closable interface. That's quite a logical naming convention there. But sometimes you'll see a class that implements the closable, and you might be inclined to think that that's not auto-closable because you'd probably expect that auto-closable is going to extend closable and not the other way around. And logically, you'd be right. But there's something funny going on, because closable extends auto-closable and not the other way around. Fun fact. Really a lot of fun. Alright, let's auto-close this video. Sorry, that was really the last word pun for now, for real. In the next video, we'll look at how to create our own custom exceptions. In this video, we'll look at how to create custom exceptions in Java. Sometimes you want to throw a more specific exception than the built-in Java exceptions. The good news is you can easily create your own. You can create your own class for an exception. When you want to create an unchecked exception, you extend the runtime exception class or one of its subclasses. If you want to create a checked exception, you extend the exception or one of its subclasses that doesn't extend runtime exception. Since runtime exception is, well, the exception here. Whatever extends runtime exception becomes unchecked. Quick refresher, that means that the compiler won't force you to deal with these exceptions using a throws declaration or a try construction. So a custom exception is an exception that's created by the Java developer. You can create custom exceptions to provide more meaningful error messages and to handle specific error conditions in your application. Let's create a custom exception in IntelliJ. So I'm going to create a new class and I'm going to call this wrong input exception. I mean, there's probably built-in exceptions for this. Since wrong input sounds like something that's out of my control, at least to some extent, I'm going to make it extend exception. And then in here, I'm going to add 3 constructors. The convention is to have the following 3 in place. One with no arguments, one that accepts a string message, and one that accepts another exception. Alright, so let me create them. And in here, I'm actually going to do not a lot other than calling super. I mean, that happens by default, but still. And then in here, I'm going to specify the string message. And I'm actually going to call the super with the message, because it's convention that a exception class has these 3 constructors. So let's do one more. This one's actually taking an exception as an argument. And I'm going to be calling super constructor again. Alright, so here's my custom exception. Let's create a main class and use it as well. I could call this main or I could call this app. Sometimes I get questions why I always call it main, so let me call it app for once. And then I'm going to insert a main method in here. I just need a main method for it to be runnable, so I can show you this. And then, well, let's say we have some sort of static method here that does a print of perhaps a string. And let's say that the string should not be bigger than 10 characters or something silly. So I'll go ahead and say string.length should be smaller than 11. And if that's the case, we go ahead and print it. And if it's not the case, we go ahead and throw our exception. All right, like this. And then since this is a checked exception, we must deal with it. So in here, I'm actually going to say that I want to have the calling code deal with it. So in here, I'm going to specify the exception that I'm throwing. And in here, you can guess that I'm going to call this code with something that's too long. And as you can see, I get red squigglies. So what I'm going to do now, I'm going to surround this with a try-catch to deal with the exception. Okay, I don't want to throw it here because it's my main method and that's not a good practice. There we go. And actually, I do know what I want to do with it. I go ahead and I'll just do a quick logging message. In this case, to the console. And I'm just going to print e.getMessage, and then afterwards, going to be done like this. All right, so if I run this, the exception will occur. And as you can see, in our catch, I'm printing the message that I've specified myself when throwing the exception. And afterwards, my code continues, so nothing goes wrong. Other than that, it's not printing the hello everybody, which is what I intended, but that was not possible. So in this example, I've created a custom exception class called wrongInputException, and it extends the exception class, and therefore it's a checked exception. I've given it the 3 constructors that I would always recommend. You know, args, the one that accepts the string message, and one that accepts another exception. And then in here, I went ahead and I used my exception for when a situation occurred that was out of my control, and I dealt with it from where I was calling this code. As a last notion for creating custom exceptions, just extend the exception that's the best fit for your custom exception, and don't overuse custom exceptions. In my case, it was not a good case. You know, we have illegal arguments, we have all sorts of exceptions. Probably one of these would have been good enough as well. So chances are that whenever you feel the need to do this, there might be some built-in exception that will do what you need already, and that is what you're looking for. So make sure to research that first. And having said this, we've covered all the essential topics related to exceptions in Java, and it's time to get some hands-on practice. After all that, we'll move on to a new topic that we could not deal with before knowing exceptions, namely dealing with the file reader and file writer. Now that we know exceptions, we can learn how to read and write files using Java. Reading from and writing files is a common task in programming in general. So of course Java provides several classes that make it easy to work with files. We're going to be using 2 of them, the file reader and the file writer classes. This may not be a huge surprise, but the file reader class is used to read character data from a file, such as text data. And guess what? The file reader class is used to write character data to a file. Both classes are easy to use, and they're part of the standard Java library, so you don't need to install any additional software to use them. You may wonder when you would use this, so let's go over a few situations in which you would want to use the file reader or file writer. So first of all, reading from a configuration file. You might use a file reader to read configuration settings from a file, such as database connection settings, email server settings, or other application settings. It can also be useful for writing to a log file. You might use a file writer to write log messages to a file, such as debug information, error messages, or other application events. It's also good for parsing text data. You might use a file reader to read data from a text file, such as CSV data or other structured text data, and then parse the data into individual fields or records. And there's a lot more options, but the last one I'm going to mention is generating reports. So you might want to use a file writer to write data to a file in a specific format. For example, an HTML or CSV file. This can help you generate reports or other formatted output. Alright, enough talking. Let's start reading. In the next video, we'll look at how to use the file reader class to read data from a file. In this video, we'll look at the file reader class in Java. We use the file reader class to read character data from a file. Some other readers don't read characters but bytes. This can be necessary for non-text data. As I mentioned, FileReader is a built-in Java class. It's a subclass of the input stream reader, and it implements the reader interface. Alright, so in this example that I'm not going to code live, but I'm going to walk you over here right now, we are having a try with resources. And in this try with resources, we are opening up a file reader that's looking for a file called file.txt. Well, where is file.txt? As you can see, it's in the root of our project, so it's right underneath this level. And this way, it can actually find it. The content of file.txt are, at this moment, the very interesting hi there. Alright, so if I go back here, that's what I do in the try with resources, but then I'm doing a few wonky steps. So on line 9, I'm creating a int data. And then that while loop, that might need some processing. This is actually quite a standard way to do this, but it's a very clever way. So let me try to explain this very carefully to you. So what we're doing in the while loop is that we're reading from the file. We're using reader.read, which is reading a character from the file. So only one character. And we're storing this character in the data, which is an int. So this makes sense because read is actually also returning an int, even though it represents a character. But the reason it's an int is because it's -1 when it has reached the end of the file. And if you remember from one of the very early lectures, the char primitive cannot be negative, it's unsigned. So therefore, what the reader.read is giving back in this case, the read method, it's an int, because it also needs to be able to be -1. So in this data, int, we are storing whatever we read. And as long as it's not -1, we have not reached the end of the file yet, so we keep on reading. But every time we do a read, we actually also are going to go one level deeper. So if we would do this twice and then only print it once, we would skip a character every time, to put it that way. So this is why we do it in a while. So we data equals and then we read. And by reading, we move the cursor of where we're reading. As long as we did not reach the end of the file, we keep on reading. And then we do something special. For every character that we read, we do a cast to char. Well, let me show you what happens if we don't. If we don't do this, we get a whole bunch of integers. So instead of hi there, we now get a whole bunch of integers. So these are the ASCII values. So 104 equals age, 105 equals I, well, etc. That is why we need to actually cast it to a char. And then we get the character representation, which we can make more sense of. So let's go ahead and run this again. And you can see that it now says hi there. But let's see that I would be looking for another file that's not there. So this file is not there. Now the catch block would say an IO error has occurred because it's a file not found exception. So let me actually also show you the type of exception in here. So I'll run it again. And you can now see that it's indeed the file not found exception. So let's change this back. And there we go. This is how to read from a file. So this is a bit funky and there's actually multiple ways to read from a file, but this is a very common way to read from a file. So once more, we use the try with resources to open up the file reader. And this means that the file reader will be automatically closed, so we don't need to deal with that. And we then use the read method to read the data from the file, one character at a time. But read is an int because it's -1 as soon as we reach the end of the file, and therefore we need to have the char type cast on line 11 to make sure that the data is printed as a character. Otherwise, we can't make a lot of sense of all the numbers in our console. So file reader is a great choice when you need to read character data from a file, but often you also find yourself needing to write to certain files. And that's exactly what we're going to be doing in the next video. We're going to have a look at the file writer class. In this video, we'll look at the file writer class in Java. Let's state the obvious again. We use the file writer class to write files, more precisely, to write character data to files. No way, right? Just like the file reader, file writer is a built-in class. File writer is the subclass of the output stream writer class, and it implements the writer interface. The file writer class is a good choice when you need to write character data to a file, such as text files. You could also use other classes like buffered writer and print writer to write to files with the additional buffering and formatting capabilities, but you can explore these later. Let's first have a look at file writer in IntelliJ. Alright, so again, I'm going to be using try with resources, but this time we'll use a file writer. And we're going to call it writer, and we say new file writer. And in here, I'm going to specify the output.txt. This can be anything. This will just be the name of the file that holds the output. Nope, no semicolon there. And then in here, I'm just going to, for now, use writer.write, and I'll just have a simply hi there message. You can still see some red squigglies because we still need to do a catch. I'm going to catch the IO exception here. And then I'll just go ahead and I'll log the message that occurred. Well, actually also the class. So we know which exact one occurred. And I'm going to say e.getMessage. All right. So I'm going to run my file right now. And there's no output, which means it was a success. So if I scroll down, on the same level as file, I can now find my output. So please mind, this wasn't here just yet. It got created by the file writer. So if I go back here right now, and I put something else in here, by now, for example, you'll see that the output has changed to by now. So it completely overwrites it. If that's not what we want, and well, that's quite possible that we actually don't want to overwrite it, we can go ahead and open our file in append mode. We just put through in there, and then right now it's not going to overwrite, it's just going to add it to the end. So you see, now it has by now in there twice. But what you can also see is that it did not go to a new line. So if I do want to go to a new line, I could put in a end of line character. And then actually, to get the result, I need to run it twice, right? Because there is no end of line character at the end. So if I run it now the first time, it's still going to be on the same line. But if I run it for the second time here, or actually the second time with hi there, it is now on a new line because the new line got appended right there. So let's wrap it up. In this example, we used the file writer. It's opened with the try with resources and therefore automatically closed. We use the write method to write to our file output.txt, and we catch it using a catch block. And please mind, if you want to append, make sure that you open the file writer with append is true. And that's it already for our video on the file writer class. We've now covered the basics of reading and writing to files. We've looked at the file writer and the file reader class. There's many more of them, but this will definitely get you started. So make sure to get some practice with it, and then we'll move on to a very fun topic, functional interfaces and Lambda expressions. So let's get started with the hands-on. It's time we add a new piece of syntax to our Java toolbox, Lambda expressions. At this point, you've probably seen it on the internet somewhere already when trying to debug some sort of other problem. Lambda expressions are the syntax that contains the arrow symbol, as you can see here on the Stack Overflow website. And as a few more times before, I want to give you the tough topic warning. This certainly is a tough way of writing code when you just get started with it. And it's normal if you need to watch the videos in this module a few times. The good news is though, that once you get it, and it's not even that hard anymore. It will become as normal as other ways of writing code if you stick with it. Let's talk about what Lambda expressions are. A Lambda expression is nothing more than a way of implementing an interface. But not just any interface, a functional interface. This is what we're going to be doing in this module to figure out Lambda expressions. We're going to start with what a functional interface is. Then we'll see how to implement a functional interface with a Lambda expression. And lastly, we're going to explore the Java built-in functional interfaces and how we can implement those. After being able to do all this, we're going to add the Stream API in the next module. We need the Lambda expressions to work with the Stream API. Working with the Stream API is really going to change the way that we are writing code. But first things first, let's start with looking at functional interfaces. In order to write Lambda expressions, we'll first need a functional interface. This is actually quite an easy concept, but it's a key concept for working with Lambda expressions. So, what are functional interfaces? Functional interfaces are special interfaces that only have one abstract method. And that means that they can have multiple methods as long as the other ones are non-abstract methods, such as default and static methods. But again, they can only have one abstract method. An abstract method is a method without a body. Here's an example of a functional interface. This interface is called calculator, and it has one abstract method, calculate. This method is returning an int and taking two ints as parameters. The add functional interface annotation is optional but recommended. To Java, this provides a clear signal that the interface is intended to be used with Lambda expressions, and the compiler will make sure that there's only one abstract method. If you have this annotation, you cannot have more than one abstract method in your functional interface. Let's have a look at this interface in IntelliJ. I'm going to start by adding this annotation as functional interface. And as you can see, we get red squigglies. Why? Well, because it must have one abstract method, and this moment it has none. So let's go ahead and give our interface a method. So it's going to return an integer, I'm going to call it calculate, and I'm going to pass in two integers. And as you can see, our red squigglies are gone. As soon as I would add a second abstract method, we would get them back, because it can only have one abstract method. But we could add other methods. For example, I could add some sort of default method. It's a very silly method, but this is allowed, because this is not an abstract method. It's an implemented method, because it does have a body. Same for static methods. There's one more funky thing we can do though. There's one type of abstract methods that we can add. For example, this one. This is clearly an abstract method, but it is allowed. And as you can see, there's something happening here as well. On the left, you see the eye and the arrow up. And that is because this is actually overridden in the object method. Since all objects are of type objects, we could add any of the abstract methods from the Java object class, like toString, because this will always be implemented already. Okay, well that's a bit of an exception, you don't need to learn this, but just remember there can only be one abstract method. Having just one abstract method makes it possible to implement functional interfaces with Lambda expressions. Now that we have seen the functional interfaces, let's see how to do this implementation with Lambda expressions next. Let's talk about Lambda expressions. A Lambda expression is a concise way to implement a functional interface. Remember, the one that only has one abstract method. So in order to write a Lambda expression, we need a functional interface to write the Lambda expression for. The Lambda expression essentially describes the implementation of that one abstract method. The syntax of a Lambda expression consists of input parameters on the left-hand side, followed by an arrow, and the method body on the right-hand side of this arrow. For example, consider the following Lambda expression: x, y, arrow, x plus y. You can read this as x and y become x plus y. The left-hand side represents the input parameters without specified types. And the right-hand side represents the body, which returns the results of x plus y. This is a method implementation, and it's basically the same as a method, though we did not give it a name, that takes x and y as input parameters and then returns x plus y. Let's discuss the parameters and body of Lambda expressions in a bit more detail. Lambdas can have 0, 1 or multiple parameters, and their types can be inferred from the method signature of the functional interface being implemented. Parameters are comma-separated when there are more than one. The body of a Lambda expression can consist of a single statement or multiple statements. If the body has only one statement, it can return a value or nothing. For a single statement returning a value, you can omit the curly brackets. Also, you can omit the return keyword and the semicolon. For multiple statements, you must use curly brackets, and you should include the return keyword again if the method is returning a value, that is. And also, you need semicolons for each statement, pretty much exactly like a normal method body. So these are the basic rules, and you may want to revisit them. Let's see some examples of this in the next video. We have seen the basic rules of Lambda expressions, and as I mentioned, I can imagine you'd have to revisit that again. But some examples of Lambda expressions might also help, which is exactly what we're going to be doing now. Here's the previous example again. X and y becomes x plus y. Let's have a look at some examples of functional interfaces that can be implemented with this Lambda expression in IntelliJ. So guess what? This would be a valid implementation of our calculate method. Why? Well, we say x and y is input, which will be the values for a and b here, and it's going to return x plus y, which is in this case a plus b. So that would be of type int. Let's create a main method and show you how to do this. So what's important is that we specify the type, so that IntelliJ knows what we're going to be talking about. So let's just create a calculator C1. And here I'm going to say x and y becomes x plus y. We do need a semicolon at the end because it's just a Java statement. And as you can see, this compiles. And this is now an implementation of our calculate method. And we could go ahead and say c1.calculate. And now I can just specify two values, 3 and 5. And this is going to return 8. So let's actually wrap this in a system out statement. So that's going to print the result. So I'm going to run this code. And as you can see, it outputs 8. The Lambda expressions use a simple arrow syntax to represent the implementation of a functional interface. So right now, we used x and y to specify the input parameters, and we made them return x plus y. Here's something else that we could have done, just to demonstrate you how the body works. If we would have said 42 over here, it would pretty much mean x and y becomes 42. That means that this always will be returning 42. Not very useful, but hopefully this is useful to explain you how this is working exactly. As you can see, the output is now 42. I'm going to change this back to x plus y. What's important to note is that the parameters need to match. So this is not a valid implementation, because the calculate method only accepts 2 parameters. You can, however, call this whatever you'd like to call them. So I called them x and y because to me that makes sense for mathematical stuff, but you could call them a and b or something and something else. It would have worked, as long as it's a valid identifier. So how does it know this needs to be the calculate method? Well, that's because our type is calculator over here. And if we move back to calculator, you can see it only has one abstract method, and that's the key. Since it only has one abstract method, it knows that must be the method that we're implementing here. And the cool thing is, I can create multiple implementations. So let's create C2, and C2 is going to be x minus y, like this. And then I can output the result of that one too. And then let's do, well, 3 and 5 again. And now we'll get 8 and -2. So Lambda expressions can handle different types of method bodies. And that includes single statements, multiple statements, and void statements. In this case, we're returning an int, so it can't do void. But let's see one that does multiple statements. So we're going to create a calculator C3. And again, I'm going to say it's going to accept x and y. And now I open curly brackets. And I'm going to do just hello from the Lambda expression. And I want to return a value as well. I'm going to be returning x times y in this situation. But since this is multiple statements, I need the return keyword again. And you can see now red squigglies on line 12. And this is because this whole thing is actually one line that needs a semicolon at the end. In my head, I call this the JavaScript semicolon. But you don't need to do that. I mean, you might not even know JavaScript, but that's how I come to think of it. So let's go ahead and call this method. You can see we do this in the exact same way. So I'm still going to wrap this in a print statement because I want to print x times y. Again, let's use 3 and 5. And there we go. Let's run it. And you can see it prints hello from the Lambda expression and 15 at the end now as well. Let's create another functional interface to show you some more examples. So I'm going to call it printer, make it an interface, make it a functional interface, and I'll give it a void print method. And let's say x accepts a string. So right now it's not returning anything, it's only accepting one value. Well, when it's accepting only one value, I can actually leave out the parentheses around the input arguments, but I can add them in as well. Both is valid. So let's go printer p1 equals, and then I could say s for string, arrow, and then let's just print a string with printer says appended. There we go. So now this is one statement, not returning anything. And as you can see, the s doesn't have parentheses around it, but I could go ahead and add them around it. It's valid too, but it's very common to omit the parentheses if you only have one parameter for your Lambda expression. So let's go ahead and call it. And I'm going to say p1.print hello. The reason I don't wrap this inside a system.out.print line is because it's not returning anything. So this is not valid to put in a system.out.print line because we cannot return voids, which is what the p1 print is returning. So let's go ahead and run this, and you'll see printer says hello at the very end. And there you have it. Printer says hello. All right, let me show you one more example. I want to have a functional interface that has a method that doesn't take any arguments. So I'm going to call this one number provider. And it's going to be a functional interface, of course. And it's going to have one method, provide, that returns an int, but doesn't take any arguments. Let me show you how to implement this with a Lambda expression. So this one is going to be of type number provider. Let's call it np1. And when it doesn't take any arguments, you do need to empty parentheses like this, then the arrow, And then you can just return any number. It could be a random number or just any number, or do some sort of calculation, use part of the time. I don't care. Just return some int and you'll be good to go. And that's what this looks like. And we can call this as well. So you can go ahead and, well, I'm going to print this again so we can see the result. MP1 provides, and that's just going to be printing 42. Alright, I think that's enough examples for now. I can imagine you need to see a few more, or you need to try it yourself and maybe watch this video again. But next up, we're actually going to explore how we can use these Lambda expressions as input for other methods. And from there, it's going to be quite interesting. So let's go. Let's have a look at how we can use Lambda expressions as method arguments. Because at this point, you may wonder, why is this instructor so thrilled about Lambda expressions? And you'd be right, we haven't seen yet how this can be helpful. It's not as if we were implementing interfaces in our code constantly before. We will soon see a new style of programming, functional programming. And Lambda expressions are commonly used in functional programming. The key lies in that Lambda expressions can be used as input for a method. This allows us to inject dynamic functionality. When a method requires a parameter of a specific functional interface, a Lambda expression can be passed as an argument. In this method, the Lambda function can be executed. This is going to make what this method does very flexible, since its functionality depends on its input, which is a Lambda expression, and it can be implemented in multiple ways. So let's look at how to use Lambda expressions as method input arguments, allowing us to inject dynamic functionality. So here's our main method again. And as you can see, we have multiple calculators implemented. So what I'm going to create right now is a static method, because I don't want to create an instance of main, so I can say public static int, and I'm going to call this execute. And in here, I'm going to say it requires some parameters, number 1, number 2, and this is where it becomes interesting, some implementation of the calculator interface. And then I'm going to say that this is going to return the result of calculator.calculate, and you can guess it, number 1 and number 2 as input arguments. So what does this method do? Well, it executes the implementation of the Lambda method as provided. That means it can do anything. So let's go ahead and create an int result1. And that's going to be execute with, well, let's go with 3 and 5 again. And let's pass in calculator 1. I'm going to make an int result2. Execute with 3 and 5 again, and now pass in C2. Make an int result3. Execute 3, 5, and then C3. Well, I mean, I did this in the last video, so let's have a quick look at these C1, C2, and C3. So here's C1, x and y becomes x plus y. So it's pretty much adding 3 and 5. C2, it's subtracting 3 and 5. And C3, which is in line 9 to 12, it's going to first print something and then return a result of x times y. The only reason it's doing that is because we want to demonstrate that we need curly brackets around more than one statement in your Lambda expression. Alright, so let's print the 3 results. So here I'm going to say result1 plus a space plus result2 plus a space plus result3. And let's run this code. And you'll see that even though 3 and 5 are the same, the results are going to be different because C1, C2, and C3 are doing different things. So you can see the hello from the Lambda expression is being printed, but it ends with 8, which is the addition, -2, the subtraction, and 15, the multiplication. So let's go over it once more. In this example, we have used the calculator. So let's go over it once more. first, we have implemented the calculator functional interface. We did this already in the last video with C1, C2, and C3. The single abstract method is calculate. So we use these three created Lambda expressions on line 5, 6, and 9 to 11 to go ahead and call the method execute. And execute is taking three input parameters, a number, another number, and some sort of instance of the calculator interface. Instead of going ahead and creating a class that's going to be implementing calculator and passing an instance of that in, which would have also been valid, we use a Lambda expression. So without Lambda expressions, we would have to do something like this. Let me show you. I'll call this calculator implementation. It's going to implement calculator. And in order to implement calculator, I of course need to override the calculate function. And taking two parameters, I'm gonna stick with the naming conventions, but I could have called them X and Y or C and D or just whatever. And well, let's actually do a division here because that's fun. Pick one extra option again. So now A and B is going to be A divided by B. Actually, that's a bit dangerous for integers, but oh well. So instead of calling it like this, I could also now create result 4. That is going to be execute 3, 5. And then here we're just going to say new calculator implementation. And this would be valid as well. But as you can see, this is a lot more hassle than just quickly doing this with a Lambda expression, which I'm going to do in just a second. I'm going to add result 4 here. And run it again. And as you can see, it's now 8, -2, 15, and 0. And the reason it's 0 and not something more sensible is that I said, hey, this is a bit dangerous. And that's because we do integer division right now. It does some casting. This topic is not for now, but just know to be careful with that. Sometimes this is actually exactly what you want to do. Other times it results into funky bugs. So I'm going to say result 5. I'm going to do the exact same thing as I just did with the calculator implementation, but now on the fly with a Lambda expression. So instead of creating a Lambda expression up there, I'm going to do what we commonly do, and that's implement it on the fly right here. Oh, so I actually called A and B right now, but I'm going to call it X and Y, and not because it matters at all, just because I know that beginners might think, oh, I need to stick to certain naming conventions. No, you don't. That's the main thing. I'm doing it like this. There you go. So this is actually how we typically use it. So we just pass in the Lambda on the fly directly. We don't create it, and well, sometimes we do, but we typically don't create it and assign it to a variable, but we just pass it in on the fly. And, oh, actually, stop. And let's add the result here, and then run the method again. So now there's going to be 2 zeros at the end. And there's a result. So this is how we can inject different behaviors into the execute method. And we do this with Lambda expressions, but as I just showed you, we could also do this by creating a class that implements the interface. However, commonly we do this with Lambda expressions. So now that we've seen how we can use these Lambda expressions to implement functional interfaces and how we can use these as input for methods, there's one more thing I'd like to mention about Lambda expressions, and that's related to its scope. Let's have a look at this in the next video. Let's discuss the scope of Lambda expressions. Scope is the area in which a variable is available. So for example, when we declare a variable inside a method, a local variable, this variable is only available inside that method. When we declare a variable at the class level, it can be accessed throughout the entire class. Unlike methods, lambdas share the scope of their enclosing environment. Therefore, you cannot use names for identifiers in lambdas that already exist in the closing context. Simply put, that means if I have an int x inside my method, I cannot call the input parameter of the lambda x as well, because that would result in a naming conflict. Lambdas can access fields and methods of their enclosing scope, but they can only access local variables if they are final or effectively final. I honestly quite like the term effectively final. It means that you could put final in front of the variable declaration and it would still compile. Okay, so Lambda expressions share the scope of the enclosing environment. That means they don't have their own separate scope. And this has some important implications. Again, identifier names in Lambdas cannot be the same as those in the enclosing scope. This is because having two identifiers with the same name in the same scope would cause ambiguity. Lambdas can access fields and methods from the enclosing scope, as they share the same scope. But Lambdas can only access local variables from the enclosing scope if they are final or effectively final. This is because the compiler needs to ensure that the variable value does not change during the Lambda's execution. Let's see an example in IntelliJ. Here we have the class Lambda scope example. I'm going to give it a main method. Let's give this a local var 6. Like this. And then we can implement the calculator. And I can say, well, let's call them A and B this time, becomes A times B plus local var. And I can access this. Why? Well, it's because local var is effectively final. Let's create an int for result. I'm going to say calculator.calculates. And I'm going to pass in 3 and 5 again. And then let's print the result so we can actually see it. So if we run this, the result is going to be 21. It's going to 3 times 5 and then add 6. And this is allowed because local var is effectively final. Let's undo that and inspect the red squigglies. So I'm going to update local var to now be, 7. There we go. And you can see we get red squigglies. So I'm going to hover over them. And it's going to say variable used in Lambda expression should be final or effectively final. There you have it. What we can also not do is, instead of A, call this local var. Why not? Well, because local var already exists in the outer scope. And it says local var is already defined in the scope. There you have it. Let's change this back. Likewise, we could also not call this A. That would result in the exact same problem. And also this one not being known, of course. But you can see here now that A is already defined in the scope. And alright, that's the last thing you need to know about Lambda expressions for now. We can say that the rest is out of scope. I want to show the built-in functional interfaces in Java. And these play a central role in functional programming. So we'll have to know the built-in functional interfaces and be comfortable implementing these with Lambda expressions before moving on to functional programming. In this video, we'll explore some of the built-in functional interfaces provided by Java. There are a lot of them, but I don't want to overwhelm you, and I'll focus on the most important ones for now. The built-in functional interfaces are commonly used in functional programming. These signatures of functional interfaces help us achieve uniformity across different applications. On top of that, the built-in functional interfaces are designed to work seamlessly with Java's functional programming features, such as the Stream API, which you'll see very soon. Let's take a look at some of the most common built-in functional interfaces. First of all, we have supplier. A supplier represents a supplier of results with a single method tGet. I can remember this name since it's the supplier. It doesn't take any arguments, but it does give you something back. Please mind, these t's are the generics, so we need to specify the type when we create them. T could, for example, be a string, an integer, or a custom class, for example, student. Then we have the consumer. And consumer is going to have one method, accept. That's going to take one parameter as input, do something with it, and then return nothing. Then we have the predicate, which represents a Boolean valued function. So it's going to take one argument and then return a Boolean, which means true or false. The method is called test. This is used a lot for filtering, for example. And then we have the function, and function accepts one argument and produces a result. As you can see, this one has two generics. So the input and the output, the input T and the output R, they could be of different types. So for example, it could be that it accepts a string and then it returns perhaps the length of the string, which could be an int. Now let's see how to implement these functional interfaces without using Lambda expressions first. And this is not because you would normally do this. I'm just doing it this way to help you understand the Lambda expressions and the built-in functional interfaces better. So let's go ahead and make this implement the supplier. And I'm going to make this implement a supplier with the generic string. As you can see, I now need to import the Java util function supplier. So let's override the single method get. Since it's a supplier of type string, the T is now a string. So it's going to return a string, gets, and let's just return a hello. So right now we have a supplier example. I can go ahead and create another class and instantiate this one. So in here, I'm going to create a main method. I can create an instance of our supplier example. And on this supplier example, I could call the method get. So this is not how we would normally do this. Normally, we would do this with Lambda expression. So for example, this. And please mind, I need to specify the generic here. And again, I need to implement the supplier. Let's call it S1. And then in here, I could do the exact same thing. It doesn't take any arguments. The arrow, and then return hello, like this. This would be the same thing that I'm doing here, but then with the Lambda expression. Let me show you how to implement the consumer. So let's also make a consumer of type string. And consumer is going to be a bit different. I need to import it as well. I'm going to call it C1. It's going to consume, in this case, a string. And it's not going to do anything, so let's just go ahead and print this string. Like this. And I can go ahead and call the method accept. And then just say hello from consumer. And that's how to implement the consumer. Then we have the predicate. And predicate is going to return a true or a false. So let's just create a predicate string. And this one is going to determine whether the length of the string is smaller than 5. So if s.length is smaller than 5, it's going to return true, otherwise it's going to return false. So let's actually go ahead and print result, p1.test. Then when we say, hello everybody, this is definitely going to be longer than 5, so it's going to print false there. And lastly, we have the function. Function takes two generics, so I need to specify two generics here. Let's have it accept a string and an integer. And call it f1. And by the way, do you see that I can use the same name for the Lambda parameter? That's okay, just like I can have the same parameter name for multiple methods inside my class, that's all fine. I just cannot use local variables in the same scope as parameter names. Okay. So this is also going to take a string, and then it's going to return the length of the string as an integer. So in here, well, actually, let's print this too. f1.apply hello. So that's going to print 5. The reason it's printing it is because I wrapped it inside the system out print line. And I'm going to run this so you can see all the results. So we get hello from consumer. which is coming from line 16. Then we get false, which is the result for predicate. Hello, everybody is not smaller than 5. And then we get 5, because that's the length of hello. And that's how we implemented these functions. So as you can see, the first time I did it, I was creating a special class, supplier example. But that's not how we normally do it. So since we understand Lambda is probably well enough right now, we need to implement these functional interfaces with Lambda expressions. So for comparison, this Lambda expression over here, nothing becomes hello, is the equivalent of this method over here. Public string get, return hello. It's a lot shorter, and it can determine what to implement because the supplier is a built-in functional interface. Here you can actually see the Java code for the supplier. I did this by doing command-click on it. I think it's control-click for Windows machines. And this supplier, as you can see, is returning t, which is whatever you specified, and the method name is get. Remember that methods and interfaces are always public by default, so it's a public method. It doesn't take any arguments, but returns whatever t is. So this is not common. It's way more common to do with Lambda expressions. So here, no parameters, return a string, hello. Here, one parameter s, and it knows that this is of type string because the consumer is of type string. And if we look at the accept method in consumer, we can see that the t is of type t. So in this case, it's going to be a string. And we can just output that string. That's what we're doing here. Then we have the predicate, which is returning a boolean and taking something that we specified, which is also a string in here. And lastly, the function, which is taking a string as input and returning an integer. So we've seen how to implement these functional interfaces. In the next module, we'll use this to learn functional programming. And we'll explore functional programming concepts such as method references and the Stream API. But before we go there, please make sure that you're comfortable with writing Lambda expressions and implementing these functional interfaces before you move on. Otherwise, you're definitely going to get stuck. So make sure to do the exercises, and once you're ready, I'll see you at the functional programming module. In this video, we'll introduce method references in Java and explain how they can simplify your code when working with functional programming. Method references are a shorthand notation for Lambda expressions that refer to existing methods or constructors. They provide a neat way to pass an existing method as an argument, making your code more readable and straightforward. Once you're over the syntax, that is. The syntax of a method references doesn't have the arrow. It has a double colon. Here's what it looks like. Name, colon, colon, method name. What should be on the place of name depends on the type of method reference. It can be a method on an instance. In that case, we need the name of the instance. It can also be the name of the class. For example, when it's a static method. There are 4 types of method references in Java. We can reference to a static method. We can reference to an instance method of a particular object. But we can also reference an instance method of an arbitrary object of a particular type. And we can reference to a constructor. Let's explore them in IntelliJ. Alright, let's start with a reference to a static method. Alright, so let's implement a function. And this function is going to have integers as input and return a string. And what we're going to do is we're going to do number to hex string here. And I'm first going to implement this with a lambda to show you how this would be done. So our input would be some value, an integer, so I take an I, but we could call it anything. So I say I, and then I say integer, and then we're going to call the static toHex string method on it. And in there, I'm going to pass in the I, like this. So this is the Lambda way to do it. This isn't new. I mean, it might still be relatively new, but we've seen this already. Let's see the method reference way to do this. So number to hex string method reference. So what we're going to say here is integer, since that's the name of the class, double colon, and then to hex string. And we don't need to pass anything in, because it can deduct from the context that we need to pass in the integer, since it's a function. And then we can call the method on here exactly like we would call it for a normal Lambda expression. So we'd go number to hex string method reference dot apply. And then we could pass in some number. And if we want to see the result, which we actually might, I need to surround this with a system out print line, otherwise we won't see anything. So let me run this code so we can see the result. And there you go. If you don't know what this does, you might want to look into hexadecimal numbers. It's quite a fun topic as well. It's unfortunately out of the scope of this course. Let's have a look at the next one. We're going to create a reference to an instance method of a particular object. So let's create some sort of string. I'm going to say string called string prefix equals hello, like this. I'm going to use function again, and this function is going to take string as an input and give string as an output. And I'm going to call this greet. And then I'm going to start implementing it with a lambda again. So I'm going to say s arrow prefix plus s. There we go. But this would be nicer to do with a method reference. So let's go again, say function string string. And we call this greet method reference. So this time we use prefix, use a double colon, and then specify concat. And this is enough, because it can figure out that we need to pass in the string and it will use the prefix. So let's show the result of this one too. And this should print hello you. Let's run this code and see for ourselves. And there we go. Let's use a built-in interface that we haven't seen yet. And we're going to use this for a reference to an instance method of an arbitrary object of a particular type. So what is a by function? By function is a lot like the function, but instead of taking one input, it's taking two inputs. And this one is going to take two strings as input. So the first two are the parameters, and the return type is going to be an integer. What I want to do, I want to compare the two input strings. I want to return 0 when they're equal, return a positive number when the first one is bigger, and return a negative number when the second one is bigger. And I'm going to do this by calling the string compare to ignore case method. So let's again first do this with a lambda expression. So we have two input strings. And what we're going to do, we're going to pass them to the method compare to ignore case. And I pass in s2 as the argument here. And we can also do this with a method reference. And that's done like this. We can say string compare to ignore case. Then based on the circumstances, it can actually deduct that it needs to compare S1 and S2, even though we never called them that. So let me show you that this is working. And let's add in two similar words, but then the difference is going to be the casing. There we go. And let's see the results for ourselves. And there you go. It returns 0, meaning that they're equal. And they are when we ignore case. All right, the last one is a reference to a constructor. A very common thing we want to do is to create a supplier that's returning some sort of type. For example, we could create a supplier for an array list of type string. Again, I need to import supplier, and I'm calling this list supplier. And then in here, I'll say array list colon colon new. This is actually the method reference way to do it right away. And then right now, I could go ahead and say array list type string, call it, well, let's call it names equals list supplier dot gets. And then we can go ahead and add some names to the list. There we go. And let's just prove this by printing the name. And this should print my name, Maaike. Alright, so when we use the method reference, we can leave a lot of more things to the context. And this way, it can deduct from the context what return type is going to be. Please mind, we can only use method references for existing methods. They're literally referencing a method. Another important thing to note is that the method that is referenced must have a compatible signature with the functional interface that we're implementing. In other words, the input parameters and the return type should match those of the interface's abstract method. And that's exactly why they can be omitted, since they must match anyways. In conclusion, method references in Java are an even cleaner way to pass methods as arguments, which can be particularly helpful when working with functional programming features. It's not always possible. It's only possible when we're using an existing method. In all the other situations, we'll still need the Lambda expression. In the next video, we'll explore the powerful Stream API and see how it leverages functional interfaces, Lambda expressions, and method references. Okay, this is quite an exciting point. All our hard work for understanding Lambda expressions and method references should start to pay off now. We have reached the point where we are ready for the Stream API. In this video, I'll provide you with an overview of the Stream API. The Stream API was introduced in Java 8 and allows for functional programming. This mainly comes down to making it easier to work with sequences of elements. It provides a more elegant and readable way to perform operations on arrays, collections, and other data structures. So a valid question at this point would be, what are streams? A stream in this context is a stream of data. And it helps, or at least for me it helps, to really think about a stream. I picture my data flowing in like water. And water typically comes from somewhere. It has a source. And the same is true for data streams. They have a source. We'll start with that in a minute, but let me provide you with an overview of what can happen to a stream. And let's picture the stream of data. A stream consists at least of a source and an end. I like to think of a glass of water as the end product here. The tap could be the source, and the glass of water could be the end. But there can be steps in between. For example, if we look at the river as a source for a glass of water, it typically takes some steps to come from the original source to drinking water. We call these steps the intermediate operations. There are several steps in between to clean and process the water and get our end result eventually. But of course, we're not talking about water. We're talking about data. Let's say we get data from the database. The data coming from the database can be turned into the source. And we want to filter this for certain conditions. The filtering steps are the intermediate operations. We then, for example, want to write the result somewhere. And this writing is the terminal operation that's going to end the stream. In the next video, we'll start at the source and look at how we can obtain a data stream. Let's talk about source operations. The different ways to get a stream are called source operations. We use these source operations to create streams in our code. Stream is just a type of object. We're going to see the following ways to create streams. We're going to be creating a stream from a collection, creating a stream from an array. We're also going to use two methods, the stream.iterate method to generate a stream and the stream.generate method. Let's move over to IntelliJ. Let's start with the first, creating a stream from a collection. Well, in order to do that, we need a collection. Let's create a simple collection of names. And I'm going to use the rabbit names that my daughter has. So let's go ahead and say arrays as list. And then let's specify the rabbits. They're very original rabbit names. And then we can go ahead and create a stream of type string. And let's just call this the name stream. Import stream from Java util stream. And then go ahead and simply say names.stream. And that's it. We have created our first stream. We could do something similar with an array, but then we'll use the arrays.stream. And it's a little bit different because we do need the static method for this. So let's create the array. I don't want a space there. Same names. So here's how to create the stream this time. Again, it's going to be type string. And let's just call this names array stream. So instead of going names array.stream, that doesn't exist. We can say arrays, the helper class, and then go stream and pass in the array that we want to turn into a stream. And there we go. This should take care of it. So I find myself using these quite a lot. The .stream in particular. Let's see how we can create a stream using the stream.iterate method. And this is where we start to need Lambda expressions already. So let's just start by creating infinite stream of integers. And what we're saying here is stream.iterate. And iterate is really going to do that. It's going to iterate. We need to specify a seed and then an iterator. So the seed is going to be the starting point, which is 0. And then I need to go ahead and specify how I'm going to get to the next value. And here's how I'm going to do that. I'm going to say n as our input, and then just do n plus 1. So this is going to increase the variable 1 infinitely. We can use method on the streams to stop this, so don't worry. So let's go ahead and use the generate method. We're again going to create an infinite stream because the generate method is going to be called until it's going to be told to stop doing this. So let's go ahead and say stream double. And let's just call this random numbers stream. And then we're going to say stream.generate. And now, well, we might as well start using a lambda. We might as well start using a method reference already. We're going to use the math.random here. Right, so this is 4 ways to create streams. And we're going to use this a lot. But there are a few important notes that I definitely should make here. And the first one is that streams can only be used once. After a terminal operation is called, the stream is closed and cannot be reused anymore. If you try to do that anyways, you'll get an exception explaining that you can't do that. The second important note is that streams are lazily evaluated, and that means that they won't be executed until a terminal operation is called. In this case, we're not calling a terminal operation yet, and therefore nothing really happens still. So let's see how to get some action up there. In the next video, we're going to explore terminal operations in the Stream API and demonstrate how we can use them to complete the stream pipeline. This way, our streams are actually executed. We have just seen how to create streams. Now we'll learn how to end streams. I'll cover terminal operations in the Stream API, which are used to close the stream and produce a result. Terminal operations are crucial for completing the stream pipeline, as they trigger the execution of the stream. Let's move over to IntelliJ and see some common terminal operations in action. So here I have already in my comments which I'm going to show you, and this is a lot, but I will go over them, so don't worry too much. Alright, so in my comments I have all the terminal operations that I want to show you. There are quite a bit of them. And I'm going to do this using the names stream. As I already mentioned, I can only use a stream once, so I need to recreate it a few times. So let's start with the for each. The for each is going to do something for every element in the stream. It's not really producing a result, it's just doing something. So let's go ahead and say namestream dot for each. And then you can see that for each expects a consumer. And we know how to implement consumers. They take something and return nothing. So let's go ahead and implement this with a method reference. And I'm going to do a very simple one, just a print line. There we go. So this is simply going to print all the elements in the stream. Let me show you. There we have them, all the elements in the stream. Let me show you count. Count is going to return the number of elements in the stream. Before I'm really going to show you count, I actually want to show you what you cannot do. And that's using namestream again, because there's been a terminal operation on it already. So if I say count over here, and I then run the play button, we'll get the exception I was talking about. It's the illegal state exception. And has a very clear message. Stream has already been operated upon or closed. So we need to create a new stream. Well, not to worry, we can do that. I just go ahead and say names.stream and then do a count. So this count is actually going to return a long, as you can see here. And I want to store the result in this long number of items. There we go. This is going to store 3 in number of items, because the stream has 3 elements. And then we have min and max. They're going to return the minimum and the maximum element. In this case, the minimum and maximum are based on the alphabet. So let's go ahead and go string min equals names.stream. And as you can see, I can pass in a comparator. And this comparator is needed for it to figure out how to determine the min and max. So let's go ahead and implement the comparator. So the comparator is a special method that's taking 2 elements and then returning an integer. That's going to determine which one is bigger. So I'm going to be lazy. I'm going to specify S1 and S2, the first value and the second value. And then in here, I'm just going to say S1 compare to ignore case S2. So this is actually a very valid red squiggly. It says required type is string. As I said, I would expect a string. But it says, no, what I'm returning is an optional. And we haven't seen optional yet. Optional means that it may or may not actually return a result. Because if this stream is empty, there's not going to be a result and it cannot store this in the string. So instead of having the string, I'm going to make this an optional of type string, like this. Just think of this as some sort of post box, and there may be some post in there, in this case a string, and also may not be some post in there. And in order to get this value out, we need to do the .get. If it's not there, this might actually throw an exception, but it's there, so we don't need to worry about this. So let's go ahead and run this so we can see the result. Please mind, I did not print the number of items because it's a bit straightforward. And as you can see, the minimum here is Mandarin, since that comes first alphabetically. And max, it works in a very same way. In this case, it would print walnut, since that's the last one alphabetically. I'm not going to show it. And then we have all match, any match, and non-match. And these are actually very, very similar. So all match is going to check if all the elements in the stream match a given predicate. So let's go ahead and say here, optional Boolean. Let's just call this all match. Or let's say bigger than 5. And then in here, I'm going to create a new stream. And I'm going to call the all match function. And now I need to provide it with a predicate. And remember the predicate, it takes an input element and then it returns a true or false. So let's go ahead and say s becomes s.length bigger than 5. And this will give me red squigglies because the return types, they do not match. It's simply going to provide me with a boolean. And that's just because my mind was with the optional still. This is just going to give a boolean, whether all of them match or not. Please mind that if you do an all match and you have an infinite stream, your code will very likely not finish ever because it won't know if all of them match if the stream is infinitely long. It will have to keep on checking. Oh, and let's actually print the all bigger than 5. And there we go. Before I'm going to run this, I'm also going to implement the any match and non-match. These are very, very similar. So I'm going to be copying this code for the any match. So what the any match is going to do is just going to check if any of them is bigger than 5. And as soon as the first one is bigger than 5, it can conclude, aha, one of them is bigger than 5. The value is true, I will complete. So how many elements this will evaluate depends on whether a match is found or not. And let's say we have an infinite stream. This may or may not run forever. If it finds a match, it will stop. But if it doesn't find a match, it will just run forever. So if you're doing something that's not going to find a match, it might actually be stuck forever. But if it does find a match, it will stop for an infinite stream. So that's an important thing to take care of. And then we have the non-match, which pretty much does the opposite. It's going to check if none of them match. So as soon as one of them matches, the non-match is false. So in this case, it will come across the first element and already conclude that none of them are bigger than 5. Let's actually also update the methods here, otherwise it's not going to work. So there we have it. So I implemented 3 of them, all bigger than 5, any bigger than 5, and none bigger than 5. So all and any should be true and none should be false. Let's run this code and see the results. And as you can see, it prints what we expected. Okay, 2 more. We have collect and reduce. Again, they're a bit similar, but let's treat these separately because they're very important and a little bit complicated. So collect is going to transform the stream into a different data structure, such as a list, a set, or a map. This is a very, very common thing to do. So let's again create a stream. Well, actually, let's first specify the list that we want to create. Let's call it names list. Now we're going to say names.stream.collects. And then you can see we can do collectors to list. And this is going to store a list of strings in the names list based on the elements in the stream. So there's actually a new way to do this. And it's actually a little bit nicer, so I want to show you. But you'll still come across the old way a lot. And this new way is quite new, so you might not have the option to see this in your code base just yet. And that's the to list. How lovely is this syntax compared to the other one? So this is available when you use anything after Java 16. Alright, and then we have reduce. And reduce applies a binary operator to the elements in the string, reducing them to a single value. So what I'm going to do, I'm going to create an optional string, because there may not be any strings in there. Total string. There we go. And here I'm going to say names.stream. And I'm going to say reduce. Then I need to specify my binary operator, but I'm just going to go for the string concat. So that's going to concat all of them together. And then I want to print result. And again, I need to do a get because it's an optional. And if there would be no value, that would be a problem, but I'm quite sure there will be values because I hard-coded them myself. And there we go. We have the total result at the very bottom, which is all the names of the rabbits concatenated. Great. So this is all really great, and we've seen some examples of terminal operations, and we should have a better understanding of how to complete the stream pipeline and produce a result. But in the next video, it's going to be really fun because we're going to dive into the intermediate operations, and we can use this to modify and filter the elements in the stream before we call the terminal operation. In this video, we'll explore intermediate operations in the Stream API. These operations can be used to modify or filter elements in the stream before the terminal operation is called. Intermediate operations are optional and can be chained together in the stream pipeline. We'll cover some common intermediate operations and demonstrate their usage with practical examples in IntelliJ. Alright, so this time I'm not going to sit you through the typing, but I am going to walk you through all of these examples. I did expand the list a little bit for the sake of these examples. So here we see the filter, and the filter filters the stream based on a predicate. And the predicate that we're having right here is that the name should start with a B. When the predicate is true, the element will stay in the new stream. When it's false, it will be removed. So the name starting with B is only going to be a stream with the element Bobby in it. And then we have map. I find myself using filter and map a lot. Map applies a function to each element in the stream. And as you can see, after this map method, we no longer have a stream of strings, but a stream of integers. And that's going to turn the stream into a stream of integers representing the length of the strings. And again, you'll see that we need to use a method reference here. So I hope at this point you understand why method references and Lambda expressions are so important. And then we have flat map. Flat map is a function that we can use on all the elements in the stream that's going to flatten the results into one single stream. So on line 20, we have a little bit of a complicated object. We have a list of lists. And on this list of lists, we have two arrays, one holding Bobby and Django, two nice dogs I happen to know, one holding Mandarin, Walnut and Snowflake, three rabbits. So these two lists means that the first stream that we're going to be creating, the nested stream that's going to be created right there, it's going to have two elements of type list string. The first one is the Bobby Django element, and the second element are the rabbits Mandarin, Walnut and Snowflake. So the flat names that we're creating is actually going to turn these into a stream of type string containing 5 elements: Bobby, Django, Mandarin, Walnut and Snowflake. It's flat after this. There's no more hierarchy, there's no other levels, it's just one stream of elements of string. And then we also have peek. Peek is nice for debugging because it's going to perform an action on each element in the stream without modifying the stream. So if, for example, after a filter, you might want to see what's still in the stream, well, you can do this with a peek. And very common is to just print the result of a peek, as we're doing right here on line 24. We can also limit the stream to a certain number of elements, and this can be particularly useful for otherwise infinite streams. In this case, we're just limiting our stream to 3, even though our stream would have a size of 5 originally, so there will be 3 elements left. Then we have skip, and with skip we can skip some elements in the stream. In this case, we're skipping the first 2. So the new stream string is going to not have the first 2 elements, but it will have the last 3. Then we have distinct, which will remove any duplicates if they are present. In our case, this won't do a lot because we don't have duplicates. And lastly, we have the sorted. And sorted, well, it's a bit in the name, but it's going to sort the elements in the string according to a comparator. And in this case, we choose for the natural order. So at this point, we have all the ingredients of a stream pipeline. And with these intermediate operations, we can chain them together. So, for example, we could first do a filter, then do a map, then do a peek, and then end with some terminal operator. And this chaining and ending with the terminal operator is exactly what we're going to do next. We'll demonstrate how to use the Stream API for some practical examples. Let's demonstrate how to use the Stream API for some practical examples. We'll combine source operations, intermediate operations, and terminal operations to create stream pipelines that can process data. Again, I'm not going to sit you through me coding, but I do want to show you the results and explain them to you. There's 4 of them in total. The first one is for filtering and collecting a list of names. And we'll be using the list of names we have been using all this time, and I'm going to reuse it in the other examples too. So on line 10, we are creating a stream, and then on line 11 we're filtering the stream for names that start with a B. We then do a collect and turn it into a list. After that I print it so I can show you that this is working at the end. The second example is finding the longest name, and here I'm using the max terminal operation. You can see I need to work with an optional. And for the comparator, I am actually using the comparing int and then comparing on their length. I'm not doing the get, but in the output it will be clear now that it's an optional and it will display the value. The third one is a few more steps. It's a little bit more complicated. So what I'm going to do, I'm going to transform a list into a set of integers. Again, I'll start by creating a stream, and then I'm using the map operator. And this map is going to turn all the elements in the stream into its length, meaning the number of characters. And then I use the distinct, because I only want to have each value once. And then I am doing the collectors to set, and that's going to create a set of unique integers. Since this is creating a set, we don't strictly need the distinct, as it will tell us. But I just want to show you how we can actually go ahead and chain these intermediate operations. And you can see in the type hinting of IntelliJ what's happening too. So here we're having a string of strings, but after the map we're having a string of integers. And then the last one is me using a special collector, and that's the joining one. And it's going to join them, but with a comma in between them. So it's going to create one big string, concatenated names, and it's going to have a comma between all the different names. Alright, let's run this code and see the output. And there you go. You can see that the starts with the B only has Bobby in it. We do get Snowflake back as being the longest name. We then get the unique lengths of the elements in the stream, and you can see they all have different lengths. And then lastly, we get one string, comma separated, of all our names. So with these examples, you get an idea already what you can do with the Stream API. And actually, my examples have been quite simple so far, but it allows you to do a lot of complex data transformation with just a few lines of code. It still looks simple. This is a very nice way of dealing with your data. But this does take a mindset shift, especially if you're very used to using loops and if statements for this already. So let's make sure to get some practice before we move on to the Java memory. Let's talk about a theoretical but exciting part about Java, the Java memory. This is actually a huge topic that we'll only cover to the extent that is necessary at a junior level. This is such a big topic, you can write a book on it. Not to brag or anything, but I did. It's actually not really a big book, but still. Long story short, the coverage in this course is somewhat simplified, but it will help you to grasp the basics. Let's talk about the different parts of the memory in the Java runtime environment. And these include the heap, the stack, and the meta space, also called the method area. The heap is the memory region where objects are allocated. It's divided into sub-areas depending on how long objects live on the heap. Then we have the stack. The stack is the area where method calls, local variables, and references to objects on the heap are stored. Each thread in your Java program has its own stack. The stack is organized into stack frames, with each frame containing information about the method call, such as its parameters and local variables. Then we have the method space. The method space is the region where class information such as class names, method names, and field names are stored. This area is shared amongst all threads in your Java program. Let's say we have the following code snippet. When executing this code, the stack memory keeps track of the method calls. Right now, our program didn't start yet, so the stack is empty. As soon as the code starts, a record gets added for the main method. The first line of the main creates a variable x and gives it a value. This is added to the stack record. The next line, int y is 7, does something very similar, and y is added to the stack record as well, including its value. Then something interesting happens. Our main method calls another method, and since this is another method, a new stack record is created for this. Variables in this method are added to this record, and from this method we cannot access variables in other stack records. This pretty much explains the scope of local variables. These are only accessible inside the method. So the next line creates a new int sum, and this is added to the add methods record on the stack as well. Next, the method returns the value and is done executing. The stack record is removed. After that, the main is done too. There are no more records on the stack and the application is done. This application had no objects, so there was no need to add in the heap. Let's modify the example to use an object. We are now creating a car, setting the color, then calling a method with this car and another color. In this method, we change the car to the new color. Let's walk through it line by line and see what happens to the stack and heap memory. Alright, so on line 1, we create a new instance of car. And this car is on the heap. So on the stack, we're not storing the car object. Instead, we're pointing to where we can find this on the heap. We call this a reference. And right now, I use add 100 to symbolize this reference. On the next line, we set the color to blue. And you can see that the color on the car now has the value blue. Next, we call the method modify and we send in the reference of our car and the color pink. So you can see that both the add and the main now hold a pointer to the same reference on the heap. And in this method, we actually change the color of the car. So instead of blue, the car is now pink. After this, our method is done executing. And we're back in the main. And what we want to do here is print the value of the color of the car. And as you can see, our main is pointing to the same object on the heap. And even though in the main method we set the color to blue, we passed in the reference to the modify method, which updated the value to pink. So the key here is that there is only one car. Compare it like this. If I have a car and you borrow my car and you then paint my car pink, when you give it back to me, it's still going to be pink. I might actually be pleased, but still. There's only one car. That's the point here. And when we pass in the reference, we're pretty much pointing to the car on the heap. And both the main and the modify, we're pointing to the very same method. So it's actually slightly more complicated than this, because the string is an object itself. So there will be objects for both the strings on the heap as well. And the car object will point to another object itself. So on our car object, we hold a pointer to another object. And as you can see, the string value for blue is also still there, but we're now pointing to the one with the value pink. And then, I'm not going to explain this in any detail. I just want to give you a heads up. Strings are actually a special type of object. And the Java memory deals with the string pool to take care of them. But this is definitely beyond the scope of what you need to know right now. When we allocate memory, we have less memory available. Luckily, memory can also be deallocated. The stack is deallocated automatically. As soon as a method is done executing, the stack frame gets popped. For the heap, this is more complex. The garbage collector takes care of this. Let's explore how this works in the next video. Garbage collection is the essential process that helps manage memory and prevents memory leaks in your Java programs. When we allocate objects on the heap gets a bit fuller. A healthy application has enough heap memory available. In order to keep having enough heap memory available, the objects on the heap will have to be removed when they're no longer necessary. Garbage collection's main purpose is to automatically reclaim memory occupied by objects that are no longer in use. This process is performed by the Java garbage collector, which takes care of handling the memory management. The garbage collector removes elements that no longer have a connection to the stack. In this example, memory location 100 and 102 have a connection to the stack. 101 can be removed, because it no longer has a connection to the stack. Another situation is possible as well. Let's assume the method called repair holds the reference to our car object. When this method is done executing, the frame gets removed from the stack. And this can have the implication that an object on the heap becomes unreachable from the stack, because no references are stored to it anymore. The objects then become eligible for garbage collection. And they can be removed by the garbage collector. This figuring out which objects no longer have a connection is not as easy as it seems, because you don't want to freeze the entire application to figure out which objects have a connection and remove all the others. At the same time, not freezing it might make the scanning a bit more hard, because it might be possible that this object on the heap, that we think has no connection to the stack, was recently added. Java has smart tricks for this. These are the garbage collection algorithms. There are various garbage collection algorithms, such as the mark and sweep algorithm, the copying algorithm, and the generational algorithm. Each one has its advantages and disadvantages. To monitor garbage collection, you can use tools like Visual VM or the Java Mission Control. And to improve the performance, you can adjust heap sizes, select the appropriate garbage collection algorithm, and set garbage collection parameters that best suit your application's needs. This is called GVM tuning. And even though you can do all this, you cannot, from the code, trigger garbage collection. This is really something that the GVM decides upon. If you're ever in the position that you need to optimize an application, you'll need to know more about the different algorithms and the tuning. For now, you'll be just fine with the defaults and understanding what garbage collection is. It also helps to understand two common problems that can arise. These are the stack overflow error and the out-of-memory error. We'll cover them in the next video. In this video, we'll explore two common memory-related errors in Java: stack overflow error and out-of-memory error. We will discuss the causes of these errors and how to prevent or resolve them in your programs. Let's first state that error is a throwable, just like an exception. But other than an exception, our program is not expected to recover from an error, so we're not handling them. A stack overflow error occurs when the stack size of a thread is exceeded. Common causes of stack overflow errors include deep recursion or large stack frames. To prevent or resolve stack overflow errors, you can increase the stack size or refactor your code to reduce stack usage. Commonly, it's a coding mistake that causes this. So when you get this, check whether your method is calling another method that's calling your method, etc., without it needing to do this. Alright, the next one. An out-of-memory error occurs when the Java heap runs out of space. And by that, I don't mean this. I mean that this error can be caused by creating too many objects, not releasing references to objects, or having objects with large memory footprints. In other words, the heap might get full. To prevent or resolve out-of-memory errors, you can increase the heap size, use appropriate data structures, and employ proper memory management techniques. Or, also not seldomly, fix the coding mistake that led to this. For example, using a static collection and storing large objects to this. The static collection will keep these large objects on the heap alive for the entire time your application is running. This can cause problems. And yes, I do speak from experience. Remember to consider the stack size and heap size when writing your code. If you get one of these errors, first check for common mistakes. If that doesn't fix it, and your application really requires more memory, you can learn how to tune the Java memory to fix this. For now, this should be more than enough to get you started. Next, we'll be dealing with multithreading when we discuss concurrency. It's time to have even more fun with Java. In this module, we'll be creating a few relatively simple games. In order to create games, we need to be able to take input from the user. This is something that you don't do very often in Java like this anymore. Commonly, some special front-end application is connected to get user interaction. But we're going to learn this just for the sake of these projects. It's not very hard, and it does add a fun thing we can do. In order to get user input easily, we'll use the scanner class. The scanner class is part of the Java util package, and is a simple text scanner which can be used for parsing primitive types and strings. It's useful for reading user input from the console. The scanner class provides several methods to read different types of input. We can use nextInt for integers, guess what, nextFloat for floats, nextDouble for doubles, and nextLine for strings. These methods just read the next input value of the specified type. Let's see an example in IntelliJ. So we first need to create a new scanner, and that's done like this. Of course, we need to import it. And then we say new scanner system.in, specifying where it should scan. Then I'm going to output a certain message. For example, please enter your name. Then I'm going to say string name equals, and then let's just do scanner.nextLine. And then let's output a message. Hello, plus whatever name was entered. Okay, I'm going to run this to show you how this works. We're not done yet though, but let me show you this. As you can see, it prints please enter your name, but as you can tell, the application is still running. It's waiting for me to enter my name, so let me enter my name. Then it's going to grab my name from the input, store it in name, and then use it for the next output message. When we're done with the scanner, it's a good practice to close it by calling the close method. This prevents any resource leaks, especially when we're working with files. In our example, we would have to add scanner close before the end of the main method, like this. The last thing I want to show you here is that we can also scan for ints. So let's make another output. Please enter your age. And then we say int age, and now we need to use the next int. So I'm going to say scanner next int. And then in here, I'm going to go ahead and just print the age. I mean, I could do an if statement, do something with the age, but we're just going to say your plus age plus years old. And then we close the scanner. Let's run this again. So the first pause is after please enter your name. Well, still the same name. Please enter your age, entering my age, and there we go, using it in the output statement. So this is how to work with the scanner class in a nutshell. We can use it to read user input, and we need to close it when we're finished. Now we're ready to use the scanner class in the Java projects to create some games in this module. Have fun!